Let me just thank the organizers, of course, for putting together such a wonderful and comprehensive program. So I got the very hard mission of providing a review on this topic, which is kind of interdisciplinary. So currently has people working together from high energy physics, people from pure relativity. So there's a lot going on. So I thought, of course, I'm going to start from just the previous time such a topic was reviewed in this conference, which apparently was never. So because it's the first time, I'm going to start with just basic ideas. Hopefully, will be some kind of pedagogical introduction to the topic. And hopefully, by the next 40 minutes, we will all make it to the state of the art computations. So, of course, let me just thank my collaborators and my friends who I've been having the pleasure to discuss these topics, and I've learned so much from them. And in particular, I would like to say that, as I said, there's a lot of people working on this, and please excuse me if I forget one or two references. I would probably not be exhaustive in terms of references. Okay, so let me just start by providing a general picture. So we know that general relativity is one of the prime examples of an effective relativity. This means that it describes, to the best of our knowledge, the low energy regime of putative quantum gravity theory. And as such, it has beautifully succeeded over the last 100 or so years in making very precise predictions at the scales we can currently measure with our technology. Okay, but as we know, as technology progresses, so does the precision of our detectors. And even though quantum measurements are still out of reach for our detectors, we can nowadays test GR to an unprecedented, to an exquisite precision, which is expected to increase over the years. So in a sense, we have been very lucky because the technology we have been developing for detecting gravitational phenomena have been keeping the pace with our current estimations derived from Einstein's equations. So as we know, as technology progresses, we're going to need more precise estimations. Okay, so this is just a general picture, but you can tell already that this brings up two major problems. And these problems have been around for, as I said, 100 years or so. The first one is actually, how do we solve Einstein equations for realistic, time-dependent dynamical processes that happen to occur very commonly? And the second is, what observables of GR should we focus all our machinery in computing? Okay, so what are the right observables we should be discussing? So I'll just leave you with these pictures, and you can tell what kind of observables we can derive from them. So let me be more precise. The first problem has to do with the fact that in graduate school, in order to devise exact solutions for general relativity, we usually assume very simplifying assumptions, such as high amount of symmetry. So we assume that there's some time-like Killing vector, there's some spherical symmetry, or there's some symmetry of the base manifold, or we look for BPS states and so on. And we arrive at these very nice and beautiful symmetrical solutions that we know and love, and they have very interesting properties. Some of them are integrable, they have very remarkable interpretations. Here you can tell from a textbook, this is from Elders and Kuhn in the 60s, that all these solutions have certain interpretations. A1 is, of course, the Churchill metric, there's the symmetric, and so on. So all of these solutions are remarkable in a way or another, but however, they fall short when we want to describe more realistic scenarios. Okay, and such realistic scenarios that we deal with today can be, for example, the perturbation of a black hole background by something that's not symmetrical, or the actual merging of two black holes. Okay, so that's the first problem. What's the second problem? Well, the second problem is that the main observables. So what are the observables we need to compute? So the main observables, for instance, we compute in quantum field theory, are scattering amplitudes. And we know that scattering amplitudes have been very successful because we can measure cross sections, and they have driven so far our current success at large particle accelerators. So the cross section is something concrete that we can estimate. But we know infamously that such a framework cannot be applied to quantum gravity because of the presence of UV divergences. So we cannot get such predictions from quantizing a theory of gravity. Okay, so scattering amplitudes at face value seem not to be a good candidate for observable. So instead of doing that, in GR we consider a similarly unrelated set of observables. So we consider, for instance, the gravitational lensing. So basically, we examine pictures of our observations of electromagnetic radiation, so we can tell what's the polarization of the light that's coming to us. We can look at in gravitational wave astronomy, certain fluxes, time delays. All of these observables are encoded in the waveforms that people analyze. So there's a similarly unrelated set of such things. But there's a problem with that. And the problem is that these are, of course, happen to be very difficult to compute for realistic situations, such as I said, the merger and so on. And in the case of the gravitational wave merger, for instance, we need to rely on certain combination of analytic methods, so-called post-Newtonian theory. So the post-Newtonian theory basically is a perturbative approach to solve the two-way problem in general relativity. But because instance equations are highly nonlinear, post-Newtonian theory, this perturbative approach escalates very quickly and becomes increasingly hard to get a handle on. Okay, but if you do want to get a handle on, and you go and do post-Newtonian theory, something like this in the left-hand side is what you're going to find, tons of diagrams that you have to compute. And when you're computing them, you're solving some equations. Usually, you're going to use a computer. This kind of reminds us, of course, of the complexity associated to computing Feynman diagrams and precision processes in the scattering of fundamental particles. So in both cases, we have to compute a huge number of diagrams. We have to perform integrations and so on. And it's not surprise, as I'm going to show now, that these two kinds of complexities are completely, they are very much related. Okay. So the same kind of tools we use for computing these processes in quantum chromodynamics can be used for computing certain processes, but in a very particular and different way than the post-Newtonian theory. Okay, so that brings me to the goal of the talk. So I pretend to give you a flavor on how we can use scattering amplitudes in quantum field theory, scattering amplitudes in a theory coupled to gravity, to define first and second compute classical observables in general relativity. Okay, moreover, such observables are going to characterize dynamical scenarios such as black hole perturbations on, for instance, the two-way problem. So the nice thing about the observables we're going to construct is that they are free from UV divergences, since they are defined in a classical limit of the scattering amplitude. So what the classical limit means is basically we're going to consider low exchange momentum, and classically, we expect then to describe dynamics where, of course, the massive compact objects in general relativity, these gravitating objects are distances certainly larger than their charging rates. Okay, this doesn't mean that we cannot prove certain strong gravitational effects, but for sure we're not going to prove inside the horizons. Okay, so in such a regime, we can fully trust GR as an effective field theory. And indeed, we can compute observables to high accuracy in the Newton's constant. Okay, so that means we can do precision grading. And in particular, we can consider the exact dependence on the velocity of these compact objects that, for instance, merge or are going to accelerate because of radiation. So such a framework we will refer to as the post-Minkowskian theory, in contrast to the previously mentioned post-Newtonian theory. Okay, so the key words here are scattering amplitudes in quantum field theory. So the relevant scattering amplitudes can be computed using novel on-chip methods. Okay, what that means is that we're going to enforce the principles of unitarity and locality that are contained in this underlying quantum gravity theory. And by using such principles, we're going to bypass the evaluation of tons and tons of Feynman diagrams that you would usually have to put on the computer. And we know that such a powerful tool, which is unitarity, is completely invisible or at least is not manifest when we are solving Einstein equations perturbatively, say in the post-Newtonian approach, taking as face value, there is no way we're implementing unitarity. So this is a novel tool in this context. So the kind of amplitudes we're going to deal with, they are usually in high energy physics, and they are basically graviton exchanges. And the key point, of course, is we're only going to consider on-shell quantities. So this effectively provides a new analytical window into perturbation theory in gravitational physics. Okay, so let me start by just from the very basic construct certain observables in gravitational physics, just from amplitudes. Okay, so to begin with, I'm going to be interested in observables that can be measured at far distances in asymptotically flat space-time. So that's the case for a gravitational wave that is emitted by certain process, dynamical process. So here, these arrows are basically word lines that are colliding, or there's some dynamics. You can throw some gravitational perturbations and so on. But at the very end of the day, what you're measuring is gravitational flux. That's the outcome of this process. So this device here is our detector. Okay, so we place it at non-infinity. And of course, the key starting point is the perturbative approach. So I'm gonna basically expand around the flat metric, but this perturbation doesn't need to be linearized perturbation. It can have all orders in the gravitational constant. Okay, so the radiative part of the metric that I'm gonna look at, of course, measured at new infinity, is usually computed from a source. So this effective source, as you can see here, basically contains all these dynamical processes, right? So it's not just matter, it contains gravitational back reaction. So there can be all kind of, this is usually called the pseudo-linear stress energy tensor of gravity and so on. There can be all kind of dynamics happening in this blob. But at the very end, you're gonna have this effective source with compact support, and you're going to perform this Fourier transform. If you want to measure it at non-infinity, you can use some saddle point approximation. This is a textbook exercise, and you're going to get to the result that basically the metric that you're observing at non-infinity is directly related to the stress energy tensor, or the source, in momentum space, where your momentum is pointing towards your observation direction. Okay, that's the key point. Okay. So, but what's the problem? Okay, the metric itself is not an observable. Okay, it's a gauge-dependent quantity. So, in order to encode gauge invariant information of the metric, which is the radiative data that we're measuring, we are going to consider certain components. So, start by defining this null tetrad. So, all these vectors, I'm going to expand them in metric in this null tetrad. All these vectors are null. The only non-trivial inner products are these two. So, these are conjugates. Now, the way I think of this tetrad is as follows. So L here is pointing in certain direction in the celestial sphere. M plus and M minus are complex directions. Okay, so what they do is they parameterize the celestial sphere as a Riemann sphere. And because they are complex directions, they inherently have some ambiguity, which is a phase. Okay, so they transform in this phase, and this is a helicity transformation, so to say. So here L parameters certain directions, and M plus and M minus are just directions in this complex sphere in celestial sphere. So in order to extract certain components, for instance, if we are looking at the metric has helicity 2, or the gauge invariant definition of the metric is a helicity 2 quantity, which we call the Newman-Penrose scalar, or the Newman-Penrose amplitude, which is obtained from the Weil tensor as follows. So we project it with M, certain component which has helicity 1, and N, which is conjugate to the null vector L. Okay, so if our point of observation is at angles theta and phi, using our formula for the Weil tensor, because as I said, we computed the metric already at null infinity, and it's given by this formula. Using this formula and plugging this into the Weil tensor, we are going to get to this point where basically the Newman-Penrose amplitude is related to the source, where the momentum of the source is evaluated in the direction of observation, which is this L L vector. Okay, so that means because L is a null vector, that we can think of L as being some momentum of a certain perturbation, in this case, a gravitational wave. And because M and M minus and M plus are orthogonal to L, and they are also null vectors, we can think of M's as being polarization vectors. Okay, so this is basically what I'm getting from this Newman-Penrose scalar defined in this way, is that I'm contracting this polarization vector associated to L or K with this source with momentum K. Okay, and K is pointing in my observation direction. So if I look at the LSC formula, in quantum field theory, this is basically a classical limit of a scattering amplitude. Okay, so I'm contracting my source in certain components, and it's a gauge invariant quantity. Okay, so the scattering amplitude is obtained by considering a quantum field theory amplitude. Okay, so this is the invariant component of the Newman-Penrose amplitude. But we have to take this classical limit. Okay, so it's some quantum field theory amplitude where we emit a graviton and we take some classical limit. Okay, so interestingly, the derivation can be done in quantum electrodynamics. It's the same. Of course, it's a textbook exercise. But this funny thing where basically for certain spacetimes, which I just described, these are algebraically special, meaning that the Wien tensor has certain properties which make it special. For certain spacetimes, the two computations are closely related, and in fact, one can perform the computation in QED and obtain the result in gravity. And such a relation is called the double coupling. Okay, so just to mention that this has no additional difficulty as compared to electromagnetic case so far. So the question is you're asking right now is how do we actually take the classical limit? So we know that this amplitude is emission of a graviton, but we have to take the classical limit. So formally, in order to get a macroscopic observable, so a microscopic effect, you need to consider a coherent superposition of many gravitons to form this gravitational wave. Okay, and this has been done in different contexts by these authors. We will explain that in a second. But for now, let me just mention that in practice, we're going to take a single graviton and we're going to define its classical limit in a precise way, and that's going to give us the actual classical amplitude. Okay, the Newman-Penrose amplitude. So let me just give some examples of how this works. So the simplest case, just linearize gravity. So consider a massive body or consider many massive bodies. So these massive bodies, they are accelerating. It's a stress energy tensor. So just the matter part of the stress energy tensor is given by this formula. So they all have some initial momentum, P1, P2, P3. And I'm looking at momentum space. So I'm going to consider perturbations of momentum K. Okay. So this is a leading order in the energy of the perturbation. The stress energy tensor looks like this. So we're only gonna need such a leading order. And for instance, if we consider a single particle, so the simplest case, we can write, because there is no other particle, so conservation of momentum, the momentum tells you that the finite momentum is gonna be P1 plus K, where K is the momentum of the wave. And basically what you get from this equation is a delta function, because the denominators just subtract and you get this delta function here. And this is nothing but an on-shell condition. And in fact, you can very easily recognize this as 3-point amplitude of a massive scalar coupled to a graviton. Okay, so it's a unique 3-point amplitude. So these two computations are closely related. So one is the stress energy tensor of a single massive body, and the other one is a computation quantum field theory. Okay. Now, what happens if we have more than one body? So we have two bodies, for instance. So in linearized gravity, the graviton is going to couple to either one or the other body, right? So we have sum of two terms, and this is the amplitude. Now, in quantum field theory, we recognize this expression immediately at the Weinberg subfactor. However, we know that the subfactor is not the full amplitude. So if I take the 5-point amplitude corresponding to this process of a graviton emission, I know that in the soft limit, I'm going to get this soft factor times some other hard piece. So this is the standard soft limit. But now you may ask, we know that in classical gravity, the amplitude is a soft factor. Then what happens with this hard piece when we take the classical limit? Okay, so that's very, it's a small puzzle. So what actually happens? No, what happens is that actually we're solving different scattering problems. So this amplitude is classical already in the soft limit, but the problems are different. In quantum field theory, we compute a transition probability for certain states for which the momenta is fixed at the past and the past and the future infinity. Okay. Whereas in classical gravity, or in this initial value problem, the initial data is given by velocities and positions. So in this problem, in the classical problem, the momentum deflection is actually computed by integrating the equations of motion, and therefore it's not a variable. Okay, so these are different problems. They are both scattering. But we can take one problem to the other. It's very easy because we can translate using wave functions. So in quantum field theory, we can consider a wave function that describes a particle, a classical particle, moving into an asymptotic trajectory. Of course, now you might say there are no asymptotic trajectories because there's some long distance Coulomb drag, but let's ignore that Coulomb drag in linearized gravity. But this already doesn't matter. So we can consider these three massive particles evolving in straight lines. Now, the wave function associated to that, because basically you're starting from certain positions V1 and V2, is shifted in this form. So you have these exponentials. And you have an envelope that its sole role is to project your scattering amplitude into certain classical momentum. So this is the envelope function. We consider it has some width L, but the width L is very small as compared to the observation distance. Okay, so we're going to look at it from far away. And basically, the envelope is not, it has no width for such purposes. And the other thing you have to consider is that the momentum transfer associated to such a particle, because it almost moves in a straight line, it deviates very small, it has a very small deviation because this is linearized gravity. So the momentum transfer is going to be far less than the mass. Okay. So when you consider such wave functions and you project your quantum field theory amplitude in such wave functions, you get this formula. Okay. So this is the classical amplitude. So now you can take the soft limit at both sides. Remember, this was a soft theorem. This was a soft factor, sorry. And this gave you a soft theorem. So this has to do with the four particle amplitude. And you get that in order for the two sides to be consistent, you need this formula. So this formula tells you the classical momentum deflection as a function of only the initial condition, this impact parameter, which is V1 minus V2, the difference of positions. And it reveals that the role of this four-point amplitude is nothing but to integrate the equations of motion. Okay. So you can tell, for instance, that already here, because it's a Fourier transform in Q, only the divergent part in Q is going to contribute. So that means that we can only take the small Q limit. It's enough to consider the small Q dependence on this amplitude. That's precisely what we assume to begin with. Okay. Sorry, there's some background noise, or is it Nathan? Okay, thanks. So this relation, you can convince yourself that is basically a relation between the scattering amplitude and some effective potential that controls these dynamics. Okay, so this is the usual Born approximation where we relate the potential to scattering amplitude. So the difference between this and that is that this equation is expressed in terms of observable quantities. In particular, this momentum deflection is basically the scattering angle from the initial momentum to the final momentum is the scattering deflection. So it's not observable, it's a gauge invariant quantity. Whereas this is, of course, gauge invariant, and you need to assume some gauge and so on. But this is an observable in gravitational physics. And we just derive it from a scattering amplitude. So the previous formulae for the 5-point and 4-point amplitudes are the simplest cases for linearized gravity of something that we now call the Cosmology and Eikonal formulae, which link quantum field theory amplitudes to classical observables, okay, in the scattering problem. So these are both scattering processes. So we will now provide a complementary perspective on such a formula, okay, and that perspective is suitable for going to higher and higher orders, and at the same time we can relate that to the bounded orbit problem, which is actually, for instance, if you have elliptical orbits of one body with another, that's basically what you're looking at in the gravitational wave mirrors, in the black hole mirrors. So we want to understand what happens when these bodies don't scatter but keep orbiting each other. Okay, so of course I have not yet given a satisfactory explanation as to why these microscopic effects, such as scattering of a single quanta, a single graviton, lead to macroscopic observables in gravitational physics. Okay, so to the best of my knowledge, the simplest way to understand this is through the Eikonal approximation in quantum field theory, which has been developed long ago. Now, we consider, in order to introduce this Eikonal approximation, consider the 4-point S matrix of two massive particles. So here I have two different mass particles interacting through gravity. Now, we can take the low momentum transfer limit, which is basically forward scattering. Okay, so we assume in accordance with our previous assumptions that this momentum of the world line change is very, very, very little. So in this regime, the amplitude is dominated by these diagrams. That's something, that's just a fact, you can check. So because the momentum transfer is very little, so the momentum that flows from one line to the other, basically these propagators here, they are almost unchecked. Okay, so that means that basically this is a product of 4-point amplitudes, this ladder diagram. But if you look at it, of course, there is some loop integration running. So basically what you get is some kind of convolution between this amplitude and this other because of the loop integration. However, if you Fourier transform to certain position space, which is the impact parameter space, so let me define this chi as the Fourier transform of this 4-point amplitude. Okay. If I Fourier transform, then you undo this convolution of the loop integration, and you basically can factor all these ladders into a product of this quantity, which is a 4-point amplitude, okay, at 3 levels. So what you've just done is to resum all this loop expansion, all these ladders, in a factorized way into some exponential, okay, and the combinatorics just work out. So that means that all these microscopic processes, repeated one and over again, lead you to a macroscopic effect, which is the Eikonal phase, which is this kind that I just defined. So in particular, this Eikonal effect, the Eikonal phase is an observable quantity, and it can be used to construct the observables that we have just defined. For instance, if you take the derivative of the Eikonal phase with respect to B, remember of this formula, if you take the derivative with respect to impact parameter, you get the formula that I just presented 3 slides ago, called the Cosmology formula. Okay, so this Eikonal phase is at the heart of this construction. Now, the exponential structure of this matrix just reflects that gravitons are just in coherent superposition. Okay, in particular, it shows that the classical information can be contained in loop diagrams. Okay, we have so far only considered factorizations into 3 amplitudes. That's equivalent to computation in linearized gravity. So this computation has been understood in many different ways. And basically it's just computing a probe particle in the background sourced by the other particle. Okay, but by now, I mean, a few years ago, we understand how to extend this Eikonal approximation to something that's called the sublinear Eikonal and so on, in which the phase contains information not only of a probe particle scattering in another background, but actually the full gravitational two-body problem, meaning these two ways are of comparable masses. Okay, so it's not a probe limit anymore. And this Eikonal phase is computed by something that contains loop diagrams and so on. But these at the very end are classical results. Okay. So we have constructed this Eikonal phase. So how do we get observables from it? Well, basically, if you take this formula, which is the Eikonal approximation, this exponential that I told you, you can kind of interpret it as some path integral where you are fixing the initial and the final momentum. This is basically the scattering angle. So it's basically related to this momentum transfer. And you're integrating all possible trajectories basically by varying this impact parameter, which is the distance of the collision. So this shows you on the notes that this Eikonal phase is nothing but effective action. So it's an action that you put into your path integral, but it's only the radial part. Okay, so it only depends on this radial direction. So in Hamilton-Jacobi theory, you compute your effective action, and because you have some time symmetry and angular symmetry, basically the only interesting part is this radial component, and I'm claiming now that this radial component is nothing but the scattering phase. Okay. So one thing to note is that the angular momentum part is related to the impact parameter by this formula. Okay. But now that we have this radial action from the Eikonal phase, we can very easily solve the bounded problem, because so far we have considered the unbounded problem in which the radial action is integrated from this R, which is the point of minimum distances in the scattering situation. If we go to the bounded problem, basically you have to integrate this radial action from the two extrema of the motion. Okay, so they are related somehow. The observables that you can compute in the unbounded case, basically from Hamilton-Jacobi theory, by differentiating this radial action, are the scattering angle, the classical scattering angle, and the Shapiro time delay, which is a very important constraint that you want to compute for purposes of causality. So you want to have a time delay, not a time advance. So this is a very important observable in the scattering problem. In the bounded case, you have periastral precession, meaning that some bounded orbit is going to be deflected for each cycle, and the period precession, which is kind of self-explanatory. So the claim now is that there is a relation between those two, given by this radial action, and this was found by Porto and Cali, so I forgot to mention the reference. But basically, the relation is given by this analytic continuation. When you take the momentum of the incoming particle and take it to the imaginary axis, this takes the energy negative. And if you actually look at the Eikonal amplitude, you will find that it actually has poles for such momentum. And these poles, they were shown to be actually the spectrum, or at least a leading order in G. They correspond to certain atomic spectrum of this bounded problem. Okay, so this analytic continuation takes you from the scattering situation to the unbounded situation, sorry, to the bounded situation. Okay, so I hope by now I have convinced you that the Eikonal is a very powerful tool, and in fact, using the Eikonal approach and also some alternative approaches, people have been able to compute the classical part of the amplitude and the observables corresponding to 4 p.m., which are at precision of G to the 4. So these are the state-of-the-art computations in the post-Minkowskian theory. Okay, so these are equivalent to computing certain three-loop integrals, but the three-loop integrals, in fact, can be very easily solved using a novel technique, which basically it consists of IVP relations, which are differential equations for solving Feynman integrals. And you can use the post-Newtonian data, which is based in expanding at low velocities. You can use that as your initial condition, solve these differential equations, and get the full integral. Okay, so just to let you know that this has progressed and escalated a lot in the recent years. Okay, so that's the state of the art. And moreover, you can include radiation effects. These are related to the binary part of the amplitude, where there's some unshelled particles being exchanged. I'm not going to talk much about that in the interest of time. Instead, let me just try to close because time is short. So let me just mention that there is a wave particle duality that enables us to go classically, but beyond the Eikonal approximation. And this consists of the following. So we can consider perturbations of a black hole spacetime. Okay, and such perturbations, which if they are not symmetric, for instance, if they are non-spherical perturbations, they are very important because they are related to an open problem, which is the stability of the black hole. Okay, and this has been seen a lot of progress recently, in particular this paper for the Schwarzschild case. So we perturb our black hole by certain waves. So these waves can have helicity, they can be scalar waves or gravitational waves. They can have helicity 0, 1/2, 1, or 2. And Ray and Wheeler actually computed that in linearized at the linear level in the perturbation, but at the full nonlinear level in the black hole spacetime. Okay, and in order to describe the result, basically what they did was to take this quantity, which is a Newman-Penrose scalar, which I introduced in the beginning. You expand it in partial waves. You look at the radial component. So it's a separation of variable problem. So sorry, a separation of a partial differential equation. And the radial component of this Newman-Penrose scalar satisfies this equation. Okay, that's known as the Rayleigh-Wheeler equation. Now, this Rayleigh-Wheeler equation has a very similar form to the Schrodinger equation, which means basically that if you're going to compute the scattering in this situation, in a black hole background, you can look at the Schrodinger equation and reinterpret the Schrodinger equation as a quantum field theory amplitude, where instead of putting this potential, you're going to put a particle. Okay, so instead of putting an effective potential, I'm going to consider a massive particle scattering with my wave. And
5 minutes.
Thank you. And I can compute the corresponding Newman-Penrose amplitude, okay, associated to this amplitude, to this quantum field theory amplitude, using the same formulas that I showed in the beginning. Okay. Now the crucial part here is that this doesn't require any Eikonal limit, any consideration on the momentum tensor. So the only thing we're assuming is that the energy of the wave is small. So in a sense, the wave is soft. It's small enough such that the long wave, the wavelength is longer than the Schwarzschild radius. That means that basically we are seeing the black hole as a point-like object in this expansion. Okay, so under that assumption, we can compute this amplitude perturbatively and match it to the classical computation by Ray and Wheeler. Now, if we take this and further consider the Eikonal limit, then we go back to our Eikonal approximation, and you can check very easily that, or actually Ford and Wheeler did it, that this partial wave expansion becomes the Eikonal approximation. And something nice that you find is that the Eikonal approximation basically describes an effective action of a null geodesic. So that means that it doesn't matter whether you put a particle of helicity 0, 1, or 2 in this Eikonal approximation. At the very end, you're only going to get a null geodesic in this approach, in these limits. So this is an instance of a wave particle duality. The simplest example of this was considered long time ago by Tooth, who considered a massless particle scattering with a wave or with a particle, and in such case it doesn't correspond to the Schwarzschild background as in the Rayleigh-Wheeler case, but it corresponds to a Chug wave background. Okay, so just to finalize with some final thoughts, which I probably don't have much time to explain, but I'll just mention that if we look at these 3-point amplitudes, basically they vanish because they have this delta function. Okay, so you might say, how are we going to recover, for instance, a black hole spacetime? But we know that the black hole information is contained because, sorry, let me just. We know that with the amplitudes that we have considered, we can just compute the two-body dynamics, right? So we can compute effective actions for two bodies. So in some way, these amplitudes contain the full information of the black hole spacetime. But the 3-point amplitude itself vanishes. So that poses a puzzle. And the solution of the puzzle, well, it has many solutions, but one solution is that actually these 3-point amplitudes vanish because basically there's no radiation of a single body. You have to consider more than one body. but they have supporting complexify moment. Okay, so that means they can be used as building blocks to construct these 4-point amplitudes from which we can read of all the information of the backgrounds as we want. So this is a standard law of the on-shell program. We're constructing higher point amplitudes by using lower point amplitudes in complexified moment, okay, which are on-shell. Let me just mention, so this is the very last comment that I'm going to make, is that actually this whole program that I showed you can be repeated, except very few details, but most of it can be completely reproduced for the case of spinning black holes. So what changes is that instead of considering a scattering of a scalar massive particle, you're going to have to consider a scattering of a particle with a spin. So that spin maps to the classical spin of the Kerr black hole. And in order to reproduce the full information, you have to consider particles of infinite spin. Okay, so we completely nailed down a few years ago this 3-point object for the Kerr black hole. This 4-point object associated to gravitational perturbations of the Kerr background is still under study, but it provides a very important link between higher spin particles and black hole backgrounds. Okay, so this is all I wanted to say for today. Thank you so much.
Thanks. If there are questions, I think Nathan has a hand raised, and then Andy.
That was a very nice talk. I had the question, so for the post-Newtonian approximation, how does the theoretical error bar compare with the experimental error bar? Can you use your computations to check general relativity?
So it's negligible with respect to the SNR. So if you actually consider the signal-to-noise ratio, that makes it negligible. So in other words, we are currently, with our current measurements at LIGO, there's no need for more precision, as far as I know. But technology progresses, so we're expecting the Einstein telescope and LIS and so on. There is going to be a considerable error bar unless we include more corrections, more precision.
Okay, thanks.
Andy?
Yes, thank you for the beautiful talk, Alfredo. My understanding is that 15 or 20 years ago, the LIGO collaboration was very concerned that even if they detected gravitational waves, that the state of the art in understanding the relationship between the source and the waves was so poor that they wouldn't be able to know what they were seeing. And then there were these fantastic breakthroughs by Pretorius and Tarnopolsky and other people using variable computer meshes and advanced numerical analysis methods that brought in a whole new era of precision of source to wave matching, which relied heavily on technical advances in numerical analysis. Are you saying these methods supplant that, and we could now compare theory and experiment at LIGO just using analytic methods? Or because a black hole merger is an incredibly nonlinear thing, and it would be surprising if this kind of method could do that.
Yes, so there are different regimes, right? So numerical relativity, as developed by Pretorius in 2005 and other groups, is extremely powerful. Where at the very latest stages of the spiral, it's not as powerful as you would think in the early stages of the spiral. So actually, there is some kind of syncretism between numerical relativity and analytic methods in the plunge, which is the latest stage of the spiral, where you have to combine the two templates in order to get the precision that you want. But let me just mention that there is another a scenario where numerical relativity fails drastically, which is in the case of extreme mass ratio in spirals. So as you
so you're saying that no, these methods can't supplant the, there's still some things that we can't
They're
read.
complementary. They are complementary. So if you consider supermassive black hole, I'm not, my talk was not solely about gravitational waves. Of course, that's the most important application. But if you consider, for instance, a supermassive black hole with a very small body orbiting around it, then you cannot use numerical relativity because the size of the resolution is just not compatible with a small object orbiting a big one. So you have to use these analytic tools that we are currently developing. And in that regime, for instance, you would hope that such a computation can be done perturbatively to very high orders.
Thank you.
Gabriela?
Yes, thank you for the nice talk. I just have a small comment. While at the 3 p.m. level, I think the situation, the calculations are complete. At the 4 p.m. level, I think they are not yet. In fact, the calculation, which is based on conservative dynamics only, is still infrared divergent, and one has to add radiation reaction to it, and people haven't yet finished the calculation. And this is also important to have a unified description of the process from the deep non-relativistic limit all the way to the ultra-relativistic limit. So this, I think, has been done nicely at 3 p.m., but not yet at 4 p.m. 3 loops. Do you agree?
Yeah. Sorry. I was very schematical in that slide because, as you know, this is about a paper that appeared last week, and I agree with you that 4 p.m. is not complete. But my understanding is that they actually computed certain radiation effect at 4 p.m. Not only the conservative part.
We almost have it, Gabriele. We almost have the whole thing.
Almost.
Yeah.
That's what I wanted to say. I saw your paper. I saw your paper, of course. Very nice.
We include all the radiation logs. All the radiation logs are there. All the nice logs are all taken care of.
Okay.
And the poles are all gone. And answering to Andy's question, actually, if you look at the waveforms, look at the neutron stars. The neutron star merge outside the band. You don't even need numerical relativity. It's purely post-Newtonian. So the waveforms I use for neutron stars right now don't even rely on numerical relativity. Without us, you couldn't do anything with neutron stars. Another thing about ET, going to 1 Hertz. You get tens of thousands of cycles when numerical GI will take you the age of the universe to run one simulation. So you actually merge everything together. And people here will insert the word effective one body, which is how you kind of stitch it together. But you rely on analytics to actually cover the majority of the spiral that has almost all the cycles. You rely on maybe, I don't know, 10, 20 towards the end, which you actually rely on numerical GI. Of course, you need them, right? I mean, it's important to have them. But the majority of the cycles are analytic. And if we don't have, even up to, right now we're at 4 PN, 4 post-Newtonian and 4 post-Minkowskian. If we don't have 6 PN, we're gonna fail, even just, well, maybe not for detection. Well, it depends, maybe very eccentric orbits we might miss. But the parameters we're gonna get completely wrong with third generation detectors if we don't go higher orders from what we have right now. So actually, it's very important.
Jorge?
Picking up on what Rafael said, I understand that you have to use the effective one-body approach when you want to connect the scattering to the bounded orbits. But I also understand that the effective one-body approach, as of yet, not been proved in its full glory. So do you think that there's a way of using these new scattering methods that you're talking about in QFT to help us prove the effective one-body approach?
I'm not sure I actually mentioned the effective one-body approach. It's true that this radial action is effective action for relative motion. So you can say it's actually one body or scattering with another. So it's an effective action. It's true that the effective one-body approach was developed in post-Newtonian theory, and now it has evolved into post-Minkowskian theory. I'm not sure exactly what part of it is not proven, but what is true, and it can be derived from very general arguments, is that the Eikonal exponentiation happens in this low energy momentum transfer limit. So the Eikonal phase actually is not quite the radial action as you go to higher orders in G. So at first they coincide and they are exactly the same in linearized order. But as you go to higher orders in G, the Eikonal is slightly different than the radial action. So so far, I think that's the most reused method that we have.
But Alfredo, do you agree that this Eikonal or radial action approach, doesn't need to talk about the effective one-body problem?
Yes,
in fact, the effective one-body uses only the conservative part of the potential, which we know now is not enough.
They do add radiation reaction, Gabriele. They do it, but they do it by hand. Yeah.
Yeah, that's right. So, I mean, I think it's better to use the radial action or the Eikonal, because if you do it well, you pick everything.
Yes.
Yes.
Can I ask you a question
from Andy? We are
sorry.
running out of time, so maybe one more question from Andy.
Yes, I had another question. So you had a slide with the phrase black hole is an elementary particle. Now, of course, a black hole is the opposite of an elementary particle because it has exponentially many degrees of freedom, but it might, in some circumstances where you're discussing it, be behaving like an elementary particle. So my question is, does this formalism have within it some way which you might be able to think about, treating black holes in their full glory with their many microstates?
Okay, so that's why there is a classical prefix to the title. That I know. So actually, in effective field theory, how this scene started in the 90s is that people wanted to compute corrections, quantum corrections to Churchill or the Kerr metrics. And in effective field theory, there is a natural way of incorporating corrections in H bar, but it's still linearized. It's still linearized gravity. So it's up to debate whether you can measure any effect at this in this framework. So it's a perturbative framework. I'm not sure if you can actually compute something observable.
There's one more question from Juan, and then I'll move to the next
my question was related to the previous one. So the black hole can deform, right? And at some order, the deformation of the black hole will be important. As I understand, this can be taken into account in this effective field theory approach. I was just wondering whether this effect, and on the other hand, it seems that from this other scattering amplitude approach, you could, at least naively, I would say you could not take such an effect into account. Am I wrong? Or
so you mean tidal deformations?
Yeah.
Yeah. So then they can completely be incorporated. These are just non-minimal couplings in the scattering amplitude.
Okay.
Okay. I think it's time to
make one comment. It seems like this is all working much better than it has any right to. And so one wonders how far one can go with it.
Yeah.
Well, that's a standard law in scattering amplitudes. Things work much better than they are supposed to until we actually understand what's the underlying construction.
Nobody knows, I guess. Okay, let's thank Alfredo again for this nice talk, and thanks for the nice discussion. Mariana, maybe you can start sharing your screen.
Yes.
There's a question on the chat. I'll let the people who are in the field answer it, and you can have the discussion on the chat, and you can answer it on the chat. Our next speaker is Mariana Grana from SYK-like. She'll be telling us about the tadpole problem.
Okay, thank you. Thank you very much to the organizers for letting me speak here, and I'm going to talk about work that I've done in collaboration with our chair, Josif, Johan Blavak, and Severin Lust, and then a paper to appear with Josif and Callum Brody. So we know that realistic compactifications will have no massless scalar fields, so no moduli, but the landscape of Calabi-Yau flux compactifications is actually populated mostly from Calabi-Yau with lots of moduli. There's this huge number of vacua coming from this Calabi-Yau, which has this huge number of moduli, and vacua coming from other Calabi-Yau with less moduli are highly suppressed with respect to this. Now, these are also the corners that can give rise to interesting phenomenology, like, for example, the possibility of uplifting anti-de Sitter vacua with a small cosmological constant, as we will see. Now, moduli need to be stabilized, and this fortunately can be done with fluxes, but fluxes induce charges. And the question we ask ourselves is how large is the charge induced by the fluxes needed to stabilize a given number of moduli? Or in other words, can fluxes that stabilize a large number of moduli generate an order 1 charge? The common law says yes, while we argue that this is not possible. So furthermore, we believe that there is a relation between the induced charge, so the charge induced by the fluxes, and the number of moduli stabilized. So our tadpole conjecture that we put out in this paper last year says that for a large number of moduli n, the charge induced in the fluxes such that all moduli are stabilized at a generic point in moduli space grows linearly with the number of moduli, and the coefficient is larger than 1/3. So, okay, before seeing the details and examples, let me give you some motivation for this. And the motivation comes from black hole microstate bubbling geometry. So these are geometries that have the same mass and charge as a D1D5P black hole, but no horizon. And they are dual to states of the D1D5 CFT. Now this CFT counts the black hole entropy. The dual solution is made out of a multi-center Gibbons-Hawking solution, and there are two cycles that have magnetic fluxes, and there's a black hole charge disorbing the fluxes. So from here, we got two supporting arguments for the tadpole conjecture. So one is a sort of experimental observation that says that the charge contribution from the cycles adds up. Otherwise, if they don't add up, so if you have pluses and minuses, you get closed time-like curves. And the other is that the number of ways to put fluxes, supersymmetric fluxes on cycles with a given charge, this accounts for the black hole entropy. And if it was possible to get this charge with a given charge, so with positive and negative individual contributions, there would be an infinite number of ways of getting this charge. And so the entropy coming from these flux configurations would be larger than the black hole entropy, which cannot be. So this is the motivation, but actually our conjecture applies to flux compactification, and in particular type 2D flux compactifications on Calabi-Yau or warp flux compactification. And in particular, the moduli that we're interested are the complex structure moduli. These are of order 100 complex structure moduli in typical Calabi-Yau. And this can be stabilized by three-form fluxes. So three-form fluxes means a VEV for this field strength, Ramon or an SNS, such that the integral on a basis of 3 cycles is some integer number. It's not hard to see that this creates a potential for the complex structure moduli and the dilaton that comes just from the action. So the action, you write it like this, and this Hodge star for an odd form depends on the complex structure moduli. So there's a minimum of this potential, and at the minimum, these fluxes are dual to one another, and this fixes the complex structure moduli in terms of these integer numbers m and k. Now fluxes induce D3 charge, and the D3 charge induced is given by this topological charge. So this is mk with some, so here indices have been raised with some intersection matrix, which has split signature. So we don't know what the sign of each individual contribution is. So we believe that they mostly have to contribute positively. But what we do know is that at the minimum, these fluxes are dual to one another. So the whole thing, the whole sum is positive. So this positive charge in a compact space has to be canceled. So the charge should add up to 0, and that's the tadpole cancellation condition. So the fluxes induce positive charge. One can also have supersymmetrically these 3 branes. And everything has to be canceled by the negative charge, which the simplest one is to have all three planes. But actually, there's a maximum number of there's a maximum charge that one can obtain, or a maximum number of. So this comes from set two symmetries with fixed three planes, and there's a maximum. There's an order of 100 of them that one can have in certain Calabi-Yau. So this doesn't give a lot of charge. But fortunately, there are other sources of negative charge, which are these 7 branes and 07 and 07 planes wrapped on curved 4 cycles. Now, these 7 branes have moduli associated, and these moduli are stabilized by work volume flux. So we have moduli coming from the complex structure and moduli coming from the D7 brane, and then fluxes that stabilize each one of them. So this is better to discuss it in the unified description of F-theory. So in F-theory, in a Calabi-Yau form, both the complex structure moduli and the D7 moduli are combined into the complex structure moduli of a Calabi-Yau fourfold. And the 3-form fluxes, the bulk 3-form fluxes and the 2-form fluxes on the D brane are combined in the 4-form flux G4. The tadpole cancellation condition says that the charge induced by the fluxes, which is given by this, and again, this is going to be a sum of integer numbers with some intersection matrix. And again, the individual contributions can have a priori any sign, but we know that at the minimum this is positive, because at the minimum the 4-form flux has to satisfy the self-duality condition. So this has to be cancelled and has to be less or equal than the negative 3 charge coming from the 7 branes and 07 planes, which is completely encoded in the Euler characteristic of the Calabi-Yau fourfold. So this Euler characteristic can be written in terms of the Hodge numbers, and in particular, if we look at H3,1, so these are the moduli which are stabilized by the fluxes, and in the limit of large number of complex structure moduli, this goes like 1/4 of n, so where n are the moduli stabilized by the fluxes. While our tadpole conjecture says that the charge induced by the fluxes, which is equal to this, such that all moduli are stabilized, so grows linearly with the number of moduli, but the coefficient is larger than 1/3. So, and obviously 1/3 is larger than 1/4. So if the tadpole conjecture is true, then one cannot stabilize a large number of moduli. Now, let me give you supporting arguments. So we look back at the literature and some old examples, these and some newer ones, which have a large number of moduli in general. But for example, these type 2B examples and F-theory examples are stabilization at highly symmetric points in moduli space, which are much simpler to analyze because there's only a few moduli that one has to analyze. But already for them, there's a large charge induced in the fluxes, and if we compute the ratio of the charge induced by the fluxes divided by the number of moduli, we get always something larger than 1/3. And in particular, we get a lot of times is 0.44, 0.45, which is quite surprising. So today I'm going to talk about this work that we did in theory on K3 times K3, and this example of stabilization of the 7 moduli of F-theory on any weak Fano base. So M-theory on K3 times K3 was actually the very first example of moduli stabilization, because this is a nice setup where to study these things. And so in particular, let's look at the middle cohomology of K3. The middle cohomology of K3 is given by this lattice of signature 319, which is twice a E8 lattice, plus 3 times the lattice of momentum unwinding on the circle. And fixing moduli on K3 means choosing a 3-plane sigma of self-dual 2 forms. So this 3-plane inside this 22-dimensional lattice, this fixes a moduli, and the holomorphic form and the Kähler form are completely given in terms of so the metric is completely given in terms of this these 3 plane, the forms on this 3-plane. Now, the difference between our work and the work of Aspin-Wall-Kalosh, for example, where they study moduli stabilization, is that we require a smooth compactification, so no orbifold singularity. So why is that? Because if there's an orbifold singularity, then there's a non-abelian gauge group, and when there's a non-abelian gauge group of dimension n, there will, in general, there are n square massless moduli that one needs to stabilize. And we want to avoid, so we want to find a situation where all moduli are stabilized, so we require a smooth compactification. Now, there's an orbifold singularity if there's a root in the lattice such that it's orthogonal to sigma. So an element in the lattice with norm -2, such that is orthogonal to this three-plane of self-dual two forms. Now, the moduli can be stabilized by four-form flux, as we have this four-form flux with two legs on a K3 and two legs on the other K3, and this is given a basis of two forms on each K3. Then this flux is given by a 22 times 22 integer matrix. It's not hard to see that this gives a potential for all K3 moduli except the volumes of the K3. And the nice thing about this problem, and that's why we worked on this problem, is that moduli stabilization can be turned into an algebraic problem. So it was shown by these people here that moduli stabilization can be turned into an algebraic problem. So this is done by defining a map that goes from H2 of K3 to itself, which is quadratic in the moduli, quadratic in the fluxes, and has the intersection number. So this map that goes from H2 to H2 is such that all moduli are stabilized at regular points if this map is diagonalizable with non-negative eigenvalues. So there are 22 eigenvalues, 3 correspond to eigenvectors with positive norms, and those are the ones that define sigma, and then 19 eigenvectors with negative norm. Now, if all the A eigenvalues are different from all the B eigenvalues, then moduli are fully stabilized. Otherwise, if there's a B that is equal to the A, then one can slightly rotate the three-plane sigma, which means that there are unstabilized moduli. And then we also require smoothness, so we require that there's no root in the lattice orthogonal to sigma. So the goal is to find the matrices satisfying all three requirements and minimizing the flux charge. So the flux charge, which is equal to this, is equal to just a trace of the matrix. Now, this is a very nice problem to study using evolutionary algorithm, and this is what we did. So we studied this by this evolutionary algorithm, which is an optimization algorithm inspired by a biological evolution. So there's an initial population, there's a mutation, and there's selection. So we start with some random initial population of, say, 1,000 matrices, which they are integer, but then when they mutate, they become real. But then we round them to the integers, and well, here we wrote them as vectors. But yeah, they are matrices. And then for each of these matrices, you mutate some of the entries using other elements of the population. And from the original and the mutated, you select the one that minimizes a fitness function. So there's a fitness function constructed as a sum of penalties if each of, so we want the matrix N to satisfy all these three requirements. So if one of these is not satisfied, then there's a penalty. And then there's a penalty for a large flux charge. And these penalties are weights, and the weights are determined empirically such that the system converges, the evolution converges to matrices satisfying everything and with a small flux charge. Now, note that this demanding that there is no root orthogonal to sigma is an NP-hard problem that we have to solve at every step in the process. So we run all this, but then at the end of the day, we also perform some local search, which is brute force around the minima to see if we can still minimize the flux charge. And what Severin and Johan, that were our brave evolutionary algorithm people, what they found is order of 100,000 matrices that have Q flux equals 25, and no matrix with a charge induced by the fluxes less or equal than 24. So this means that, so if we look at the tadpole cancellation condition for K3 times K3, chi over 24 is equal to 24. So one cannot, on K3 times K3, one cannot stabilize moduli at a generic point. So this is one thing. And then also, if we look at the tadpole conjecture constant, which is the quotient between the charge induced in the fluxes divided by the number of moduli, we get this ratio 0.44. Now, since these are large matrices, or as vectors, they have 484 entries, we also confirm this behavior by looking at smaller dimensional lattices. And we confirmed that there's always a minimum charge induced by the fluxes, such that all moduli stabilize at a generic point, and that this flux is related to the dimension of the lattice, which is related to the number of moduli. Now, one example that one can study analytically is that of the 7 moduli stabilization, but we studied it from the point of view of F theory. So we consider F theory on a Calabi-Yau fourfold fiber over a base in the same limit. The number of the 7 moduli can be completely encoded with the first gen class of the base. And these are stabilized by two-form flux. So what does it mean? So the D7 a priori is free to move. There's a free modulus, but there are some points in the manifold where there's a rigid curve, a rigid holomorphic curve that is only there, is rigid. So when you tune the D7 and you turn on one volume flux along this curve, then the D7 cannot move anymore. So that's the image of moduli stabilization, D7 moduli stabilization by F2 form flux. And if we look at the tadpole cancellation condition, the charge induced by the fluxes, which is equal to this, has to be less or equal than the negative charge from the 7 branes and on 7 planes, which is this chi over 24, which in the same limit can be written completely in terms of the first gen class of the base. And if we look at this, the ratio of this to the number of moduli in the limit of large number of moduli, what we get is, again, we recover the same as, so we recover a quarter, the same as between chi over 24 and H3,1, the same. There's a quarter ratio. While our tadpole conjecture says that the fluxes induced, the charge induced by the fluxes such that all the 7 moduli are stabilized is larger than one third of the number of moduli. So again, 1/3 is larger than 1/4. So if this is true, one cannot stabilize a large number of the 7 moduli. And we verify this tadpole conjecture for any weak Fano base. So this is a huge number of examples. So we don't know how many, but we know there's a subclass of weak Fano which are toric, which there are more than 500,000 of them. So this is, we don't even require it to be toric. And so the way to study, so moduli is stabilized by a flux, and the way to study it is through the complex curve dual to the flux. And Callum Brody, who is very good with these calculations, could compute the number of stabilized moduli completely in terms of some quantity that one can think of some degree, which is intersection of the curve with the anti-canonical bundle. And we have to require that this is equal to the number of the 7 moduli, while the flux can be written also completely, can be written in terms of the same quantity and this extra contribution of 1 minus g, where g is the genus of the curve. So for large N7 at fixed genus, we recover that the alpha, so the charge induced by the fluxes divided by the number of moduli, is again this 0.44. And so this is, on one hand, this is larger than the 1/4 allowed by tadpole cancellation condition, and this is larger than 1/3 of the tadpole conjecture. So moduli stabilization cannot be stabilized within the tadpole, and the tadpole conjecture is satisfied. And this reduces to a result that there was an old result of Colinucci, Denef, and Esole that had computed this for the base equals CP3 and a genus 0 curve, where everything can be computed very explicitly, and this in terms of the degree of the curve, and the degree of the curve, which is the intersection of the curve with a hyperplane, so it's 4 times this. So our d tilde is 4 times this degree for the case of CP3. And again, here one cannot stabilize moduli within the tadpole. So the tadpole is 172, and the charge induced in the fluxes is this, and the same, we recover the same tadpole, we recover the same constant if we divide the charge induced by the fluxes divided by the number of moduli. So one of the implications of this is for the sitter with the anti-brain uplift. So we computed in this paper with Josif Severin and Emilian Dudas, we computed what happens so the potential, so how is the moduli stabilization plus the anti-D3 works when one really considers the warped effective theory. So in this business of flux compactification, these are warped compactifications. And here, so this is the typical, so this is KKLT, so here there's a throat with a deformed conifold geometry, and the modulus, the conifold modulus is stabilized in terms of the units of Ramon fluxes on DS3 and NSNS fluxes on the dual cycle. And if we look at so this is done looking at the potential in the unwarped effective theory, but if one looks at the potential in the warped effective theory, here is very different. So the minimum is at the same point, but here is very different. So what happens now when one has one anti-D3 ring is that the anti-D3 ring wants to collapse DS3. So in general, the de Sitter minimum disappears unless there's a lot of flux on DS3. So unless there's this flux, so square root of G string M larger than this, then DS3, then the anti-D3 makes DS3 to collapse and the solution to be singular.
5 minutes.
A similar bound obtained from demanding the existence of a Klebanov-Strassler black hole. So we're quite confident of this bound. Now the problem of this bound is that you need a lot of flux. So in particular, if we look at the hierarchy, which is 1/3, which is this to the 1/3, then what we get here, so one can multiply and divide by M, and here you get the charge induced by the fluxes in the throat, and this has to be larger than 6.7. So we get that this hierarchy is larger than this. So if we demand that this hierarchy is of order 10 to the -2, which is not too much, then then what you see is that you need a lot of fluxes, a lot of charges in the throat. So the charge induced by the fluxes on the throat has to be at least 100. So then in order to cancel this 100, you require a large tadpole charge, but we know that a large tadpole charge means a large number of moduli, and a large number of moduli need to be stabilized with extra fluxes, and then this cannot be done if our conjecture is true. So if it's true, there's no anti-brane uplift and no de Sitter vacuum a la KKLT. Okay, so to conclude, the tadpole conjecture says that for a large number of moduli, the charge inducing the fluxes, such that all moduli are stabilized, grows linearly with the number of moduli, and the coefficient is larger than 1/3. So this conjecture is supported by several examples, and we worked out evolutionary algorithm on K3 times K3, and there was an analytic computation for the 7 moduli in a huge number of examples. So if true, one cannot stabilize a large number of moduli in F theory, which means that these 10 to the 272,000 vacua are not phenomenologically relevant because they have lots of moduli unstabilized. Also, if true, there is no anti-brane uplift in long warp throats, no de Sitter vacua like KKLT. Now, we hope to find an analytic proof for this. An analytic proof in general, I guess, is going to be quite hard, but maybe one can hope for an analytic proof in K3 times K3, or in particular regions in moduli space, such like large complex structure limits, for example. So stay tuned. Thank you.
Thanks. Questions? Sandeep.
Hi, Mariana. Thanks for a nice talk. I'm sorry, my memory is very bad, but in the old days, and you mentioned this, at least when we looked at the stabilization, I think here you're just talking about complex structure moduli stabilization, right? Say from the F theory perspective. Mm-hmm. And, when if I remember right, I could be wrong, when we looked at simple examples, for example, with Tripathi and so on, and then as you mentioned in that paper of Geryavets, but I'm remembering especially the paper with Tripathi, I thought at least at symmetric points, you're right, we looked at only rather symmetric points, but we could indeed stabilize all the
complex structure moduli with the tadpole cancellation taken into account. Am I wrong in my memory? And if so, maybe if you're not at a generic point but at a symmetric point, can you get around it?
Yeah, no, you're not wrong in your memory. The problem there is, so you need a large tadpole, which means you need to add the 7 branes, and that's the part where stabilization fails. Then, so
you mean then the 7 brane moduli were not stabilized?
Not stabilized, right? Yes.
I see.
Point, yeah.
But okay, but there was all right. But then there was the follow-up work also, you know, where you looked at it in F theory, as you say. I can't remember where, but there all the complex structure moduli were not stabilized, is it?
For large moduli, no, there is no example that I know for large moduli where all moduli can be stabilized within the tadpole.
I see. Okay. Okay. Thank you.
There's a hand by Ed Witten, and then
perhaps you explained this, but can you say anything simple about the moduli that aren't stabilized when you've turned on the fluxes?
The moduli that aren't stabilized?
Yes. Do they mean something, or?
Yeah, no, I mean, yeah, there are moduli that are not stabilized, but yeah, I don't have a clear way of identifying them. Yeah, not really. So as I was saying to Sandeep, in these examples of type 2b, in general, the moduli, so when moduli, complex structure moduli in type 2b are stabilized at highly symmetric point, then the moduli which are not stabilized are the D7 brane moduli. But this is not, I mean, these are these particular examples. I'm not sure one can say something in general.
Thank you.
Yeah, hi. Sorry if my question is naive. In your construction, you have been fixing two forms fluxes as well as through their integrals. What in the construction guarantees that they have come from a gauge field as a field strength, or it's not a matter of concern?
Say that again.
What in the construction guarantees that the field strength, the two forms that you are writing is a field strength of a one form, or it's not a matter of concern at all?
I don't think it's
sorry, no, I don't understand the.
I think it's about the flux curve. So when you have a flux curve on the D7 brane, there's a two-form field strength. The question is there some abstraction to? I mean,
right.
Is there some abstraction to have this? No, I think yeah. So in that construction, you have these rigid curves, and yeah, there is no abstraction to have these rigid curves. They are. Yeah, I'm not sure if I answered.
I think that I think this is the I think this is the answer. So
yeah, thank you.
Jorge.
Hi, it was a great talk. Thanks. My question is whether you can have a simple argument for a factor of a third, like a black hole type argument for the factor of a third.
No, not really. So if you want the third, by inverse engineering, we could have put a quarter, because that's what you get in the, but we saw actually that all the examples, and a quarter gives a little room for stabilization, and we saw that all examples, actually alpha is larger than a third, but no, we don't really have a motivation for a third per se, as it is.
I think the one in the gazillion cases of weak Fano basis, the number tends to be 0.4385. So 7/16. That seems to be the number for weak Fano toric and for toric basis. Ashok. Ashok.
Yeah. So my question is, if we take this D7 moduli which are not stabilized, are they compact?
Yeah, so some of them will be compact, some of them. So one tends to think that they are compact, and so they are no problem. But from the point of view of F theory, they are unified with complex structure moduli. So I don't think all of them are compact. And if you take into account also the metric in moduli space, then yeah, there are non-compact moduli which are non-stabilized.
I see. And so it's always the case that there are always some non-compact moduli which are not stabilized?
Yeah, we think so. I mean, it's a conjecture, but yeah, but that's what happens in the case of the D7 brane. Yeah.
Thank you.
No, that really, I'm sorry, that really confuses me. Why aren't there 7 brane moduli which are not fixed, just motion of the 7 brane in the Calabi-Yau? I'm missing something? I mean,
no, because I mean, yeah, you can fix a certain number of them, but you cannot fix as much as you need and as much as you are allowed by the tadpole cancellation condition.
No, I mean, I understand about the stabilization. I'm just saying towards Ashok's question, I thought they are all compact, no, because they correspond to motion in the compact Calabi-Yau. Is this not correct?
It's unclear in F-theory language, right?
Yeah, in F-theory language is the same as any other complex structure moduli. So I don't think there's a natural way to tell between those and complex structure moduli, and I don't think one can say that they're all compact. So one has to take into account the metric in moduli space, and I don't think they're all compact.
I see. Okay.
Kumnon is saying on the chat that they're not compact, like the D7 branes in F-theory and K3. Igor Klebanov has a question.
Yeah, so if I understood correctly, this condition that G string M squared is bigger than 6.7 squared, it basically guarantees that the throat is well described by supergravity. Namely, the S3 at the bottom is pretty large in string units.
No, it's a condition such that the S3 doesn't, such that the anti-D3 doesn't shrink the throat to, doesn't shrink
Right. But it also has a side effect of this, the throat looks pretty geometric, right? The supergravity describes it well.
Yes.
I mean, that's, I'm just trying to be on the positive side of the argument. Because if say you found that G string M squared is very small, then you really cannot trust
you cannot, yes.
solution, and then you don't know what's going exactly.
Yeah,
it's a very interesting condition that this S3 stability also implies that the throat is geometric somehow.
We were very surprised by the result, Igor, because actually when we started the calculation, I was actually firmly convinced that the moment you put anything in Klebanov-Strassler, it would immediately get flushed into Klebanov cycling because there's a flat direction. The size of the S3 is a flat direction, and therefore you put some energy or something, the energy tends to go to zero size. So we didn't expect, we thought you put one anti-brane and it's over. It will be completely killed. And then only when you glue to the Calabi-Yau or somehow because of the compact effects, it will be actually stabilized. But then Severin actually found that no, actually things are stabilized even for infinite Klebanov-Strassler. You also have stabilization. And then based on that, we conjectured the existence of a Klebanov-Strassler black hole. And then when we put the paper on the archive, basically the 1 hour after the paper appeared, Alex Buscher wrote to us saying, look, I found a Klebanov-Strassler black hole. And we conjectured that the black hole should be there, even if, again, nobody expected it for like, many years. People were doubting that such a black hole exists because it's dual to a phase with deconfinement and Carrier symmetry breaking. So nobody was expecting this black hole, but we conjectured it, and Alex Buscher actually was working on it on the same time without knowing. And then and then came out and amazingly it turned out that the condition for the existence of Klebanov-Strassler black hole, which is obtained when G string times n is actually with strong back reaction, is almost the same as the one we found. With a different numerical factor because we work in different regimes of parameters. But the same dependence, the same G string, the same n. It kind of
Very interesting story. Yeah. Thank you.
So I'm really sorry. Can I just ask for a clarification?
Of course.
Then I'll drop it and we'll do offline. But Mariana, I'm not saying that all the complex structure moduli in F theory are compact. No, that wasn't what I was saying. But what I was saying was, for example, let's go to the 2B limit. Then you can, at symmetric points, stabilize all the non-compact directions. And what remain are the 7 brane motions in the compact geometry. So there you can see that if you haven't stabilized the 7 brane moduli, they're all compact moduli. This is what I was trying to say. Not that all complex structure moduli viewed from F theory are compact. No, that's not true. But you can show that all the non-compact ones can be stabilized while meeting tadpole conditions. And I thought that was the question of Ashok. Sorry, can you comment on that? That's, I think, what we showed in even the old paper with Tripathi, no?
Yeah, but I'm not sure the D7 moduli are really compact in that case.
But you can check that they correspond to geometric motion in the compact space.
Yeah, that's but you have to take into account the metric in moduli space. So it's not, to me it's not so obvious that they are compact.
No.
Okay, maybe I can add just a comment. This thing about compact versus non-compact. I mean, again, when you have complex structure moduli, you can also discuss them as a non-compact direction and compact ones. But still, normally we stabilize all of them. I mean, the whole spiel about moduli stabilization is that we should stabilize all of them, whether compact or not. So I think the same game should apply to the D7 ones.
No, I agree. You should stabilize all, but it's important to know whether these are compact or not because they can run away. That's all.
Yep. Okay, if there are no further questions, let's thank Mariana again.
Thank you.
And I guess we reconvene in 20 minutes or so. I don't know.
Yeah, 20 minutes.
Okay, sounds good. If people want to stay to discuss, feel free. I think the Zoom is going to be on, so if people have further questions, and I don't know if the live is still going or not, but if people don't want to be, if there are further questions, we can keep on discussing informally.
Yeah, sorry, Yusuf. I just wanted to say, I think in 4D n equals 1, you have no correction. So every compact direction, and maybe that is why Sandeep was asking, every compact direction will be stabilized through some type of higher order corrections, I think.
Mm-hmm.
Only at n equals 2 or n equals 4, you can have enough supersymmetry to have flat directions. That's why distinction is important, yeah.
But then the question is when people stabilize complex structure moduli, in general, because I can take the complex structure moduli space and I can break it into some non-compact direction times some compact directions. In principle, then, using this logic, I don't need to stabilize all the H to 1 complex structure moduli. I can just just stabilize the non-compact ones.
Yes.
And then the compact ones, I just cross my hands and invoke corrections and pray to higher.
Yes, well, yes, that you can calculate, but I think that is correct. I remember when I was very young, I was giving a talk and Bobby Asharia was giving me a very hard time because I was stabilizing some axions with compact moduli, which now I appreciate why he did that. So I think the compact directions, if you have n equals 1, only supersymmetry will be stabilized through some higher corrections that you might or might not include in your setup.
But also there's a danger that the D7 moduli, which again appear to be compact, if you look in F theory, again, you think, oh, the D7 moduli space is compact and so on and so forth. But if you look at the D7 moduli, I think there are some directions in which actually they spill over into the non-compact directions. I don't think the moduli space is cleanly broken into compact 2,1 and non-compact 2,1 times compact.
Yes, I agree. I think this is why Sandeep was asking about the type 2b limit, where you could somehow break it up into separate. But in F theory, I agree what you're saying.
Even in the type 2b, there are some limits when actually there's some cycles shrink and you go to F theory and directions open up. So this kind of
okay, there could be, but what I'm saying is there are regions of moduli space, say in 2b. The other limit we looked at was the heterotic, because you can also do in some cases a duality, and there it's clear that some directions are compact. On the heterotic side, for example, they become Wilson lines, and so then at least if you work in those limits and you stabilize the non-compact ones, I agree with you. It's good to also stabilize the compact ones just to, if you're going to do other things and break supersymmetry, but at least you have dealt with the most worrisome directions, in a sense. And all I was saying was, I think that can be done, but okay, we can have more of a discussion. I'm also not very, it's been a while for me, so.
The other thing I wanted to mention, I don't know, Sandeep, whether you look at the chat, but for example, Daniel Harlow posted a paper where explicitly all moduli are stabilized and tadpole conditions are satisfied. That is kind of what you were asking about. Yusuf wrote there that that was a limit of few moduli and that they're
they're very complex structure moduli. We looked at the paper, of course, this is one of the first papers we looked at, but somehow the main issue seems to be, when you have a few moduli, you can play around, and there also there's the 1,1 moduli, and you can play around with. You can play around. With a few moduli, there are various factors of 3 and 4 and 5, with which you can play, and you can hope that maybe things can work. The main issue, I wanted to find was whether you can get a tadpole of order 100 from the Klebanov-Strassler throat. This seems to be necessary. Without having a 100 tadpole, you cannot uplift. And the problem is, so essentially, there's a budget of D3 tadpole. You need 100 units of D3 tadpole in the throat, and then it needs to be cancelled somehow. And then you need a lot of D7s, and then this automatically pushes you in the large number of moduli direction. All these compactifications which have a few moduli, they cannot accommodate the Klebanov-Strassler throat, which has some reasonable warping and some anti-D3 brains and some chance of uplifting. Those are just.
If there's some finite number where it works, then do you think that there's some?
Oh, that would be great. That would be great. No. Our purpose. Again, if there's a bunch of guys which work, I'd be popping champagne, of course. No, absolutely. If there's that's what we want. We really want to find some sliver where things work. But it somehow looks like this mega big gazillion 10 to the 500, 10 to the 200,000 things and so on. It looks like none of them it works. All of them have.
You would certainly guess that typically it doesn't work, right? But what you said, for a finite number, you kind of play around and try to balance things, and somehow you get lucky, right? But even so maybe if there's more, you just have to work harder. You have to typically it's not going to work, but if you have a good machine learning algorithm or something, maybe you find one. I don't know.
Well, this is what we did on K3 times K3, and you cannot finally stabilize.
But it was unclear.
It's hard. There's a difference between it's hard to find and can't find. That was what I was having.
No, yeah, there you cannot.
Okay. K3 times K3 actually has a few moduli, so they are actually it wasn't clear at all. We started and we had this hyper powerful machine learning guys, both Johan and Severin, they're machines, and in terms of doing this, so they really run all these things, and the limit was 24, and the bloody algorithm kept on giving us 26, 27, and then 25, gazillions of 25, and nothing 24, and you get it was really shocking that it didn't work. We didn't have much hope actually for K3 times K3. I didn't, maybe Mariana had. But because
So I was late to the talk and to the discussion, but I heard that there was some discussions about compact versus non-compact moduli space. Yeah, so I think if you don't stabilize the Kähler moduli, this question is not really settled, right? If you have a D3 brane, if you stabilize the Kähler moduli, then the moduli space of a D3 brane is compact. But that's actually a vibration of the axial dilaton coupled to the D3 brane, and so it's actually the Kähler moduli and the D3 brane moduli together is a non-compact space. So in the same spirit.
Yeah, that's true. That's true. And here we are not even.
So if you don't stabilize the Kähler moduli, I don't think you can make a distinction between compact versus non-compact. So Sandeep's intuition is right. So if you already stabilize the Kähler moduli, then the D7 brane is moving in a compact moduli space, but you have a whole bunch of Kähler moduli flowing around here. So
you obviously stabilize all the Kähler moduli using KKLT. Okay,
right,
never mind.
But at the level of the discussion,
I'm getting off the chat. No. You're right. Right. Of course, we have to step. No. You're
right. So I think we could make that distinction if we have a second mechanism to stabilize the Kähler moduli. Then I think you can.
Yeah. I agree. I was just saying for a fixed Kähler modulus, which we hope to stabilize, then we do.
Right.
Yes. True.
Right.
Okay, I'm going to step out, guys, but thanks. Oh, yeah. Ashok is here.
Yeah. So the question I was asking is, suppose you fix the Kähler modulus, then I think it's a well-defined question as to whether the remaining moduli space after you have chosen it, whether it's compact or non-compact. Right. So even if say take the original K3 times K3 moduli space, it is not compact. But let's look at the submanifold, right? After you have fixed whatever could be fixed.
Yeah.
Is that submanifold compact or non-compact?
Right. Right.
That's a well-defined question. I think you can ask, right?
Yeah. Yeah, I think so. And what I would say is, but I can go back and look at my papers, but all of you can say, take the 2B limit, okay, Ashok, where all the PQ orientifold PQ branes have come together, as you know very well. In that limit, I think one can show that all the non-compact complex structure moduli are fixed using fluxes consistent with tadpoles, and what remains are moduli which can be interpreted as motion of 7 branes on the manifold. If it's K3 cross T2 mod Z2, then that manifold from the 2B point of view. I think this is correct. I think we showed this. I can check, others can say. And therefore, I would say the remaining unfixed moduli are all compact for a given Kähler, for given volumes.
Yeah, but what I'm saying is that this question is more general. You can ask it even in more general context, in F theory, right? Where you don't have this simple picture that whether the manifold on which you have fixed, whatever moduli you have fixed, right? Yeah. Whether that manifold is compact or not, I think that's a well-defined question.
Yeah,
right? It doesn't.
I agree.
The manifold in two compact and non-compact directions.
No, I agree with you. I only evoke 2B because there the motion of, you can check that the remaining moduli correspond to motion of 7 branes and it's geometrically clear. But you're right. You're right in general.
Oh, sorry to interrupt. Maybe we can now check the share screen and then you can continue later, but let's just see if everything's working okay. Eva, do you want to?
I can, oh, Gonzalo, good.
Looks good.
So can you just check, just go to the next screen just to make sure it's working okay?
Yeah, 1 second.
The bottom is cut.
Yeah, now it's okay.
Yeah, it looks good now.
Okay, thank you.
Okay. I may have to turn off my camera while I'm discussing to get a better internet connection.
Oh. No problem.
Is Jeff around already?
Not yet. So maybe Eva can check if hers is okay.
Yeah, I can check if you just unshare for a moment, Gonzalo. I'll just check quickly. Where did it go? Okay, you're seeing that?
Yeah, we can see now. Can you just put it on the full screen mode?
Yeah.
Just flick a few pages just to make sure.
Okay.
Yep, looks good.
Okay, awesome. Thanks.
Okay, thanks. So what about Daniel? Do you want to try? Are you going to show? So,
sure.
Just how many time zones are we covering on this session? Here you are.
So you're in charge of the first two.
Yeah, that's right.
Can you see this?
Yeah.
Yeah, we can. Can you just flick it just to make sure that, yeah. All good.
Very good.
All right.
Okay, very good. So I sent an email to Jeff. Let's hope he...
Just make sure, Nathan, just make sure it's after 20 minutes, I should warn the speaker. Yeah, okay. So, Gonzalo, is that okay? After 20 minutes, I give you a warning?
Yeah, please. Thanks.
Okay.
Jeff will probably show up. He's just...
I'm sure he will.
He's on the West Coast, so my suspicion is that he's going to roll out of bed and give his talk 2 minutes later.
That's right.
Hopefully there will be no camera.
Yeah.
So you guys have probably already discussed this, but how is the COVID wave in Brazil? Is it as bad as the headlines say? I hope everyone's okay.
So it depends. I mean, right now it's stable, but stable at a high level. It's like 2,000 deaths a day. So, so it depends on which side of the coin you look.
Which, yeah, glass half.
If it gets worse, it'll get much worse, but hopefully it won't.
Well, the numbers in England are also not great at the moment, but at least the death rate is relatively low.
Mm-hmm. It's mostly unvaccinated people, right?
In England?
Yeah.
Well,
Delta is taking over the unvaccinated.
Yeah, there's like, I think there's around a fourth or so of the ICU that are occupied with people that were vaccinated once.
Oh, okay.
That's in the same numbers. I think in Portugal, it's like a third of the people that are in ICU have been vaccinated once.
With the AstraZeneca?
No, the ones that's more worrying. The ones in Portugal is with the Pfizer. Because I think only above 65 you get the AstraZeneca in Portugal.
But almost nobody who's been vaccinated twice.
No. There are people who have been vaccinated twice for in the hospital. I think in England there's a large number, but there's a correlation between being vaccinated twice and being old. So the point is there's a correlation between being vaccinated twice and being sick from the Delta. But there's also a correlation between being vaccinated twice and being old. And usually people who are vaccinated twice and being old, they have less protection. So, they can still get sick apparently.
Well, yeah, your immune system is not so good when you're old.
Yeah, I think we're expecting huge inhomogeneities in the US because of the no-vax regions. There will be a delta. Sorry?
There's around 30% of the population that is not vaccinated, right?
And apparently it's, a local effect by and large. So
the problem with this is that these pockets can develop variants.
Yeah, exactly.
And then those can escape and can affect everybody.
Right. I mean, also like I have a 3-year-old who can't be vaccinated, right? So the people who choose not to get vaccinated, I don't have very much sympathy if they get sick, but the people who don't have
then I have an 8-year-old, a 5-year-old,
exactly.
and a 3-year-old, and we've been homeschooling so for a year and a half. So I understand.
In Europe, there are entire countries which are not vaccinated. Bulgaria, for example, I think it's at 20% or something. So, and
where, sorry?
Bulgaria, for example. I mean, in Romania, the numbers are still, they're like, around 40% or so. And, right now, nobody wants to get vaccinated. I mean, it's really horrible. I mean, the amount of fake news coming and, the misinformation is really like beyond belief. And I think Bulgaria is worse. So, that's always,
But the numbers are low because of idiots, or because the supply is not there?
No. The supply is the same as in all of Europe. So all the European Union has constant supply. So the percentage of people who should be vaccinated is the same as in France, as in Germany, or in other countries. Except that, you basically have, there's a huge amount of rumor of misinformation channels, which are basically seeded by, ex-KGB agents and so on. I mean, those countries, until, 30 years ago had like, 10% KGB informers. So, those guys are not idle, and, there's some correlation between that. So,
I don't know whose interest it is to have people non-vaccinated.
Oh, many people, of course, many people, the more Europe has non-vaccine people, the worse our economy goes, and then, economy goes down the drain, who comes and buys it,
Oh, okay.
It's a simple question. Who has the money to buy?
Here we're about like 80% vaccinated, I think. And it's basically gone. No more.
I heard it's surging again in Israel, though, actually.
Oh, really? I didn't hear. Maybe.
Yeah, we have, in England, we have 80% of the adult population vaccinated. Once. So to get 2 vaccines, like in Israel, I think it's much lower. It was absolutely impressive in Israel how many people got vaccinated so quickly. It was absolutely amazing.
Yeah, I mean, there were people that were scared, but I think most of those people ended up doing it.
Peer pressure.
Yeah, I mean, being scared mostly just delays it. Eventually, you give in to peer pressure and do it, and then once
but here, the peer pressure is the opposite, right? Like if you live in like Alabama or something, like
Yeah,
Right.
That's.
You have to keep it a secret if you get vaccinated, because otherwise the people in your church will judge you or whatever.
Yeah, I think we can start. So, Georgie, do you want to introduce the first speaker?
Yeah. All right. So welcome back. I hope you all have a good break, a nice coffee for some of you. So we start this session with Gonzalo Torroba. He's going to tell us about hyperbolic compactification of M theory and de Sitter quantum gravity. Please take it away.
Okay, thank you very much. I'd like to thank the organizers for putting together this wonderful conference. It's really helpful in these difficult times. And also thanks for the invitation to speak. I also want to acknowledge my collaborators in this work, Bruno, De Luca, and Eva Silverstein. And yeah, let me turn off, as I said, my camera so I get a better connection, but I'll turn it on in a little bit. So one of the central problems in theoretical cosmology, as we know, is to understand the accelerated expansion of the universe. And especially, we would like to be able to have a framework to understand quantum gravity in such cosmological spacetimes. Our approach to this problem proceeds in two steps. So first, try to find de Sitter solutions in string or M theory, and then understand them as the formations of AdS-CFT. So if one succeeds in uplifting AdS-CFT from negative to positive cosmological constant, then that would provide us with a holographic formulation of cosmology. So that's a broad plan. Now, in this talk, it will be a bit more specific. I'll present a simple mechanism we have found very recently that yields de Sitter solutions in M theory, and it uses a very, very minimal list of ingredients, especially hyperbolic manifolds and Casimir energy. So it's based on this paper here. I do want to apologize because I only have time to cover this paper. And of course, this is a very exciting area with many interesting and new results. So hopefully we'll have more on that in the discussion sessions later today. Let me begin with a brief overview of the framework. So in string or M theory, we look for solutions of the form, some d-dimensional space-time that we want and some internal space. We have to solve the Einstein plus matter equations of motion to find this. But it's usually very helpful to think about a slightly simpler problem, which is a homogeneous dimensionally reduced potential, where we are just integrating the different energy sources over the internal space, and then we get to understand how these sources compete or how they can be used to find useful solutions. Okay, and let me super briefly review how the standard AdS-CFT energetics works when we do this. So remember, generically we have some color branes, and as we know, these space-time directions combine with the radial direction to give AdS, and the internal manifold that had positive curvature gets stabilized at a constant size. Now it's nice to understand how this arises from this homogeneous potential. What happens there is that there are two energy sources that are contributing. The positive curvature of the internal space contributes negatively to the potential, so it's trying to shrink, say, the sphere, while, of course, the flux lines are getting squeezed if we try to shrink the sphere, and they contribute positively to the potential here. Okay, note that I'm plotting the potential as a function of 1 over the internal size. Okay, and out of the competition of the two, we get a minimum with negative cosmological constant that corresponds to this AdS solution we were looking at. So the idea to uplift AdS-CFT to cosmology in perturbative string or M theory is then to change this first contribution that had positive curvature into a manifold that had negative curvature, because that would contribute positively to the potential. Okay, and then we have to find an appropriate source of negative energy that sits in between this curvature contribution and the flux contribution. Okay, and by working enough, one can try to put together these three types of ingredients to find solutions with positive cosmological constant. Let me remind you of the well-known Dine-Seifer mechanism that says that we know in string theory the potential will go to 0 into the compactification limit, and that's why you see that the potential is 0 here as a function of 1 over r. Okay, so that means that if we find a de Sitter minimum, it will be metastable. Okay. So many years ago, we gave a proof of principle that this works in type 2b. We found the S3 solutions Okay, these solutions, this solution was consistent, but used a somewhat complicated list of ingredients. Today, the goal will be to present a DS4 solution, so in the realistic dimension we care about, with as simple a list of ingredients as it can get. Yeah. So what is the setup and the stabilization mechanism? So we work in 11-dimensional supergravity limit of M theory. This source of uplift of the positive first contribution to the potential will come because we'll compactify on a finite volume hyperbolic manifold. Okay, and then we'll argue that the appropriate source of negative energy actually comes from Casimir energy that is localized in small cycles where we put antiperiodic boundary conditions for fermions. And we'll get the n units of S7 black flux, which means we have M2 branes around. For the side of the hyperbolic geometry, let me just remind you that if we are thinking, for example, in terms of H7 in the upper half plane metric, then we can get a finite volume hyperbolic manifold by modeling by a freely acting subgroup of the isometry group of the hyperbolic space. Okay, and for our purpose, these manifolds have a very important property called Mostow rigidity, which says that the hyperbolic structure is uniquely fixed in terms of topology. Okay. For us in particular, it implies that all metric fluctuations, except for the conformal mode, are gapped. And that's a really huge simplification if we compare to other compactifications that start their life with many moduli that one has to worry about. So here we'll basically have to worry about the conformal mode. Okay, so let me now briefly describe the source of negative energy. As I said, it will come from Casimir energy. So the idea is that these hyperbolic manifolds have small cycles. In those small cycles, we'll put antiperiodic boundary conditions for fermions, which means that the Casimir energy is dominated by bosons, and so it's net negative. Okay. One way to get these small cycles is from near cusp regions in the hyperbolic geometry. And here I'll locally describe such a region. So it has some radial direction, and then it has some toroidal cross-section that is decreasing with this exponential factor that accounts for the negative curvature of the space. Okay. So the idea is that we have some compact manifold. There are various of these near cusp regions that are glued into the bulk. And of course, if in this toy model we allow this y to go off to infinity, the manifold will be non-compact. At the level of this toy explanation, I'm just stopping the radial evolution at some fixed value yc, but there are ways to get smooth solutions where this ends in a smooth way. For example, by using a generalization of then filling called Anderson filling, and I'll talk about that in a little bit. So let me call lambda c the size of the smallest circle, this T6 in the toroidal cross section. Okay, then the proper size goes as lambda c times the exponential factor from the metric. So we get this small proper size, but it has a simplifying property that is shrinking very slowly, right? Because the derivative of this proper size with respect to y is much smaller than 1. Okay, so in this case, it's easy to evaluate what the Casimir energy is, right? The Casimir energy is basically an energy density in 11 dimensions. Okay, so it will scale like 1 over RC to the 11, 1 over the proper size of this cycle to the 11. Okay. And again, the minus sign is important. It comes because we're using antiperiodic boundary conditions for fermions. In terms of the comoving length, then we'll get this power of e to the 11y. Okay. And then basically we have to solve the semi-classical equations of motion that are supplemented by this quantum contribution from the Casimir energy momentum tensor. So that's the idea. At this stage, let me make 3 remarks. So the first is we learn from this formula that the Casimir contribution is strongly localized near these cusp regions because of this e to the 11y. Okay, this means that Casimir energy is distributed in homogeneous way. So we'll have to include the back reaction of that on the metric, and I'll talk about that in a little bit. Now, this is a quantum effect, so we have to make sure that it's large enough so that it can compete with the classical sources. We'll see how that comes about, how that can be done. But at the same time, we have to make sure that other quantum corrections are suppressed. And one can show that this happens if the curvature size of the internal space is stabilized at a much larger value than RC, and both are much larger than L11. Okay, so in this case, we only get to include this leading quantum effect from the Casimir energy. So let me combine these three ingredients we described at the level of the homogeneous potential, and then we'll consider what happens when we include back reaction. Okay. So we basically, as I said before, we have to integrate the energy sources over the internal space, and we like to understand how they can, how they contribute and how they can give rise to an interesting minimum. Okay. So we have three types of contributions. The first goes like 1 over L squared. That's the usual curvature contribution. I've written a coefficient A here that will play an important role for us. It basically accounts for the fact that the background curvature of the hyperbolic geometry gets corrections from warping and back reaction. So for now, I'll keep this number A, but I'll then argue that this A can be chosen to be small. Then we have the usual flux contribution. It goes like the number of branes squared divided by volume squared. Okay, so in terms of L hat, defined as the curvature radius in units of the Planck length. So the first term would be 1 over L squared. The flux is 1 over L to the 14. Okay, because it's 7-dimensional volume square. Okay, and then the last contribution is the Casimir density we just understood. So remember, we said it goes like 1 over RC to the 11. Okay, but the internal space is rigid. That means we can trade out for a 1 over L to the 11. Okay, and then there will be a coefficient K that basically has the ratio between L and RC. Okay. So this is the basic structure we get. Okay, and we see that this quite minimal list of 3 ingredients has the right properties to yield a metastable solution with positive cosmological constant, because the negative energy source sits in the middle between the curvature term and the flux term. Okay. In particular, by balancing these terms, one finds a solution where L hat, so the size in units of the Planck length, is stabilized at order K divided by A to the 1/9. So if we can take K divided by A large, then we'll have parametric control, and we'll argue that indeed we can get A small. Okay, and moreover, this is a polynomial with 3 terms. So as expected, we can differently, like we can control differently the curvature of the potential and the height of the potential. Okay, and in particular in these solutions, we'll get near cancellations of the different terms. We'll get scale separation. Okay, meaning that the internal size it becomes much smaller than the de Sitter size. So this was at the homogeneous level. So the main message so far is that from these 3 ingredients, we get the right structure to get the de Sitter minimum. But now, of course, we have to understand what happens when we include back reaction that is driven precisely by this property of the Casimir energy that is strongly localized near these thin regions, like near these cusp regions. Okay, so to account for that, we have to consider the following metric ansatz. So besides our de Sitter 4 metric, we need to allow for a warp factor, e to the 2a. I'll often call e to the 2a-u. Okay, and also in the internal space, there will be modifications. The conformal mode will generally be activated. And also there will be metric deformations orthogonal to this volume mode, to the conformal mode. So this becomes a PD problem with 7 variables because we have a 7-dimensional space. Of course, it's very hard to solve, and I'll make some brief remarks about that towards the end. Here, instead, I'll focus on a more semi-analytic approach to understand this problem. So one useful way to organize the problem is to think about an off-shell effective potential that is completely equivalent to the 11-dimensional equation of motion and includes the effect of warping. So this was found by Mike Douglas a few years ago. So it looks very similar to the potential we were writing before, but notice that it includes the effect of this warp factor U here in the volume element and in the gradient term. Okay. And Mike showed that in order to get the correct 11-dimensional equations of motion, one has to supplement this potential by Lagrange multiplier C, whose role is very intuitive. It's basically fixing that we're working at fixed G Newton. Okay. And if this C is chosen to be the 4D curvature scale, then one can prove that extremizing this potential with respect to U and the other matter fields is the same as the 11-dimensional equations of motion. Okay. Here, I want to know that the extremization of the potential with respect to U, which is the same as the time GR constraint, has a very simple and suggestive form. Here you find it. So notice that this is a Schrödinger problem where U is a wave function, okay? And the Schrödinger potential is basically minus the potential density from here. So there is a right-hand side that comes from this C. But as I said before, usually this C can be tuned to be much smaller than each of the individual contributions to the potential. So in many cases, it's enough to neglect it. Although one can also take it into account, of course. But then it's important to realize that this has a form of a Schrödinger problem that provides a lot of intuition for different properties. Okay, and here I'm just showing again the fact that if one extremizes. If one solves the constraint, which is the Schrödinger problem, and also extremizes the effective potential with respect to the other fields, this reproduces the full 11-dimensional equations of motion. Okay. So let me just list some general properties that can be understood by using this effective potential. The first is we understand that we can get this important tuning A much smaller than 1, because we see that what contributes to the curvature is not just the background curvature, but there are also corrections from warping, like this gradient term. Okay, so by choosing discrete parameters in our compact manifold, it's possible to nearly cancel regions of negative curvature with regions of positive curvature. Okay, and that's the origin of this A much smaller than 1 tuning that we need. Okay, remember that tuning is needed so that the Casimir term, which is a quantum term, can compete with the classical sources. I'll also say that, well, Douglas proved that the naive conformal factor instability at large momentum is stabilized by warping. So that's an important property. Also, warping provides a bound on negative energy, okay? And the way to understand that is that if we get a region, say, where Casimir is growing too much, okay, this negative Casimir energy is contributing positively to the Schrödinger potential, which means that the wave function will transition into a classically forbidden regime, and it will decay exponentially, and it will shut off that excess of negative energy. Okay, so that provides a bound on negative energy. And also we have derived that the warp factor provides a universal positive contribution to the mass matrix of all the metric fluctuations. Okay, so these are some general properties. Now I want to change to show you an explicit de Sitter solution, a smooth solution in one of these near cusp regions, okay, that then will have to be glued onto some compact part. And again, I'm focusing on this near cusp region because that's where inhomogeneities are concentrated. As will become clear soon, it's enough in this case to just focus on the real direction because the angular directions become important once we try to glue onto the bulk. Okay, so for now, I'll just consider a metric that depends only on this single radial direction. That's quite simplifying because we get ordinary differential equations instead of partial differential equations. Here is the metric ansatz. As before, it will have some warp factor. There is a radial direction, and then there are two say fields. One comes from the Casimir circle, RC. Here, just for simplicity, I took 5 of them to be equal, okay? And in the last term, I'm incorporating this Anderson or then filling, which will basically be a cycle that shrinks smoothly and ends the space in a smooth way, instead of having to just end it by hand at the wall as we did before in the toy model, okay? And here in the left-hand side, I'm showing one of these numerical solutions that leads to a DS4 in the space-time. Okay, so let's begin with the orange curve. Okay, so the orange curve is R. Okay, and you see that at y equals 0, R goes to 0 linearly. That's precisely this Anderson or then filling that is ending the space there. In physical terms, we would say it's like the horizon of a black hole, except that it's a space in a space direction. Okay. And then the green curve has a warp factor, and the red curve has the evolution, the radial evolution of the Casimir circle. Okay, and the idea is that
there's a question. Edward has raised his hand.
Excuse me, I'll post.
Okay. Okay. So this is a local solution, and the idea is that at some point around here we had to glue it onto the bulk. Okay. And on the right-hand side, I'm showing how the energy sources evolve pointwise. So this is the warped curvature. The flux, as expected, doesn't play an important role in this near cusp region. It's localized in the bulk. Okay, and the blue curve is the negative contribution from Casimir. Okay? And one can check that by integrating these energy sources, they all these two are competitive. Okay? And in particular, note this example already locally exhibits what I said before, that there are regions of negative curvature, like here, negative curvature contributes positively to the energy, and regions with positive curvature here and we can think about balancing them to accomplish this small a. Okay, so this was a local solution. Then the next step would be to glue this onto the bulk. A way to build a finite volume hyperbolic manifold is to start Hello?
Now we can hear you.
Can you hear me?
Yes,
Can
now we
you hear
can.
me now?
Yeah,
Okay.
and
Yeah,
you have 5 minutes left.
Good. Yeah, I'm almost done. So I was going to say, so we have to build now a finite volume compact manifold. We have to glue together these polygons. One difference with flat space is that polygons in a hyperbolic manifold also include hemispheres. Okay, and they are important in order to get finite volume because they stop this, growth towards, say, the boundary where we get infinite volume. Okay, and these hemispheres are precisely what source the dependence on the angular variables. Okay, so here we're focusing here on the cusp, but we'll be sourcing these angular directions. And at that point, of course, this becomes a PD problem with 7 variables, which is very hard to solve. The main point I want to make is that it's a completely explicit problem. Okay, and we have started exploring a promising direction, which is to use neural network methods to approximate these solutions. Okay, so the idea is that we construct a loss function that is the sum of the equation square, and we use neural network ansatz in order to minimize this loss function, okay, and provide an approximate solution. And we have started this in the first non-trivial example, which is H3, and there we have found examples of solutions that work to a good approximation. Okay, so I'll just end there. So in summary, we have found a simple mechanism to obtain DS in M theory that uplifts the Largan limit of M2 branes, and it uses negative curvature and the automatically generated Casimir energy. Okay. We have given arguments for the existence of the solution beyond the homogeneous level. We are currently thinking more about tackling directly this PDE problem. Okay. Now, as I said at the beginning, for us, it's very important to have an understanding of holography in these cosmological spacetimes. Here, I'll just say that such uplift with realization of the DS-DS correspondence. And recently, there has been interesting and exciting progress in also understanding the dual of DS by using TT-bar type methods. So that's another interesting direction we are pursuing. Okay. And one last comment at this level is that the framework I was presenting can actually also be used to find more general cosmological solutions with accelerated expansion. And the idea is that one constructs a slow roll functional in the landscape and evaluates it to try to decrease it. Okay, thank you very much. I'll end there.
Let's all thank Gonzalo for a wonderful and well-timed talk. So there was a question by Edwards.
My question is just this: to make the Casimir effect compete with classical effects, did you start with an infinite family of hyperbolic manifolds such that the diameters of some cycles can be parametrically small?
What was important was this ratio that I gave here, this ratio K over A. That's what matters. So K indeed is related to the ratio between L and RC, but this A appears there. And what we used at the end is that this A can be tuned to be small by near cancellations of regions of positive curvature and regions of negative curvature. So indeed, we need some amount of small cycles to make this important, but it doesn't need to be super tiny, because what really care about is the ratio between K and A.
Well, there I can see two possibilities. One is that you just hope that there is a hyperbolic manifold where the numerically things work, The other is you might have a family of hyperbolic manifolds that approaches some kind of singular limit, such that if you're far out in the family, parametrically, it will be guaranteed to work. I was trying to ask which of those two is the way you're looking at it.
Can you repeat the first option? I couldn't hear it.
The first option is just that you might be lucky and find a manifold where numerically some cycle is small enough so that some Casimir energy is big enough. That's one option. That would be a little bit more like what people usually have with flux compactifications, where you don't have things working parametrically. What would be better would be if you had, I don't know if it happens in 7 dimensions, in 3 dimensions, you can have an infinite family of smooth hyperbolic manifolds that approaches a singular configuration, such that parametrically you'd have small cycles if you're far enough out in the family. So in that kind of scenario, you'd be guaranteed, possibly, that it would work, rather than just hoping that numerically it manages to work. My question is,
I think,
my question is,
I think there are examples like that in higher dimensions also, that mathematicians have studied that can.
Are you built into your story so that parametrically, when you claim something is big enough or small enough, is that supposed to be true parametrically in your work? Or are you simply hoping that numerically it's big enough or small enough?
Well, as I said, I mean, well, parametrically, I mean, here the parametrically large number is this k over a. That's what I'm saying.
Well, I've lost a little bit what it was, but I'm
just saying it's not just k. We care about the ratio k over a.
But the mathematical question that you asked, there are explicit examples like that. This Anderson paper gives those examples. So,
well, do they have the right property for your construction? Is your analysis based on examples with infinite families so that you can make parametrically valid statements?
The cusp can be parametrically small in the way that you suggest, and there are explicit examples with right-angled polygons that have been that you can find in our paper that were discovered recently that show that.
And your assertion is that then parametrically, whatever inequalities you need are satisfied?
Well, what we showed is that in those examples, the cusps are an order 1 part of the volume, that in the local solution, A starts out a little bit less than 1, and that the discrete parameters in this construction, including these ones involving the Anderson filling, allow you to tune A. There's a way to go up in A, there's a way to go down in A explicitly in the discrete parameters.
Okay, thank you.
Next one is Ivano, please.
Yes, hi. Thank you for the very nice talk. And the paper is also very nice, but I was wondering, I suppose my question is at least somewhat related to the previous one. More in general, what are the possible subtleties regarding, control and stability of all the constructions? Not necessarily just the hyperbolic manifold itself, but anything else that could go wrong, essentially.
Well, okay. I mean, as I said at the beginning, one thing that is very helpful here is this rigidity property. Right. That is quite helpful in order to stabilize most of the directions you could think about, like these, like these metric fluctuations that are orthogonal to the conformal model. They all get masked because of this Mostov rigidity. What can go wrong? Well, I don't know. I mean, for example, you could worry that this negative, this Casimir energy produces a tadpole for RC, for example, right? Because it goes like 1 over RC to the 11 and is negative. So it will try to just shrink RC and produce a singularity like that. You could worry about that. But as I said very briefly here, that is actually avoided by the warp factor, right? Because once this RC starts to decrease and the Casimir becomes competitive with the other sources, it will change the sign of the Schrodinger potential. And it will send you into this classically forbidden regime where the warp factor will shut off that because it will decay exponentially. So, yeah.
So essentially,
I should also say, sorry, go ahead.
I'm sorry, I was just saying what it seems to me that you're saying is that everything is controlled within a dimensionally reduced effective field theory. So there's no subtleties.
Well, as I said, I mean, here, for example, I showed an example of a local solution that was evolving in internal space. That, of course, goes beyond just a naive, homogeneous approximation where you do dimensional reduction. So far, I mean, we have various indications that the solutions are stable. We do not have a complete proof yet, but we're as we say in the paper, we are working on that also. Yeah.
Okay. Thank you very much. Thanks.
Yeah.
I think we have time for one more quick question, then. No.
Sorry, is it my turn?
Yeah.
Thanks for beautiful talk. Most boring question. What is the SUSY breaking scale? So you have a couple of scales in your compactification here, right, from these small cycles. And it seems like that shortest length scale is probably the SUSY breaking scale. Is that correct?
Yeah. Here SUSY is broken at the high scale when we compactify on the hyperbolic manifold. Yeah.
Right, but it's the shortest. I mean, you have these cycles that are degenerating, and then you want to get Casimir energy from them. So those boundary conditions break SUSY at that short scale, right?
I think we might have lost Gonzalo.
Oh, so maybe we go to the next talk.
Yeah, maybe we can go to Jeff's talk if he's around already.
Jeff is here.
Yeah, thanks.
Okay, let me share my screen. Okay, that seems to work.
Ready? So next in line is Jeff Pennington. He's going to tell us about quantum extremal surfaces without a bath and where we can find dangerous Pythons. Please take it away.
Great. Okay, so thank you very much indeed to the organizers for inviting me to talk. Sorry I can't be in person in Brazil. Okay, so this is going to be a talk on some work with Netta Engelhardt and Arvind Subramanian that came out last month. It's going to be a talk, as may be clear from the title, that's not actually going to be about evaporating black holes. It's going to be about non-evaporating black holes. But I wanted to start by very briefly reviewing the hopefully familiar story back from 2019, originally from these two papers about quantum extremal surfaces and what they tell us about evaporating black holes. Okay. So to make an ADS black hole evaporate, what you do is you couple it to some auxiliary system that's normally called a bath. And what you find, the sort of technical central feature of these papers, so we find this so-called quantum extremal surface, this dot here, which is just an extremum of generalized entropy area over 4G plus bulk entanglement entropy. So just the bulk entropy of everything between this surface and the boundary of the original system. And yeah, just by finding an extremum of this surface, then extremum of this generalized entropy, then we find out all sorts of properties about how the information in the interior of the black hole ends up being encoded in this sort of combined black hole bath bipartite system. So just to briefly review some of the things you get out of this, via the so-called QES description, generalization of Ryotaki-Nagy, of Engelhardt and Moore, then you find that the entanglement entropy of the radiation of the black hole, and the black hole itself follows the so-called page curve, goes up until the page time and then goes back down. We also have this idea of entanglement wedge reconstruction that involves a lot of people, but particularly there was a beautiful paper by John Carlo and Wall that sort of first proved it. And in this case, what that tells you is the so-called Hayden-Preskel decoding criteria, which is just a precise statement about sort of when and how information comes out. Basically, you need to wait until after the page time, and then there's a scrambling delay for particular information thrown after that. And it also tells you that the way that information gets out is what's called state dependent. You can only, if there's a couple of qubits you don't know about the state, then you can find them out. But if you don't know anything at all about the state, you can't find it out. The information is only accessible if you know a decent amount already. And the sort of final thing that I'm going to mention follows from this thing called the Python's lunch conjecture. There was recently a paper I wrote with Brown, Garabay, and Siskins. And what that tells you in this case is the complexity of reconstructing this information, say in Hayden Presco and so on, is actually exponentially hard. It's exponential in 1/G Newton. Okay, so this one QES, this one technical contribution, finding this surface, just has all these huge consequences. There is one very brief note I want to say before I move on to non-evaporating black holes. Just there's a slight difference between these sort of points 1 and 2 I made here and point 3, which is that really there's two quantum extremal surfaces in an evaporating black hole. There's this surface, it's now very famous, I've just talked about so much. And there's another surface, which is just the empty set. It's not really a surface at all, but it is extremal in a sort of trivial sense. And what matters, what causes a lot of this stuff, is working out which of these two extremal surfaces has smaller generalized entropy. It's the so-called minimal QES. Okay, so points 1 and 2 follow from basically tracking which of the two quantum extremal surfaces is minimal. And before the page time, it's this trivial empty set surface. And after the page time, it's this non-minimal, non-trivial one in the horizon black hole. Point 3 is a bit different, and point 3 actually follows just from the existence of the second non-minimal QES. So it's following from the opposite QES from point 1 and 2. But given one of the QESs is trivial, then at a technical level, really they all just follow from finding this non-trivial QES. Okay, so that is 5 minutes of talking about evaporating black holes. Now let me move on to my real interest for this talk, which is of course non-evaporating black holes. So in this case, we're just taking some black hole in ADS, we're not coupling it to any bath or anything crazy like that. And we're just letting it sit there for some long time, maybe more than a scram of time or so. So let's think about what we have and what we don't have out of the sort of interesting features from bath that were explained by this quantum extremal surface. Well, obviously we don't have a cage curve. This is just some pure state that's just sitting being a pure state for all time. There's no interesting transition happening there. So that one we can rule out. Okay, what about point 2? How information is encoded? Well, we don't have the sort of two systems of black hole and bath with it potentially being encoded in one and the other, but we could still have some notion of state dependence. This goes back to Raju and Papadopoulos back in early part of last decade. And in particular, we definitely still have point 3, we still have exponential reconstruction complexity. Specifically, if I have some interior partner of a Hawking mode sitting like this, then the sort of usual methods we have for reconstructing that will not work. And there's very good evidence that it should be exponentially hard to reconstruct that on the boundary. Okay. So it sort of seems like we still have a lot of these features that the QES explains so nicely for evaporating black holes with baths. But we have a problem. And that problem is that in this state, there is absolutely, definitely, certainly no 10-second proof of why that's true. And that's just that if our black hole is formed from collapse, then the entire space-time is causally separated. It's in the causal future of the boundary. And by the quantum focusing conjecture or the generalized second law, there's various ways you can prove it, but a quantum extremal surface can never be causally separated from the boundary. Roughly speaking, if I shoot light rays from my causally extremal surface, then the generalized entropy always gets smaller as I do so, but that means it can't get out to the asymptotic boundary because the surface, but we don't have a quantum surface. So it seems like maybe we need some whole new explanation, some second way of explaining the exponential complexity and so on that it's just completely different to the usual one, to the evaporating black hole one, which obviously would be a bit unsatisfying and sort of how many times would we have to keep doing? And actually, there's something a bit stronger here, which is that in the paper Netter and Arvin and I put out in February, we actually proved that so long as the bulk physics in your ADS-CFT spacetime looks classical, then in fact, there could never be another explanation for exponential complexity. That exponential complexity can only come from having some external surface and trying to reconstruct stuff behind that. Right? There's no alternative possibilities, at least in the case where the bulk physics looks classical. So of course that's not the case here. The bulk physics is inherently quantum. There's the Trans-Planckian problem and so on that you just wouldn't have classically. So again, you could say, okay, sure, maybe that's true classically, but maybe once you include quantum effects, then there's sort of no analogous version of our theorem, and you again just need a different explanation for the exponential complexity. So that would be a set of answers, but it would be a pretty unsatisfying set of answers, I think hopefully you would agree. So now I've set up the sort of central conflict of my narrative, then I can sort of introduce the resolution and tell you how it's all going to work out and everyone's going to get home safely and live happily ever after. And that's that really quantum extremal surfaces are always still going to be secretly, making everything work and manipulating everything behind the scenes. They're just going to be doing so in a slightly more subtle way. So let me now lay out our claimed resolution to this story. So the first thing to note is that when we talk about reconstructing operators, we can never mean sort of that reconstruction doesn't depend only on a single state, right? Like sort of by definition, if you want to do some reconstruction, then in the language of Almiri, Zhang, and Harlow, you need to be considering an entire so-called code subspace states, an entire set of your black hole is in one of those states, but you want to distinguish them all using some operators, some set of states that differ in this degree of freedom that you want to reconstruct. Okay, so hopefully that's a familiar story to most people. But the key point that may be less familiar, and unfortunately I won't have time to really deeply justify it for you, but it's like vaguely intuitive. But if we want to know the complexity of some reconstruction of a particular operator for some particular code subspace, then what we got to do is we got to look for quantum extremal surfaces for the maximally mixed state within that code subspace. Okay, so the operator is not associated, the reconstruction is not associated to a single state, but a code subspace of states. Entanglement wedges are associated to a single state. So you might say, like, which state in the code subspace should you be using? There's a whole infinitely many of them. The right answer is that you should look at a maximally mixed state in that code subspace and look for quantum extremal surfaces for that maximally mixed state. Okay, so this follows by just going carefully through the sort of original analysis, the original arguments for this Python's lunch conjecture that QASs explain exponential complexity. But I'm not going to have time to really go deep into those arguments. They involve tensor network analogies and there's various other pieces of evidence you can argue for. But the evidence is as strong as the evidence that this Python lunch conjecture is true. Okay, so then the final statement that will resolve all the problems and make everything work is that any code subspace where the interior degrees of freedom, the interior partners of the Hawking modes, are like some excitable degree of freedom in that code subspace, they're included in that code subspace, will always have a quantum extremal surface in its maximally mixed state. So even though the actual specific state you get from like forming a black hole from collapse, which always has this interior Hawking partner and this exterior Hawking partner in sort of the same fixed entangled state, that doesn't have a quantum extremal surface. But if we allow those degrees of freedom to be part of our code subspace and to be excited and so on, then the maximally mixed code state in that code subspace always does have a quantum extremal surface. And this explains why reconstruction is so difficult. It also explains state dependence and so on. Okay. And again, I want to emphasize that at least for small code subspaces, this is going to be a non-minimal QES. The minimal QES is still going to be the empty set. So reconstruction will still be possible. It will just be exponentially hard. Okay. Any questions about that? Just briefly, and then I'll try to sort of focus the rest of this talk on explaining this point for you and showing why there's a QES in these maximally mixed states. Okay, great. Okay, so why is there this sort of secret QES that we don't see in the sort of state we usually consider that's formed from collapse, but it is there when you actually try to reconstruct QES? Well, the first thing to note is that if this a particular Hawking mode and its interior partner in our code subspace, then in the maximally mixed state in that code subspace, they're not going to be entangled anymore, right? In the usual post-collapse state, they're entangled, they purify one another, but in this maximally mixed state in our code subspace, they're just going to be in some mixed state. We're going to have no correlations between us. Okay, so now what we're going to do is we're going to consider some surface gamma. So it's going to be a sphere. It's going to be sitting a bit inside the horizon here. And it's going to be a very, very long way into the past, really far into the distance. And then we're going to imagine it perturbing it sort of outwards, either to future light-like direction or past light-like direction. And we're going to see what's happening to the generalized entropy when we do so. Okay, let's start by imagining perturbing it a bit in this direction, so in the future outwards direction. What's going to happen? Well, we're in the interior of a black hole, and it's a fixed size black hole. So the area is just going to get smaller when we do so. Okay, so as we move, that's just a feature of being the interior of a black hole, being trapped surface, classically. But it turns out for perturbing in that direction, the area change is going to be the dominant effect. It's going to have a much bigger effect than the bulk entropy change. And so perturbing in that future outwards direction is going to make the generalized entropy smaller. Okay, say that the quantum future outwards expansion is strictly negative. Okay, what about if we perturb the sort of other way in the past outwards direction? Well, in this case, obviously, we're going outwards to larger radius. So the change in the area from this little perturbation is going to be positive. But on the other hand, you've got to remember that this surface, we've moved way into the distant past. Okay, and as the surface, as we go back further into the past, parallel transporting everything along light rays, then everything gets sort of closer and closer to the horizon, right? The areas of surfaces all basically become the horizon surface. Everything comes at the horizon area radius, and so this sort of change delta A from perturbing outwards gets exponentially suppressed by the time that our surface gamma is in the past. Okay, so if it's really far back in the past, this effect becomes very small. There's another effect, and that effect comes from looking at the change in the bulk entropy. So remember that this mode, this interior Hawking mode, was not entangled with its exterior partner. That means as we move the surface gamma outwards and into the past a little bit, then we're going to be losing the entropy, the bulk entropy of this mode, which isn't entangled with anything else outside. And so that's going to decrease the bulk entropy as we perturb it outwards. Okay, and this effect is not exponentially suppressed, it's just still there no matter how far we get into the past. And so if we go far enough back in the past, this change is going to dominate, and the overall effect is that, again, going outwards is going to make SGen smaller. The quantum past outwards expansion is going to be negative. Okay, so that was probably the most technical part of the talk. I was just trying to give a heuristic picture of why it happens. Obviously, the actual arguments are a lot more technical. But basically, the summary is that we found this surface gamma that's deep in the past, inside the interior of the black hole, that if we move it outwards, either to the future or the past, then it gets smaller generalized entropy. Okay, it's going to turn out this is going to get us a long way towards finding a quantum extremal surface. So let me explain how it does so, because so far we've not actually found a quantum extremal surface. We've like quantum extremal surface would have delta SGN be 0 at leading order for any perturbation. But it turns out that having this gamma with its properties will always lead us to finding a quantum extremal surface that is outside gamma, like further out than gamma. Okay, so let me explain how that works. It's a sort of cute little argument involving what's called restricted maximin. So the first step is we have our surface gamma, and we're just going to consider a Cauchy slice for the exterior of gamma. Okay, starting gamma going out, blue dot. We're just going to minimize over all surfaces within that Cauchy slice. Then finally, with step 3, we're going to take that minimal SGN surface, and we're going to maximize its generalized entropy over all possible Cauchy slices going outwards from gamma. Turns out this is a well-defined thing that basically doesn't become badly behaved or anything. And it's pretty clear from the variational sort of construction we use that one of two things has to be true. Either this surface is just extremal, and then we're done, or it would have to be sort of impossible to fully vary it in every direction. I.e., it would have to be on the boundary of the sort of allowed region. It would have to either be touching gamma or be like have part of it light-like separated from gamma. Okay, but this is where the fact that we found these outwards expansions from gamma and found them both to be strictly negative is going to save us. Okay, we can't have it, for example, touch gamma here, because by definition, then perturbing it slightly in any outwards direction will decrease SGN, and so it will always, surface touching gamma can never be minimal within any Cauchy slice. And you can make a similar argument that
you have 5 minutes left.
Great. Yeah. So you can make a similar argument that it can't be light-like separated from gamma. Okay, so the fact that we found a surface gamma with these properties means that there must exist a quantum extremal surface outside it, and that quantum extremal surface will explain the exponential complexity and so on. Okay, so it's reasonably good timing, because I'm just going to make some brief final summary here. So what have we learned here? What have I not told you about, and so on? I think the big takeaway of this paper and what we sort of advertise it as is that the lessons about into black holes from studying quantum extremal surfaces aren't just some very specific feature of what happens when you make a black hole and ADS evaporate by coupling to a bath. They're not even specific to like evaporating black holes, maybe in flat space or whatever. They're really a very general story about that they explain the weird information theoretic and sort of reconstruction properties of black holes. There's always a QES somewhere that's responsible. So even though non-evaporating black holes that have been formed from collapse don't have a quantum extremal surface, the moment you consider a code subspace that allows excitations of interior Hawking partners, then the maximally mixed state of that code subspace will have a QES, and this explains the exponential complexity and also the state dependence. So it didn't really talk about, but it's also important of trying to reconstruct those interior modes. It's a load of stuff in the paper I didn't talk about. I encourage you to go read it. But in particular, I just sort of said some vague words about exponential complexity here. There's actually precise formulas you can give that will exactly give you the exponent depending on the size of the code subspace you're considering, et cetera, et cetera. There's also other examples of black holes being weird and being hard to reconstruct the interior, et cetera. Particularly this paper from 2019 by some computer scientists, Bulan, Fefferman, and Bazarani. And again, it all gets explained by very similar stories about secret quantum extremal surfaces that aren't there in the states you naively consider, but when you consider the right state, then you do find them. Yeah, so please read the paper. But I just want to finally end on something that I think otherwise someone will ask me as a question. It's a pretty natural question. So why did we need to do all this? Why did we need to start explicitly talking about code subspace and reconstructing interior Hawking modes before this QES appeared? Right, for an evaporating black hole, you just use the original post-collapse state, and you already have a QES, and you don't need to do any of this rigmarole. Aren't we just like, desperately trying to come up with something new to fix the problem? So the answer is no. If you want to do the evaporating black hole calculations correctly, then if you're trying to ask a question about like reconstruction complexity, about whether reconstruction is possible, then you do need to consider maximally mixed states in an appropriate your particular choice of code subspace to get the right answer. But of course, for evaporating black holes, you have weird stuff going on, like the page curve, etc. Even before you do that, even if you're just considering a single state and you're not talking about reconstruction at all. On the other hand, not evaporating black holes, then there's nothing really weird going on until you start thinking about these interior Hawking parts. For example, if you just think about some object being thrown into a black hole, for an evaporating black hole, that becomes exponentially complex to reconstruct. But for a non-evaporating black hole, it's easy. So the sort of lesson here is that quantum extremal surfaces appear exactly when they're needed, but not before and not after. They're like a wizard in Lord of the Rings. They show up precisely when they mean to. If there's weird stuff going on, there'll be a QES that's causing it. But if there's no weird stuff going on, probably not a QES. So yeah, thanks a lot.
Okay, let's all thanks Jeff for a really, really good talk, and again, well timed. And I can already see Dan as his hand up.
Hi Jeff. Yeah, so there's in this maximally mixed state where you allow both the interior exterior modes to be entangled with the reference system. I'm curious, so one way you could try to think about that is you could say in that state, those modes aren't entangled, so there should be some kind of firewall, at least for the modes that you allowed to be activated in the code subspace. But then I could also say, no, entanglement equals geometry, and the interior mode is now really the thing in the reference system that the exterior mode is entangled with. Do you have an opinion about which way is the right way to think about that state, or maybe they're both right depending where you got it from, or yeah?
Yeah. Okay. I feel like there's a few sub questions in there, so let me try to answer them one by one. If I forget one, then remind me. Okay. So the question of whether there's a firewall or not, I think people use different words to mean firewall, in the sense that they're not entangled anymore. Then there's always a firewall. In the sense of will you get vaporized if you fall in? Then it depends when you fall in, right? So if you fall in at the time that we're these are IR modes, then it's fine. You'll just see that they're not entangled, but nothing crazy will happen to you. If you evolved a while back in time, back towards where this quantum extremal surface is showing up, then you'll hit some sort of firewall.
But you see, in the other way of thinking about it, though, like the old black hole, then you would say, even if you jump in early, you don't hit a firewall, because really that interior mode is now encoded out in the reference system, right?
Yeah. So okay. Yeah. But that is again just if it was actually in this maximally mixed state, right? We're having to consider that it's maximally mixed state because we want to be open to the possibility that there's a firewall and determining whether there's a firewall or not. But if it actually turns out that it was just a post-collapse state and nothing weird had happened to it, then there's no firewall. You just jump in and you just see that there's no firewall. So yeah, I think that's
actually in this state. It seems you can think about it either way, right? You can either say there's a firewall. I mean, this is kind of an avatar of state dependence in this even for this simple black hole.
It's certainly. Yeah, I certainly agree. It's in some sense an avatar of state dependence. But I think, at least at this level, I would say, this is the state you're considering the state because it's the state of your knowledge before you're jumping in, and you're like, oh, it could have a firewall, it could not, we don't know. So the state of my knowledge is it's a mixed state that could have either. But then you jump in, if there's not a firewall, you just see there's not a firewall. Yeah, the other thing I would say is I think you were saying, isn't really the interior mode the thing that purifies the exterior partner? I would say to that, definitely no. I mean, like it is in a post-collapse state, but in this state, we've like disentangled those two, and yeah, at least when they're low energy, then you can do that. Now, if you go into the past and they become transplanckian, if various things happen, it becomes a white hole, blah, blah, blah. But yeah, maybe we could talk about that question more offline. But I think at least the simple question is no, they're just disentangled.
There's one more question, Suvrat.
Yeah, hi. I actually had a very similar question to that of Daniel, and maybe I can make it a little sharper. So if you were to consider these states where these modes are disentangled, there would be a contribution to the stress tensor, and that would back react on the metric and would also change your area term. So you took into account the change in delta S due to the disentanglement, but I was confused why you didn't have to take into account the change in delta A, because there would be a strong back reaction on the metric.
Yeah, great question. So there's a certain amount of ambiguity in how you gravitationally address this change. One nice way to do so is you can disentangle these two modes just by basically acting with a random choice of unitary on this exterior mode, and then averaging over all those different choices of unitary. Okay, so that will disentangle them. And with that particular gravitational addressing, then just by causality, then it can't change the local geometry over near the surface gamma. And so this geometry near the surface gamma will be completely unchanged. It will the geometry sort of back here will be completely changed. And in fact, in this maximally mixed state, what will happen is with high probability, if you evolve back in time, you'll get a white hole, and you need to have that happen because this thing can't be causally separated from the boundary. But the geometry near gamma, depending on how you gravitationally address it, there can be no back reaction at all. And even if you gravitationally address it a different way, then I think the back reaction would be negligible there, or unless you do something weird, it would be negligible there. So yeah, very good.
Okay, thank you. Yeah, okay, thank you. Yes.
Ben, if it's a really quick question, you can have it now. If not, we can leave it for the discussion perhaps tomorrow. But if it's a quick question.
A very quick question. I don't know if the answer is quick. It seems like you developed the tools to answer the question whether a generic pure state has a firewall. And what is the answer to that?
It is not a quick question.
I'm not sure we fully, yeah. I don't think we fully developed the tools to answer that because we're starting from a bulk state and then asking questions about that bulk state. I think when I always get unhappy with this. So to me, I only know how to talk about a generic state from a boundary point of view rather than a bulk point of view. I'm not sure what I mean generic state from the bulk. That's I guess the question. And it's not clear to me that a generic boundary state has one unique preferred bulk description. It seems to me that it might have a load of different equally horrible equivalent bulk descriptions. But that's all I'm going to say because otherwise we're going to get way too far in the weeds and I'll get in trouble. So
thanks.
Well, because we don't want Jeff to get in trouble, let us give the floor now to the organizers for the discussion session that comes afterwards.
Great.
Oh. And let's thank Jeff again.
Thank you very much. So indeed, let's get started with today's discussions. So just a quick reminder that the way this works is 20 minutes for Eve and Daniel to do absolutely as they please, followed by 30 minutes of informal discussion, where I will be calling people by the order they raise their hand, except if you wave. And if you wave, it means that what your comment is related to what is being discussed right now, in which case we will go directly to you before continuing with the people that are waiting with their hand raised. And I just remind you that there are two discussions, one about cosmology and basically why we want the sitter, and the other one about the sitter construction. So how do we get to the sitter? So please keep that in mind as well, so that we can distribute a little bit the topic between between this morning and the afternoon. Okay, for me. So so thank you very much, and without further ado, I'll pass it to Daniel, I guess, who will start.
I'm muted. Okay, thank you very much, Pedro. Thanks a lot for inviting us to lead this discussion. Yeah, so I will kick off by making some, somewhat loosely related remarks, and then Eva will say a few words, and then we will open it up for everybody. So maybe the first thing to say, if I can change the slide here. Yeah, first thing to say is that I think what's nice about the subject is that there's a healthy information flow that goes both ways. So on the one hand, cosmology constrains string compactifications. So a realistic string compactification, should at the very least contain this is the vacuum, so that it describes the real world. But at the same time, string theory also informs the type of effective field theories that we study in the early universe. And so, of course, famously, inflationary models are UV sensitive. So, we need a theory of quantum gravity to give a conceptual foundation, to those theories of the early universe. And so it's a nice back and forth, and hopefully in the discussion, we will also see that these two things, are very strongly linked and inform each other back and forth. All right, so then the next thing, maybe let me remind you that we have a very successful standard model of cosmology. It's very simple. It only has 5 parameters. And with those 5 parameters, we fit a host of cosmological observations. So from the cosmic microwave background to the last great structure of the universe, it all fits with just these 5 parameters. But it's also a strange model because arguably, we don't understand any of these parameters from a fundamental point of view. So we don't know exactly what created the baryon asymmetry of the universe. We don't know the nature of dark matter and dark energy. We have good evidence, but no proof that inflation occurred. So we don't exactly know what the mechanism was that created the initial conditions. And so every single one of those 5 parameters, in some sense, is still not completely understood. And then, as I mentioned, dark energy and inflation are UV sensitive, and we need quantum gravity as a conceptual foundation for cosmology. And so that's an opportunity for string theory to make kind of statements about, current and future observations. Let me also say a few words because, in recent years, this has become very hotly debated, and I'm often asked about it, the so-called Hubble tension. So that's a persistent disagreement between measurements of the expansion rate of the universe derived from the cosmic microwave background and measurements derived from supernova explosions. And so both sets of measurements have become very precise at a statistical level, as you can see from these error bars, but they're discrepant at more than 5 to 6 sigma. Okay, so at a statistical level, there's a very significant tension or disagreement in the measurement, which some people interpret as the first crack of the standard model of cosmology. So the simple lambda CDM that I just showed you, maybe it's incomplete. If these measurements are correct, then that's the conclusion. Of course, there's still the option that these are just systematic errors that explain this big widened gap between the 2 measurements. And actually, there was a talk by Robert Dijkgraaf that I was listening to last week that made showed this quote in a different context where it said, any theory that can account for all the facts is wrong, because at any given time, some of the facts are always wrong. So that could be possible here as well. But to be fair, supernova people have been checking their measurements more and more precisely, and anything that people have thrown at them as possible systematic errors, has been addressed so far. And so there's nothing at this point in time where we actually know precisely to point at the weakness in the measurement. Okay, so it might be true. If it's true, however, it's hard to explain with new physics. So the problem is actually very easy to state. So maybe let me just take 1 minute to explain it. So the way the CMB measures the Hubble constant is by measuring the angular scale of features in the cosmic microwave background, and from that inferring the distance to the last scattering surface. Because you can predict what the sound horizon is at the time of when the CMB was formed, and then the angular scale tells you the ratio between sound horizon and distance. And so we have this measurement of the distance to the last scattering surface that tells us the Hubble constant. So if the Hubble constant was larger than what's inferred from this measurement, it means actually that the CMB is slightly closer to us by about 10%. Okay, and in order to keep the angular scale fixed, it means you have to then change the physical scale at recombination, namely the sound horizon, by the same 10%. Okay, so that's the theoretical challenge. You have to change the physics of the early universe to make the sound horizon shrink by about 10%. Unfortunately, 10% is a huge change because we are measuring cosmological parameters at the percent level, or better than a percent level. So the challenge really is to change the sound horizon by 10% while keeping everything else fixed, everything else that fits so beautifully, like this peak spectrum that you're seeing here. And that just so far hasn't been possible. So any change that people have proposed in the early universe physics, has other changes that are too large. Okay, but it's a very clearly stated problem. It's and so if somebody comes up with a solution, I think we would all recognize it as a solution. Okay. Of course, it would be nice to discover new physics using cosmology, and let me here just point out that cosmology is good at testing two different regimes of physics beyond the standard model. So on the one hand, of course, it probes very high energies because we go to very high temperatures in the early universe. But on the other hand, we also probe high densities, and high densities means that very weakly coupled particles that in colliders would be produced very rarely because the collisions don't have enough luminosity. In the early universe, these things can still be produced in significant numbers and then affect the dynamics of the early universe. Yeah, and I would argue that string theory is relevant in both of these regimes. So of course, it's the high energy completion of our theories, but it also, those high energy completions often come with extra weakly coupled hidden sectors, and those hidden sectors have to be consistent with cosmological evolution. Okay, so that's another point I just wanted to make quickly. Let me check my time. So high energy effects are encoded in cosmological correlations. So the correlations between densities at different points in space are the main thing that we measure in cosmology. And so we can trace those correlations back in time to an initial surface that's the initial surface at the hot Big Bang. The moment when the universe thermalized, the initial correlations imprinted on that surface. We discovered, in fact, that there had to be time before that surface that created the hot Big Bang. Something like inflation, had to have occurred there. And so the challenge is to figure out what type of high energy physics was first of all creating these correlations, and are there extra imprints that we can discover that give a more detailed features of the microscopic origin of this early phase in the history of the universe. And maybe more abstractly, can we actually classify or carve out the space of consistent correlations? Very similar, like on Monday we were discussing the S matrix bootstrap in trying to carve out the space of consistent S matrices. We would like to do exactly the same in cosmology, where we carve out the space of consistent cosmological correlations according to a certain set of rules and predict what's possible and what's not possible in kind of some broader context. And then string theory would be a specific, very concrete example of that broader context of quantum gravity. So the challenges in cosmologies are slightly unique in the sense that, of course, these are spatial correlations living at a fixed time. So time is integrated out. So we have to figure out how to describe this field theory at a given moment in time. The boundary theory is not Lorentz invariant. It's not unitary. The interactions in the bulk are scale, but not conformally invariant. And even more abstractly, we don't even have rigorous non-perturbative observables in cosmology. So things are a bit harder in that respect. And that explains actually why we understand things much better on the boundary of ADS or at asymptotic infinity for scattering amplitudes. And we have much less understanding for these structural questions in de Sitter space. Okay. And I would have argued, in fact, until recently, we didn't have a good understanding even at tree level of the analytic structure of these correlation functions living on the boundary of the space. Maybe I skip over this quickly because I don't want to run over time, but this is just to advertise that there was some recent progress in kind of trying to understand these correlation functions at tree level. And I think we now do understand the pole structure of these correlators and how to connect all the sets of poles that these correlators can have at tree level. And then last but not least, I should mention that there's many future observations that are coming up, both of the CMB and the last great structure of the universe. So I've just listed a few of them because it doesn't fit on a slide, but they're really a factor of 3 or 4 more. And so this is just a field with a very high volume of data coming in the next decade or so. And so I think it's an opportunity for theorists to say something now about what these experiments should or should not be seeing in the next 10 to 20 years. So maybe I stop here and let Eva take the floor.
Thank you very much. While Eva sets up her share screen, let's please thank Daniel.
Thanks, Daniel.
Beautiful talk.
Could you unshare? So thanks. Okay.
Today is the day where everyone is on time. Thank you very much, everyone.
Okay, that's a lot of pressure. Yeah, okay.
Not accidental.
So you see this? You see this? I'm just going to do the PDF version because I think it's quicker. Okay, so Daniel just beautifully summarized the status of observational cosmology as related to what you might call fundamental physics, and it's in a good place. One thing that's very inspiring to me and probably many other theorists is that part of the story of how this precision cosmology developed involved a brilliantly successful theoretical prediction of something big, the origin of all structure in the universe from quantum fluctuations. So the 2-point function of quantum field theory. This was quickly converted into explicit formulas for how it should appear in the radiation that we see. There was an observational, a multifaceted observational campaign to check that, and it works. It works beautifully. And it's sufficiently successful that it enables us to do further tests. So we can do precision tests of various things. Now, what I've written here is the level of error bar that we can expect already from CMB modes. There's an inequality here because we'll get more from large-scale structure. And if you think that the information problem debates are heated, you should see people debate how many modes we're going to be able to get out of large-scale structure. I mean, they go at it as well. And it's by the way, it's a place where theoretical work is important, and it's there are lots of interesting challenges there. As far as how it relates to our subject of the meeting, the theories can imprint their signatures on the power spectrum itself. There can be substructure in it. There can be non-Gaussianities, which in its full glory is a wave functional of the primordial perturbations. It's hard to get a systematic handle on that, but there are really interesting individual directions in this huge space that are testable and are in the process of being tested, and certainly more is available along those lines. B modes remains extremely important related to large field inflation. I'll say a little bit more about that later. And there are many other opportunities, as Daniel stressed. Okay. Sorry, I'm trying to go down. Okay, there we are. Okay, so there's that beautiful observational story with this simple model. And then there's the mess that we theorists deal with, which is, the full configuration space of string theory is involved in cosmology because we have lots of evidence that all the different limits of it are connected. For a moment, let's focus on the patch that we see, which is some causal subregion of the full picture. In that causal subregion, as I said, we get CMB and large-scale structure information, for example, that gives us constraints on primordial physics going on nearly 14 billion years ago. The main connection to our subject is that it is a fact by just standard Wilsonian effective field theory that all inflation models are UV sensitive. So a satisfactory theory does require control of quantum gravity effects. We, of course, describe or classify the perturbations perfectly well using bottom-up effective field theory. But with this motivation, over 20 odd years, there's been development of different string theory inflationary mechanisms that work out very well in themselves with testable signatures and discriminations available among them. To the extent that this has actually strongly informed some of the analysis, including the formulation of the bottom-up effective field theory. So as Daniel stressed, there's been a serious back and forth here. The connection that we have to data is nuanced, but it's there in this conservative sense of having these tests, but they are model dependent, and that's just the true status. So, but as theorists, we're interested in the challenge that we're given by the discovery of the cosmological constant in parallel with the structure of the string landscape. So we have to make sense of this bigger picture, and maybe even things like extra components of the universe. So that's a big job that's still in progress. Okay, so de Sitter underlies these models of cosmological evolution in string theory. So let me do a super quick overview of how those work in general. We've heard a lot of discussion of specific cases. So we start from some higher dimensional limit of the theory. We reduce to 4 dimensions. There are various contributions. One of them that plays a role in every example I know is the fluxes. The fluxes, as you know, as string theorists, take a generalized form, which is really important and interesting, which is that the field strengths are not just the standard field strength DC, say, but instead contain also these terms that involve wedge products of lower form fields and lower flux fields. And why that's important is that when you reduce the F² terms, you get axion potentials from these fields, these potential fields. And so you very typically get this phenomenon of axion monodromy. And in explicit models, one finds very clearly that as you go above around the 10 Planck range needed for phenomenology, you don't always find, there are models which are very, very clear on this point, strong effects of light fields. So I can, there's a paper, Powers of Monodromy, you can find examples there and a number of others. My point is this is a rather generic phenomenon, and this is where it comes from. In terms of the potential energy, we have many contributions. Gonzalo's talk really laid out why this kind of three-term structure is important, so I won't belabor it here. But I'm just kind of listing the laundry list of contributions, starting from the fact that most limits of string theory are supercritical and give a positive potential energy. Most manifolds are negatively curved and also give a positive potential energy. There's NS flux that appears in this leading term in the expansion in the string coupling, various negative contributions from orientifolds, Casimir energy, other quantum effects, and as I mentioned, the generalized flux fields. So there is UV sensitivity, or to use the more fun term, dangerous relevance in the problem, but we always have to keep track of when it matters and when it doesn't. So the warping plays an important role. We saw that in Torroba's talk, and I highly recommend this paper of Mike Douglas. It's a beauty. So the de Sitter examples that we work with so far can be kind of classified in this way. There's non-perturbative stabilization consistent with sub-KK scale supersymmetry breaking, basically the KKLT mechanism and many, many follow-ups. There's power law stabilization where one has less supersymmetry, which I would say is clearly generic for what it's worth, allowing for other contributions that give power law stabilization, the original one being this one where we start with the leading term in the potential energy, and we include O planes and flux. There's large D as the parameter that helps control the physics there, including corrections to the flux, which competes with the linear dilaton. And we've heard about other examples throughout the conference. And of particular interest to some of us are the ones where we uplift ADS-CFT. Okay. This potential energy is mostly positive, but has controlled negative sources. And for early universe inflation, we start from such models and then we consider more general dynamics. And the thing that's super interesting for this interface with cosmology is that both the existence of inflation and the signatures are sensitive to Planck suppressed operators and even in anything, you know, at lower scales than that. One phenomenon that I think is quite interesting is what we call the flattening effect, where as you go out in an influence on potential that might appear to be m squared phi squared, like that generalized flux squared, instead, since the flux potential depends on the moduli, those moduli relax a bit, and that leads to these funny flattened shapes that were found phenomenologically. And that I'll show you where that goes in the data. But there are earlier models realizing a certain form of slow roll inflation or non-trivially interacting single field inflation, the latter testable by non-Gaussianities. Particle production, even of massive fields, can enter into the power spectrum. There's a huge amount of phenomenology here. So if I'm still okay on time, let me elaborate a little bit more on axion physics. This has been of interest by many people for many reasons. One is that if we do the special case where there are light axions, for example, Calabi-Yau models, which are very beautiful in themselves, one can obtain light axions, which could lead to black hole superradiance and other effects. I already mentioned the axion as an inflaton when we consider more generic situations. So to me, it's intriguing that axions dominate the string spectrum in this at least in this large D limit. So in some sense, you know, string theory is a high positive potential energy theory of axions. I want to stress generically there's no saxion, so effects to do with it are not universal, despite some claims to that effect. And again, this flux effect is pretty generic. Okay, so this flattening of the potential effect goes this way in the famous plot of the tilt of the power spectrum and the tensor to scalar ratio, while multi-field effects, like by Demopoulos et al., for a given single field model, head that way. And so this is one of those things where we can abstract a lesson from all our work on specific models and find some interesting phenomenological trend to predict. Okay, no one should overstate this. I would not say that although m squared phi squared is often removed by this flattening effect, I wouldn't say it's impossible. That would be a too strong and irresponsible statement. But I'm saying that there are patterns that we see, and this is an example. Okay. So another aspect of the physics that I find interesting these days, so Daniel reviewed the beautiful work on what are called cosmological correlators with sort of symmetries that help us give elegant formulas for those. In its full glory, the non-Gaussianity is this functional, this probability distribution function for the whole quantum field theory, psi squared. And we've found by some explorations, and the most recent work on this is a beautiful non-perturbative calculation by Cremonelli et al., that these non-perturbative effects related to the tail of the distribution can be significantly non-Gaussian themselves, and maybe this gives us some novel observational probes. The thing I really want to leave you with is this: the connection between string theory and cosmology is not all or nothing, okay? It's not that a connection requires a universal prediction of string theory, which is not justified. Deriving the mass of the electron, that was, early on, that seemed like it might be in the cards. And of course, people quickly revised their view based on the evidence. Any statement, for example, about R being detectable or not, being favored or unfavored, is not reliable. On the other hand, this idea that people say anything goes is a straw man. I've never, that's also not the way it goes. Instead, as it so often is, the truth is in the middle. So the landscape is rich, but it's highly structured. We do have these really interesting empirical tests and discriminations that are ongoing. But these are model dependent. They're also dependent on your choice of wave function. If we can make progress on somehow restricting that, that would be useful. And regardless of all that, also, when we work toward a real full framework for quantum gravity, given the observation of positive cosmological constant, we can think about that as a data-driven question. Okay, so I have comments that I could make on the more conceptual side of the subject. My favorite approach is this one where we have radial emergence using all the insights from the TT bar deformation and so on. There are other approaches and developments, including those in recent black hole physics studies using just semi-classical Euclidean quantum gravity. There are no doubt connections among the different approaches and many, many questions. I have some slides on that, but I think we should just go to the discussion. Okay, so Daniel and I put together, maybe I can make this a little bigger. Does that still work? So we put together a bunch of questions kind of organized by being more observational or more conceptual. In our defense, I mean, this is a busy plot. In our defense, we were handed the entire universe to compress into a discussion session. So we did our best. And I guess we kind of had a tentative hope of starting from the more observational phenomenological side if people have questions or comments about that, and then moving more toward the conceptual side. But, at this point, it can be a free for all. So.
Thank you very much. Let's thank Eva and Daniel for a beautiful introduction. Yeah, so I think that sounds like an excellent plan to stick with this observational, phenomenological, and conceptual flow. But of course, please help me then in identifying people to call, because I will not know all the names in the field. As I said, I will be calling people mostly by the order people raise their hands, except if you wave. Please turn on your camera. It's much more fun that we can see each other. So if you wave, then we can call you, because then it means that the topic you want to ask about is what is being discussed right now. So we will call you. And of course, the priority is for Eva and Daniel to call upon people. Yeah, go
yeah. I'm really sorry to interrupt you, Pedro. Should I leave this slide of questions up or should I not? Let me just Just let me know.
I mean, normally what I do is I put side by side gallery and slide, and I make the slide small and gallery big. I assume everyone knows how to do it. So I think
okay, good. So I'll leave it up for those who want it. That's all I meant.
Yeah. If people think otherwise, please say so. But yeah, so as I said, please leave your camera on, especially if you are participating in the discussion and if you want to ask questions. And so let me start with Shaheen Jabari. Yeah.
Okay, and thank you, Daniel and Eva, for the very interesting summary. I just wanted to make a comment on the Hubble tension. Basically, there are many other determinations of H0 other than the shoes and the supernovae that was mentioned. And all of them are giving us H0 above 70. So it's not, the Hubble tension is not just between shoes and Planck. It's much more than that. And still, there could be a possibility that this is down to systematics, but given that there are many different observations, all leading to this same tension, it's not very likely. And then the other comment I wanted to make is that actually we and many others have tried many different possible resolutions, resorting to different dark energy models, early, late, and many different possibilities. But what we have shown in two recent papers is that actually, if we consider CMB plus BAO plus supernovae, and very difficult within FRW cosmology to get H0 above 71. So then maybe the Hubble tension is not going to, it's not just showing something beyond lambda CDM, but showing the rate that out of FRW cosmology. So that would be a very, very interesting outcome. We are still in the middle of this, and I hope that we can clear this out. Thank you.
Well, I think
Okay,
Daniel
yeah,
should. I think Daniel should mainly answer this, but there was large scale structure studies that went in the direction of CMB with independent data, and I think Daniel should comment on that or whatever.
Mm-hmm.
Sure. Well, I comment very briefly because I didn't want this to devolve too much into a discussion on this kind of messy topic. But so first of all, I agree with you that there are other measurements of the Hubble constant. I mean, the reason I was picking this supernova result was kind of twofold. One, because I wanted to keep it simple for this short presentation. And the other one is that I would still claim that this supernova result has been scrutinized the most. And it has the smallest error bars. So if there's a single late time measurement that you would like to pick and you know, maybe at this point it's being trusted, there are other measurements, but they haven't been kind of scrutinized as much. And so yeah, I just didn't want to get into that discussion. Yeah, what Eva was mentioning is that there are independent ways of trying to constrain the Hubble constant using baryon acoustic oscillation measurements combined with late time measurements of the matter power spectrum and BBN measurements that don't use the CMB at all. And so that's an interesting consistency check. That's not completely late universe. So it's a bit debatable whether that's an early or late universe measurement, but it's definitely, it's independent of the CMB. So it proves that there's not just some big error in the CMB. So what's going on is something more subtle. But maybe I'll leave it here because this would be a whole discussion on its own, I think. And we have lots of other questions.
No one is waving, so I assume we can move to Ivano.
Yes, hi, thank you. I wanted to ask, any comments about brainwave cosmologies? Since I've mostly heard about compactifications and such. And I'm asking because these have been recently reconsidered by, for instance, the work of Ulf Danielsson and collaborators, where you have essentially a non-supersymmetric ADS that decays, and the brains that nucleate host a brainwave cosmology on them. So I was wondering Any thoughts about these kinds of settings for cosmology?
So are you getting localized gravity in the sense of Karch and Randall there? Is that the idea?
Yeah, essentially, yeah. Something like that. It's a bit different because the brain lives in an EDS, so there is an asymmetry between the outside and the inside. But the scenario is qualitatively similar, I would say.
Yeah, I mean, the usual issue is, first of all, whether you get localized gravity in the first place and so on, but
there seems to be at least at large scales on the brain. But yeah, I was wondering if you had any thoughts about this in general.
Maybe we can discuss on Slack, because I guess we would have to check out the paper.
Oh, okay.
And then maybe
thank you.
Since not everybody has maybe seen it.
Okay.
Mark van Ramstonk is raising a hand, and I thought he had an interesting paper.
Oh. Okay. Yeah.
You're muted, Mark.
Sure, okay. Yeah, I was just going to mention. I mean, I think I'm not sure if this goes towards realistic cosmology or just sort of possible models that we can explore. But I think the study of ADS CFT with boundaries seems to be a route to at least realize some of these Karch-Randall models microscopically in string theory. And so you can look at this. I had a recent paper called Cosmology from Confinement, so yeah, I think it's maybe an interesting direction to explore, but I think it's not necessarily something that will immediately lead to phenomenologically realistic models.
Yeah, I mean, I can reply to that. I know your papers are very nice, very, very interesting approach. If you're asking for a comment, I mean, I would just say there you're using bulk reconstruction for this region that is cosmological, right? And so one thing that's true of all the holographic approaches, and this is just the right physics, is that you never quite get around the fact that its gravity fluctuates, at least in the region that you're interested in. So I would say that in your case, you have the asymptotic ADS boundary, but the region you're trying to focus on is, some finite region. So there'll be the usual uncertainties in bulk reconstruction for any finite region. But still, it's interesting because your setup is still UV complete to begin with overall. It's just that in isolating the cosmological region, there will be some irreducible uncertainties, which is not a criticism. It's true of any of the approaches to holography and cosmology, where like in DSCFT you integrate over gravity, and DSDS you integrate over gravity. It's lower dimensional, it's easier, but
yeah, I think it's interesting to understand those conceptual puzzles.
Aaron?
Hello, thanks for the talks. So I wanted to bring up the topic of the field ranges in inflation, trans-Planckian field ranges, because I think it's very important, because I think it's one of the probably closest kind of predictions that string theory could make for experiments. And Eva mentioned in her talk that there are well understood controlled models with, let's say, 10 Planck excursions. And I wanted to ask two questions in a sense, in a challenge to that statement. The first question is, since the discussion is perhaps about whether you can have 1 Planck or 3 Planck or 10 Planck excursions, then how is it that in these models where it looks like in some kind of KTLT scenario, you're balancing terms a little bit not so precisely, how do you know all the order 1 factors so precisely to be able to discriminate between 10 M Planck and, let's say, 5 M Planck, if there was a factor of 2 missing somewhere? Let me just make the second question, which is related to it. The second question, which is related to it, is that in supersymmetric cases where we can calculate things extremely precisely, so there are studies in Calabi-Yars which calculate excursions to a percent level, how far you can go, then we can see that very precisely there are no super-Planckian excursions before exponentially light states appear. So if that's the case, why is it that in where we can calculate things precisely, there are no super-Planckian excursions without light states? What is the meaning of those results? So that's the two questions. Yeah.
Great. Let's go with the first one first. Okay. So I had a chance in my little presentation to set up the stage for this, right? So the source of the potential is this flux, generalized flux squared term. What I'm saying is that in the models that are explained in the Powers of Monodromy paper by McAllister et al., one can calculate which is based on a kind of compactification rather like the one that Torroba talked about today, in that case, a product of Riemann surfaces. You have this flux-supported monodromy potential. It gives a reincarnation of the phi to the 2/3 model. In that model, as I said, the flux squared term itself is a part of the usual moduli stabilization potential, and so it depends on the radii. And so as it changes, as this flux squared term changes, indeed, the size of the cycle that the flux threads changes. Okay, you can calculate how it changes. You can calculate the leading effect there very, very explicitly. So there the answer is you get a whopping factor of 10 to the 1/6, not 10 to the 6, 10 to the 1/6. So basically order 1 rescaling of the KK masses in this range. It's really not surprising if you delve into the details of the models. The comment about supersymmetry, I'll be very glad to address because, I have a different view of it. I don't think that these studies.
So let me just, before you move on. So in your model, is it exactly 10 or is it 10.5 or is it 9.5?
Oh, I'm saying it's easy. If you put it's since it only changed by this 10 to the 1/6 over 10 Planck ranges, it's not very sensitive to that. It's not that you stop at 10. It's not that it's, about to fall over the edge. As Westphal and I found originally, the thing that stops it is when you hit the scale of the moduli stabilization barriers. By the way, one pattern that let me continue. Let me continue. One pattern that we saw early on, indeed, is that these are simpler in the examples with higher scale of supersymmetry breaking. The original model, however, in a Calabi-Yau, we also studied the effect of the charge buildup as you do the monodromy. This was reanalyzed by Flauger et al., and it also fits. Okay, so I think it's really irresponsible to imply that there's some kind of grand prediction out of string theory based on studies that are so limited as to be inapplicable to the problem. I don't agree that studying how as you go out toward weak coupling into supersymmetric moduli space, you don't see that effect. That is true. And it's a very interesting and beautiful thing about string theory that in fact, modes come down exponentially as you go out in those limits. That is fine. It's interesting in itself. It should not be misapplied to make some grand statement about R in cosmology. And when it comes to, do we need supersymmetry for control? Is everything without supersymmetry somehow suspect? Think about all physics that's ever been done. Okay, just all of it. Somehow we get by without needing supersymmetric control. And why is that? Is because we have methods like perturbation theory, we have lattice methods, we have mathematical theorems, we have numerical work. Supersymmetry, extended supersymmetry in particular, is brilliant at allowing us to interpolate from weak coupling to strong coupling. That's where it was used to best effect in the theory. So it's a wonderful thing when you have it, but it's not relevant for phenomenological studies, which are really more about much more pedestrian methods, perturbation theory, basically. So yes, thank you for the question. And I was
so what is the meaning that you can't get 3M Planck in supersymmetric?
Maybe let's at some point also give room for the other people to ask also some questions.
All right,
and we can come back. There's no problem. But I wonder if the question by Juan in the chat, if it's related or not. Sorry for my ignorance, but Juan is also making a comment about trans-Planckian field ranges. I don't know if it would make sense to fit in now or if we should move to Qumran.
I think it's covered. I think that's covered. are not the same.
It's
Maybe I can make a comment. Can I make a comment about the transbranchial field ranges before moving on? Yeah, sure. So it's related also to Eran's and what Juan put in the chat. I think at the moment, precisely because at least eventually we're going to hit these infinite towers of the states, one of the nice things that we have realized is that there is an upper bound for the tensor to scalar ratio. I mean, we can discuss what it is exactly, but one of the nice things about, I don't know, at least for me, is that string theory seems to give an upper bound on the tensor to scalar ratio, which is not obvious at all. And it's something I think we should remark more. And of course, now the hard part is try to determine exactly this bound in a sharp way so we can really use it for cosmology. And then, yeah, of course, then we have all the debates of, okay, now we have sharp bounds for originally supersymmetric compactifications, like in Calabi-Yau and so on, which I think is already amazing because some years ago we didn't have that. And I agree with you that the next step is to go then now to other setups and try to get also sharp bounds there and see what we get. But I think, yeah, I don't know, I think it's an interesting topic to keep in mind that there is an upper bound and we have to find it. And also, I would love to ask also, like, I mean, there is a chance that these towers of states are not so far in energies. I mean, maybe we can still have 5M Planck, I don't know, I mean, like we can have some large field inflation that is consistent with experiments, but it could be that the towers are not so far away. And I wonder also if it wouldn't be nice also to understand better what is the effect in the cosmological observables. Can we give universal predictions in terms of the non-Gaussianities or things like that about having towers of states that are becoming light when the field range increases? No, I mean, I don't know. I think that would be something nice to know what is the answer, no, before all these experiments come in the next years.
So I think all that is great, but let me just say that you know, in any UV completion, regardless of string theory, you would expect an upper bound on R simply because you hit the high scale of you know, of the theory. You hit the cutoff. You're never going to go arbitrarily high, and the question is, okay, where is the first time you hit the high scale? Regarding, I do think you have to keep in mind that these examples are controlled by an approximate symmetry, much like the original m squared phi squared of Linde. So the idea that there's, you know, something right around the corner, it would be great if, as you say, it were true, but or I don't know, great, or we shouldn't put value judgments. But I don't personally find that very likely. Not you know, not to be a downer on the idea. You're right that there would be phenomenological implications of being, you know, right on the edge of inflating. But the way these models work, they're controlled in a standard Wilsonian sense by a shift symmetry. Regarding what Juan said, I think, as Daniel said, everybody agrees that it's an important question. The thing I would caution, though, is I think it would be really irresponsible to prematurely declare that the theory prefers one or the other thing. I think that is not the case very clearly from what we understand now. If there's some, you know, enormous surprise in which one can exclude one of the two possibilities, that would be super interesting. With this all or nothing comment that we tried to stress, it's interesting either way. We will get a discrimination about whether or not this sort of large field matter model did happen in the early universe. And that's, you know, we don't have to be more greedy than that. That's already quite interesting.
Maybe I can make a quick comment about.
Yeah, well, officially we have about 10 minutes. So please remember there is another session afterwards as well. So
I'll be very quick. No, actually, I just wanted to reinforce. I agree with the last thing that Irene said about it would be nice to kind of make statements about other observables. And in fact, to always keep in mind that we measure correlation functions. It's like in particle physics, we measure the S matrix. And so statements, you know, like in the bootstrap sense that we can make about the S matrix are very, or in this case now cosmological correlators are very valuable because those are in one-to-one correspondence to what we actually observe. Rather than statements just about the background, we actually never observing the background during the de Sitter phase directly. And so it's maybe just something to keep in mind also that those are our main observables, and making statements about those would be nice.
Kumram?
I guess Kumram, yeah.
Yes, thank you. So what I want to say is just a comment, not a question. So
related to distance conjecture, but applied differently, and namely to our universe going backwards in time. Just imagine that we had discovered that our universe, the current universe, was not expanding, but was contracting. So I'm not talking time reversal, but actually just imagine that our universe was contracting. What would we have predicted for the fate of that universe? Well, we would have said the temperature is going to go up, up, up. That's natural from, from the Big Bang cosmology reverse. And then you would ask, okay, what's going to happen when the temperature gets very large up? From what we know from string theory, in almost all the examples, when you go to extreme conditions, you get a dual description. The original description has to break down. High temperature is dual in the Euclidean language to a small circle, so we know that something is going to come, making it light. Now, we don't have a proof of that, of course, but it's very natural. Whether you want to say it's exponential or whatnot is secondary, I would say. So from all we know from string theory, we expect the dual description to take over, meaning many, many light states should come in. It shouldn't be just one inflaton field, for example, taking over. We would expect something dramatic to happen. To ignore that lesson we have learned in all of this string theory is not doing favor to us. We have learned that. That's a major lesson we have learned. We want to ignore that lesson at our own peril. So I think the general idea of what happens in early universe and what new degrees of freedom take over is crucial. To try to find a solution with conventional techniques might be true, might just add one field or something, despite all the issues that already we are discussing about distance and all that. But it's also natural, given that we are string theorists, to look like solutions which are natural in string theory, like emergence of the space, like ideas that are not driven by those ideas. For example, one such idea we were exploring in a recent paper with Agrawal, Gukov, and Obeid, where we had the description of a space emerging similar to T-duality, but where the space that is emerging in our language of our space is described by a topological gravity, and the toy model we studied was the model given by Witten's 4D topological gravity. So ideas that relate emergence with topological ideas could naturally lead to, for example, things which would be like scale invariance or homogeneity or horizon issue, which look topological, which look like position independence. So many new ideas could be there. I think, to be honest, I don't think as a string community we have been imaginative enough. Thank you.
I think it's a great idea to study alternatives to inflation. There are many ideas, and it's hard. It's hard, but it's. I agree with you. It's worthwhile.
Mark?
Yeah, I just had a general naive question about cosmology and or kind of getting, the question is whether in top-down constructions, is it easier to, so we can imagine sort of stabilized de Sitter with a constant amount of dark energy versus models where you have some kind of rolling or changing dark energy. And I'm just wondering, from top-down constructions, I mean, is it sort of easier to do completely stabilized, or is it similar for either one?
Yeah, I would like to, I'm sorry if I'm talking too much, but I'd like to take this because it's one point of intersection between the kind of the two camps on this, in my view. So, you know, I don't have doubts about particularly serious doubts about the de Sitter constructions, but that doesn't mean that, I mean, as Mark is stressing, nonetheless, you can ask, what does it typically want to do? Does it typically roll, or is it typically in one of those vacua? Of course, that ultimately brings in measure questions, but never mind. So it's, you know, it's a stronger condition to impose v prime equals 0 than it is to just impose accelerated expansion. So, you know, I would agree that from that point of view, which may not be the right measure, but from that point of view, it is true that it's more generic in that sense to find the rolling case. Now, we can be very explicit about this. So this thing about the generalized fluxes squared illustrates that. So in any flux stabilization model where the fluxes would normally be participating at order 1 in the stabilization mechanism, if those are replaced with topology and so on going on, if those are replaced by instead this Stuckelberg-like thing where you have the Q1 plus axion Q2 squared kind of structure to it, well, then you're doing this large field inflationary evolution instead, so I actually wouldn't be surprised if that is generic. There are many papers in this subject. We had papers with Shidong and company showing many examples like that, where these generalized fluxes were essential to the stabilization of the moduli, and they were generalized so the axion was rolling. So I'm with you on that, and this is a point of intersection with folks who prefer non-zero V prime, so I wanted to stress it.
Okay, thanks.
Fernando?
Yes. Okay, thank you. Well, let me bring the discussion a little bit down. So just trying to address a couple of the points that you mentioned in the questions, the observational part and the phenomenological part. You say that what are important effects for the UV completion, and I think it's very good that you concentrated on inflation and high energies and so. But usually we say that inflation is very bad in the sense that it erases everything that happened before. And so in that sense, it kills the possibility of seeing any, it dilutes everything else. So it may have a problem for you to see anything about the string scale states or something. However, at least something that survives are in the supersymmetric compactifications are the moduli. So the moduli survive at low energies, and then they may have a lot of implications at energies much lower than the inflationary scale. And for instance, after inflation finishes, the moduli still are not stabilized in the minimum, so they can actually reheating happens when the lightest modulus decay. So it's a different picture than what we had with just reheating saying that it's inflation that give you the reheating. And so that will also give you a period where the moduli dominate the energy density of the universe, so that it changes also that part of the history of the universe, not just going from inflation to radiation domination, but from inflation to matter domination and then radiation. And it may even have some interesting implications, like gravitational waves. So when that happens, you can have inhomogeneities like oscillons, and that will produce gravitational waves. And I find that fascinating because something I realized by working on this is that usually the frequency of gravitational waves that you produce is essentially proportional to the energy that were the source created. So and you want some energy of the order of the GOT scale, 10 to the 16 GeV or so, it will give you frequencies of the order of the gigahertz, or anything between megahertz and gigahertz will cover you from TeV to the GOT scale. And so I find it fascinating that this range of frequency for gravitational waves has not been explored at all, or almost not at all. Very few people are doing it, and it's not in the plans because people go from LIGO to LISA, which is smaller frequencies. So I just wanted to advertise that we have have a working group on this, and we have a workshop. We had a workshop 2 years ago, and we're organizing a workshop in the next 2 or 3 months, and that will be a beautiful possibility, not in the next 5 or 10 years, but in the long term, that we can actually put to test some things about the string theory. For instance, you can even think about dreaming about the so here in the shape of the extra dimensions, something like that. And they said that moduli decays will give you some pictures about that can be observable eventually. So I think that's another aspect of string cosmology that is probably lower energies that but may have an interesting observational future. And now let me finish with the question. That happens in supersymmetric models, because the moduli survive after, they're flat because of supersymmetry, and then they get a mass relatively small compared to the string scale. So to Eva, what happens in your models, which are non-supersymmetric? Do you have the corresponding moduli are relatively light or not?
Well, I mean, generically, they're not. Generically, you'd have all these fluxes turned on. Generically, you have negative curvature and hence all these rigidity properties of the manifold that Torroba mentioned. But I think, I think there are generally two questions of this kind. What is generic, and what are the interesting model dependent possibilities? And it seems to me that what you're describing is an interesting model dependent possibility. And I think what you're getting at is, could it be that if we saw evidence for that, it would be some sort of indirect evidence for low energy supersymmetry? That would be super interesting if one could make such a statement. So yeah, if there's some motion there, one could go back to the less supersymmetric models and see what happens if you try and keep things light. But it's things are even at tree level typically driven up. But I thought that there was a lot of study of trying to see gravitational wave signatures from things like oscillons, like Mustafa Amin and so on. And it is a great question, but it was hard. I mean, it was not obviously a high enough signal, but if you're getting more optimistic answers, that's fantastic.
Yes. No, and this, don't get me wrong, this is not, I mean, this is just like an example where this can happen, but any physics beyond the standard model, there are no competing standard model effects for frequency beyond the kilohertz to the megahertz, to the gigahertz. So anything you will see there, essentially, it will be new physics, and most of it will be cosmological. And so oscillons is a particular case, but anything that you can think of coming from string theory or any physics beyond the standard model, that's a way that that's a way to test it, to put it in test. So in that sense, it's far beyond just talking about oscillons or something. It's just any energies, any new effects, cosmological, like preheating, reheating, phase transitions. All of these things happen and at higher energies, and they will give you naturally higher frequencies. And the range is very well defined too, from megahertz to gigahertz, which I find fascinating. Yeah.
Thank you. I have a suggestion. So I think in 10 minutes, we have to test the screen sharing for the next session, but we could continue for a few more minutes informally. But as usual, let's close the official discussion and thank very much Daniel and Eva and everyone. And yeah, people are welcome to please continue a little bit more, not much more, because as I said, we have to test the screen sharing for the next session. But yeah, thanks again. So we could go on with Samir.
It's a question for Daniel, if he's still there.
I'm here, yeah.
So I've been playing a little bit with whatever we've learned from black holes might imply for cosmology, and it's really very primitive, but it seemed that there could be some extra source of vacuum energy when the expansion power law changes from, let's say, T to the half to T to the 2/3. And then I looked at some papers which were suggesting that if you have roughly 10% extra energy at around the time of matter radiation equality, that could resolve the Hubble tension. Is that true? And is that all that's needed to resolve the tension?
Sorry, so I think the one rough statement that I sometimes hear is that you need to inject energy. Yeah, it's true. You have to inject energy right around the time of matter radiation equality, which is an interesting coincidence, which has some people led to construct models where somehow the change from radiation to matter acts like a switch, but then turns on some early dark energy that does its thing. So it is a very specific moment in time at which this energy injection or whatever's happening has to occur. If it happens before, it just kind of gets absorbed in thermal equilibrium and it doesn't do much. And it happens too late, then it doesn't have enough effect. So somehow the main effect has to occur right around matter radiation equality. So that is true. But the devil is really in the details. Like, it's easy to convince yourself that like some, that a basic effect is happening and that will change the sound horizon in the way you want it to. But the CMB has been measured extremely precisely at sub% level. And to not change anything of that success at sub% is just hard. And it's often hard to see with pen and paper. One actually has to run the full analysis to actually see what goes wrong and whether the fit improves or doesn't improve and so on. So it's a quite a tricky question.
Thank you.
To add another word about this, I think the problem is that you need to inject this energy, but it has to disappear amazingly fast.
Yeah, that's right.
So you can make various simple mechanisms using conventional physics. You need to assume a new field or something, but they're conventional mechanisms. For example, you can have a field that starts oscillating at just a given moment, but then it has to stop oscillating incredibly fast, faster than you would get from conventional physics without fine tuning. So what you sounds simple, but in detail is actually amazing hard.
Yeah, that's true.
And maybe if I can add a point on that, the CMB is measured so well that it's really hard to do things like this. So we already have bounds of 10 to the minus 6 on any deviation from a black body. If you have any injection of energy that the photons know about, even a little bit, you are completely ruled out by 6 orders of magnitude. So the photons have to be completely isolated by this and anything talking to the photons, otherwise you're screwed. Then we know very precisely what are the tails of the CMB that really measure what is the free streaming of photons. And free streaming goes like the square root of the number of scattering, which grows with time. If you shorten that time, you change how much the tails of the CMB are suppressed. And then the third thing that I wanted to say is that we measure quite well the early integrated Sachs-Wolf effect in the low L of the CMB, and people look at that, and there is no sign whatsoever that the potential changes in a way different from the standard radiation domination to matter domination. So anything that you try to do, changing just the expansion rate, is going to affect all of these 3 variables that are all measured to either 10 to the minus 6 or the percent level, and you're trying to get through with a 10% changes. It looks really, really bad. So people are trying this, but it's really hard. There are way too many obstacles.
Actually, just one quick correction. I mean, the early integrated Sachs-Wolf effect actually affects the first peak, which is even worse because the first peak we have measured so accurately. It's the late Sachs-Wolf that affects the low L, but early integrated Sachs-Wolf is actually the first peak, and that height of the first peak has been normalized so precisely that it's really hard to do anything with it. That changes that. But there's lots of things people have played with, and for example, you could imagine that recombination happens faster than you thought, which will also reduce the sound horizon because it just means that recombination happened at a slightly earlier conformal time, and so the sound wave didn't propagate as far just because it got kind of decoupling happened earlier. But always the question is, how do you implement it? What type of physics do you add in order to make this happen, and how does that affect the rest of the CMB? And so it's a super well-defined problem with no solution so far.
There's one more question.
Harvard note has,
yeah. Can I make a quick comment? Yeah. So related to the question of what lessons can we get from certain corners of the string landscape and apply them to cosmology or to models where we don't really know how to do stuff. There's one thing that seems to be true in every example. It's certainly true in every example that I know of, and you can even justify it in some corners. And it doesn't have to do with supersymmetry really, which is the idea that black holes have to decay. If you have an extremal black hole that is not protected by supersymmetry, it always decays, and that's the motivation behind the Grigory conjecture. So principles like that, if you take them seriously, they really lead to universal predictions on properties of the spectrum of the theory, like the Grigory conjecture. And for instance, you could imagine a situation like you have like positive vacuum energy and apply it to a black hole with which is very big, like an area black hole, as big as the horizon size. And then you actually get constraints on the spectrum. So this is something that we worked on in a paper with Thomas van Riet and Gerben, and we had a follow-up recently with Kumrum as well. So you get things like a lower bound on the mass of charged states. So that's interesting already for particle physics in the present universe. But it's actually particularly interesting in the context of inflation because there has to be an interplay. It basically puts constraints on the matter fields and the quantum fields that you might have during inflation to satisfy this kind of bounds. So actually, I just wanted to basically ask Eva about what do you think about like principles like like the principle behind the Grigory conjecture, black hole decay? Do you think that's something that could be general? Because the evidence that we have for that is certainly non-supersymmetric, almost by construction.
Yeah, I mean, among all of these conjectures, I think the weak gravity one is the most clear. And I mean, I don't really understand the logic behind it. I don't think anybody, including the authors, claimed it was some sort of derivation. But the fact that it lines up with things like cosmic censorship, I mean, maybe George Santos, if he's still here, could speak to that. I think that, there's an interesting story there that might well be true. But since I didn't really understand, I mean, if you have a black hole, there's no conserved charge or something. There's no reason that it shouldn't decay. I'm not sure. Maybe I'm behind, but I'm not sure there's a principle needed per se about that. Maybe I realize it has to do with pair production and how light the fields are and that sort of stuff.
Right. It's not automatic, but
Yeah, I don't know. I don't think anybody really knows. I think it's intriguing how those ideas do overlap with cosmic censorship ideas. These are both conjectures, but that is intriguing. But I think again, with all things, and even in like the primordial cosmology community, my role has been adding adjectives, making sure people don't overstate. No, single field inflation is not necessarily slow roll. Yes, I even though I'm always taking this view, I think it is the conservative view. So I'm not sure that there's really a principle there, but it's an interesting thing to explore. It's an interesting pattern.
Right. Like if there's really a principle, if it's really justified, it's something that it becomes quite powerful. It can concern effective field theories, even in cases where we don't have a full top-down approach.
Okay, yeah, but one thing that I do think is super important and should go without saying, but it is, look at what is known, even if it's not, this year's news or whatever, to make sure what you're saying is consistent. And if there's, and I think there's that, when it comes to these things, the control that we have is really the more pedestrian, perturbation theory around weak curvature, weak coupling. If some proposed principle contradicts that, it's not that the proposed principle takes precedence. When the control, we're talking about, in other words, that is more uncertain than, what are the contributions to the background and what is the solution and so on. So that's how these things should be, in my view, that's how these things should be addressed, is just through the nuts and bolts of it.
Right.
I would suggest we close with a question from the chat from Sayatan that did such an amazing job yesterday with the Gong Show questions. And he's asking Daniel and Eva about what you think about the asymmetric bootstrap helping cosmology research.
I think Daniel should take this one if he's still here, because it's his.
Yeah. Maybe I take it because I had a slide on it, but I rushed through it. Well, I'm biased. I find it very interesting. And what I think is interesting is actually that, we could try applying a similar bootstrap philosophy to cosmology, but the rules are slightly, less well defined as of yet. So, usually the bootstrap is kind of a combination of two things. It's a statement of principles and then trying to implement like locality, Lorentz symmetry, and causality and unitarity and so on, and then trying to see what those principles imply for observables. Yeah. And so in flat space, we kind of understand the principles very well, and we sort of understand how to implement them order by order in perturbation theory. In ADS-CFT, we understand the principles completely, and we understand how to implement them non-perturbatively. That's why I had this axis of understanding. And it's somewhat embarrassing that when the closer we get to the real world, the less we understand both of these things, that we don't understand the full set of principles. And even in cases where we do think we know what the principle is, we don't understand non-perturbatively how to even implement them. And so, which I think is interesting. It's a good challenge to kind of trying to transfer kind of this bootstrap philosophy to the cosmological gravitational space-time backgrounds. And it's a back and forth of like trying to determine what are the rules that we should be imposing on our observables, and how do we impose them, and then go back and forth. Yeah.
Thank you. And by the way, I remind people there is a Slack channel, so this would be a very nice topic to explore further there. And there is already a channel about asymmetric bootstrap, and there is now a channel about cosmology. So feel free to go to one of these two and continue there. And let's thank very much once again Daniel and Eva, and test the share screening for the next session. Thank you. So Nathan, I'll let you take over, and I will try to quickly eat a little bit.
Okay, I don't know if we handled all the chat questions yet, but that's okay, I guess.
Nathan, can we practice sharing at this point?
Sorry, I was muted. I didn't notice. Yeah, Shamit, do you want to try yours now?
Sure. And by the way, is my connection good? Can you hear me and everything?
Everything is perfect right now.
That's the most you can ask for. Okay, let me try to share. Let's see. Okay, do you see a screen that says de Sitter space and string theory?
Yep, looks perfect to me. You want to just change a slide, make sure that's right.
Sure. Sorry, hold on. How's that?
Yep, very good. Okay, we can go. Grisha, do you want to try yours now? Very good. Perfect. Fernando?
Yes, okay. It's okay?
Yep, looks good.
Good.
Okay, so we're all set. Subir, you want to combine with Grisha about timing, however you want to do it. It's fine.
Okay, I presume it's 25 plus 5, right? Is that the normal?
Yep.
Yeah, okay.
Yeah, I don't know if he wants a 5-minute warning.
All right, I'll do that.
Subir.
Hi, Fernando. How are you?
Good to see you. Yes.
Hi, strange to see you without a ICTP affiliation.
Yeah, more relaxed. Yeah.
Hi, Roger.
Hi, Subir.
Oh, how is he? Yeah.
There's Grisha.
I was very impressed by Shamit's background, which disappeared.
So are you in your office, Grisha, in Carnegie Mellon?
Yeah.
How's life in Pittsburgh?
So far, so good.
Yeah.
And you're back in your office?
Yeah, as of a couple of weeks ago. Well, limited amounts of time, but. Okay, I think maybe Grisha, you can put your slides up. So Fernando, is the US going to go in the green zone and the UK soon? I can't hear you.
I can see, yes, I don't know. Yes, you want to come?
Yes, there's some conference next week. They said.
Oh, really?
We'll wait till the last minute and maybe you might go in the green zone, but I don't think it's happening.
Yeah. No, I think they're getting strict, which is, I mean, because the number of cases is rising.
Yeah, that's disturbing.
Yes, yes, the number of deaths is more or less stable, so that means that something is working. But there's many more cases now. Yes. So yes, we just had a kind of complicated examining session. I just had my examiners meeting today with the several hours. That because everything we did most of it. Well, we had to mark at home, of course, but some of the students came, so we had percent of the students did the exam here, percent of the students did it at home. We had to scan everything together and do everything online. Because I think we're not going to the university.
Okay, all right. Well, I think it's well 13:40 Brasilia time, so we have to start, right?
Sure.
All right, so we start this session, and the speaker is Grigory Tarnopolsky, who's now at just joined Carnegie Mellon University.
Thanks a lot. First, I would like to thank organizers for inviting me to speak at this great conference. It's an honor. My talk is based on this pre-works written with J1 team, Igor Klebanov, Ven Zhao, Alex Velyohin, Maria Tikhanovskaya, Hao Gu, and Subir Sajdev. And my short plan is first we'll give some introduction to random SYK models. Then I will talk about operators in SYK models and their effects. Finally, I will discuss coupled Majorana and complex SYK models and spontaneous symmetry breaking in this case. So we'll start with some very basic things. So if we consider just a non-relativistic Hamiltonian of interacting particles, where the first term is just Laplacian plus potential, so just single particle Hamiltonian, and there's the second term is two particle interaction and three particle interaction and so on. So if we write this non-relativistic Hamiltonian in the second quantization representation, we will get this form where now C and C dagger are creation and annihilation operators. So we assume fermions for simplicity here. And this element JKL here is just nothing but just matrix element of two particle interaction with eigenfunctions of the single particle Hamiltonian. And now if we assume that this eigenfunctions of the single particle Hamiltonian for some reason irregular or random, we can assume that this couplings, JKL couplings, they are random as well. And this way we sort of arrive to what we now call complex SYK model. But there's a problem. There's this kinetic term which comes from single particle case. And so the point here is that these models, they're not far from reality. And in fact, back in 70s, people consider a model which we now call complex SYK model, where they say that instead of taking, if we consider a nucleus, instead of taking Hamiltonian to be random matrix, full Hamiltonian to be random matrix, we just consider Hamiltonian to be two particle interacting term and with the random coupling. But they also fixed total momentum of the states. So they consider some big nucleus, outer shell of this big nucleus, fill it with 7 particles with fixed total momentum, and they just diagonalize this Hamiltonian numerically and get histogram of energy levels of this random Hamiltonian. And so here it's a reproduction of it. But at the time they concluded that it's not a Wigner semicircle. It's a Gaussian. So they say that it's not a Wigner semicircle and it's a Gaussian. But so they missed, I think the most important part is that actually at the tails of the distribution, it's not Gaussian, but it actually goes as square root of energy. It's sort of more like a Wigner semicircle. So they sort of missed the most interesting physics about the SYK model. And also I want to mention that this type of random models, they were considered in the late 90s in the context of quantum dot physics, where people consider like quantum well, and they populated with electrons. And I assume that if this quantum well has irregular boundaries, then we can think that this eigenfunctions of electrons are random, and that's why couplings, JJKL couplings are random as well. But in this model, there's the kinetic term is present, and the questions people asked is how does random interaction affect single particle term, free particle. So there's no way to get rid of this quadratic term, which spoils SYK physics. I also want to briefly mention non-random large N models, which are called tensor models, where the randomness basically replaced by additional two indices. So we can have the model which has a product of 4 Mariana fermions, where so each fermion has 3 indices, and in addition 2 additional indices. So we can call them orbital indices. And the problem of these models is that the Hilbert space grows as an n cube. But on the other hand, if we look again at this Hamiltonian as a matrix, this matrix is very sparse. So here's the picture of this tensor model matrix for 32 Mariana fermions. You see the white regions are where the matrix is 0, matrix elements is 0, and the blue regions is where they're not 0. So basically, it's almost empty. So and finally, I would like to mention again a SYK model, the basic SYK model, which already appeared in a couple of talks before. So it's a product of 4 Mariana fermions, which interact through random coupling JJKL with 0 average and variance. And the Hilbert space is 2 to the n over 2. And we can think about this model again as a big matrix. It's also quite sparse matrix here. Here's the picture of this matrix for 18 Mariana fermions. And we can proceed and diagonalize this matrix. And we'll get a histogram of energy levels, which look like this. It's actually, this is for 32 Mariana, which has 65,000 levels. And indeed, in the center, this distribution is Gaussian. But if we zoom in at the bottom, near the ground state, we will see that there are many energy levels even near the ground state. They behave like a square root of energy here. And if we zoom even more, we can see that there are high density of energy levels, exponentially high density of energy levels. So the density of energy levels is e to the S0 times n, where S0 is what is called zero temperature entropy, and it's some number which can be computed theoretically. And by this fact that there's a high number of energy levels near the ground state is related to very interesting physical properties of the SYK model, such as non-Fermi liquid behavior, emergent criticality, and so on. And if we consider in most of this random SYK-like models, this high density of energy states near the ground state is related to this emergent scale invariance, and the 2-point function of fermions behaves as a 1 over tau to the power of 1/2. And we can ask if it's a common behavior of 2-point function in all this type of random models. So, but to check this behavior theoretically, we need to analyze spectrum of 2 particle operators. And as I will show, there are models where this behavior is not really correct. And there's a phenomenon of spontaneous symmetry gradient. But first, let me describe how we compute 2 particle operators in this type of models. So we consider 2 particle operators of this form, where always it's just a product of 2 psi fields addressed by tau derivatives. And in the SYK, in the simple SYK model, we can only have odd time derivatives. And we consider a 3-point function of 2 Majorana fields and this operator. And for this 3-point function, we can, in large and limit, we can derive beta-salpeter equation. So we can basically address bare 3-point function with letters and resum this infinite diagrams and get a self-consistent beta-salpeter equation, which in terms of formulas can be written like this. So the 3-point function equals to kernel, which acts on this 3-point function. So it's an integral equation which defines the anomalous dimensions of this operator. And so the kernel is just some product of full 2-point functions, which we assume in infrared having this scale invariant form. Next, we assume that the 3-point function itself has a conformal form plugging it to this equation, we will reduce this integral equation to just algebraic equation which defines this anomalous dimensions. So just to recap, and we can solve this algebraic equation numerically and get anomalous dimensions of 2 particle operators. The first anomalous scaling dimension is h equals 2, and it's very special. It actually breaks conformal invariance. But there are higher anomalous dimensions which are some transcendental numbers. So the first is 3.77 and so on, and they approach n+1/2 and then goes to infinity. And so why are these operators important? They're important because they actually define physics of the SYK model and observables. And this is because we can think about SYK model as some abstract CFT action plus perturbation by this infinite series of these irrelevant operators, and where GH are couplings. And this representation is actually phenomenological. So I don't know a straightforward way to derive it, but we can check it, and it looks like it works. So these operators, they form operator algebra. They have their own OPE with structure constants and so on. And also this abstract CFT, SYK CFT is something which, if we schematically integrate 2-point function over it, we will get scale invariant, leading scale invariant form of the Green's function. But next, we can use this representation of SYK action to compute corrections to the 2-point function. So just using conformal perturbation theory. So we can expand these operators and just compute correlators. And this gives the full answer for 2-point function, which involves this scaling dimensions of operators. And we can go and actually we can check it numerically. Here the plot where the red line is a exact numerical 2-point function in a SYK model, and this dotted line is just this conformal approximation, and the dashed line is the full approximation, which involves at least these first 2 operators, the h equals 2 and h equals 3.77. And we see that the agreement is actually really good, and we can actually detect this irrational scaling exponent in this case. We can detect numerically, so it's not abstraction, but it really shapes the physical behavior of the SYK model. We can also use this representation to compute thermodynamics of the SYK model. So we can compute, for example, free energy, just using, again, conformal perturbation theory. And in this case, so the first 3 terms is ground energy, the 0 temperature entropy, which I mentioned at the beginning, and the specific heat. This alpha 0 is actually what is related to Schwarz coupling. And here, the next operator only contributes at higher power through this 2-point function. And in this case, it's really hard to observe it numerically because it's kind of hidden in very high powers of 1/beta J expansion. But the thing is a bit better and more interesting in complex SYK model, because in this model, we have additional set of operators, this H tilde, And also, among these operators, there's a special operator which is a U1 charge. In the complex SYK model, we have global U1 symmetry. There's U1 charge, which we can add to action, and this corresponds to marginal deformation of the theory. So this deformation keeps the theory conformal, but it changes scaling dimensions. So the scaling dimensions of operators, they depend on this deformation, this chemical potential mu. And also along this 2 and 3.7, there's a scaling dimension 265, which is much lower than 3.7. And this dimension will contribute to free energy of the complex SYK model at lower powers. So there may be a chance to detect this in numerics. But in both of these models, the leading operator is a H=2 operator, which actually very special. As I said, it breaks conformal invariance, and its effect is it provides leading contribution to the observables in SYK model. But now we can actually consider coupled Majorana SYK model, where we have just 2 copies of a single Majorana SYK model, which now interact through each other through the coupling alpha. And here JIJKL, just a Gaussian random, they're exactly the same as in a single SYK model. And one can show that using symmetries that this coupling alpha could be taken only in the region from -1 to 1/3, and other values of this coupling can be brought to this region by symmetry. So it's natural to assume that in this model, 2-point function of left fermions agree with the 2-point function of right fermions and equal to g of tau, and the 2-point function of psi1, psi2 is 0 because of symmetry. And if we assume this under this assumption, the g of tau, it coincides with the SYK 2-point function, which is scale invariant, and we can go along the same procedure and find anomalous dimensions to various bilinear operators in this model. And here the picture, the story is more interesting. So this is the plot of scaling dimensions as a function of coupling strength alpha here, and there are 2 important regions here. So from 0 to 1/3, what we basically observe is that the model behaves, the operators, they more or less coincide with the just a single SYK model operators, and the model behaves similar to the single SYK model. There's operator psi1, psi2, which is not generated in the effective action because it's forbidden by symmetry, but it's a relevant operator, so it's less than 1. We can add it to our Hamiltonian, and then the spectrum will be gapped, and this would correspond to a model discussed in the paper by Molbasena and Chi. On the other hand, the interesting thing happens when we go to negative alpha, when we consider a region from -1 to 0. In this case, this operator psi1, psi2, it becomes complex. And actually, the fact that it becomes complex means that this operator acquires a vacuum expectation value, and the Z2 symmetry of this model is spontaneously broken. And if we do numerics and look at the spectrum at this region, the spectrum is completely different from the single SYK model. It has this strange shape. And if we zoom in at the bottom, we will see that instead of many energy levels, we have two tiny split ground states and a gap. So this actually, for negative alpha in this model, the conformal invariant physics was a delusion, and the correct physics is different. So there's this gap, and there's basically there's no Fermi-liquid behavior, non-Fermi-liquid behavior in this model. And finally, so if we go to and we can consider coupled complex SYK model, basically following the same logic. So we take 2 copies of complex SYK model, which interact now through coupling alpha. One can think about these indices 1 and 2 as the spin-off electron, and So this model has U1 cross U1 symmetry, where we can rotate each fermion, each type of fermions by its own phase. That means that we have two conserved charges. And also at special value of decoupling, when alpha equals 1/4, this model has a U2 global symmetry and can be written, the Hamiltonian could be written in this form, where again, the sigma, there's a sum over the sigma, which can be thought as a spin of electron. We can again do the same procedure and compute a spectrum of anomalous dimensions in this model. And in this case, it's more interesting than in Mariana case. First of all, again, there's a region where everything, the conformal solution is stable. There's no complex modes. They're quadratic operators. They're relevant, and we can perturb Hamiltonian by these operators, and then the spectrum will have a gap. But if we don't do this, the effective action of this model does not only have this SYK type operators, and it basically, the physics is very similar to the physics of the complex SYK model. Also, but there's a special point, as I mentioned, alpha 1/4, where there's a U2 global symmetry. In this case, these quadratic operators, they become exactly marginal and they have dimension 1. And again, there's a two region, alpha less than 0 and alpha greater than 1, where this quadratic operators become complex. And again, the similar thing happens. It means that these operators acquire vacuum expectation value, and one of the U1 symmetry of this model is spontaneously broken, and the spectrum become gaps. And so in this model, the story is very similar to my Mariana one. So and finally,
4 more.
Sure. So I'm already at the end. So finally, I want to also mention interesting thing about this model is that in this case, if we in a region from square root of 3, 8 and less than 1, here it's a stable region. There's a special operator which looks like a twisted kinetic term, C1 dagger dt tau C1 minus C2 dagger dt tau C2, which has scaling dimension less than 3/2. So we can see that it has scaling dimension less than 3/2. And this operator is not generated in the effective action of this model because it's forbidden by symmetry. But it is possible to add this, to perturb this Hamiltonian by this, to add this operator to the effective action. And in the Hamiltonian formalism, this could be achieved by twisting commutation relations between fermions. So we can consider this model, but now C1 and C2, they have different commutation relations with this psi. It would correspond to adding to effective action this operator with the coupling psi. And if we do this, if this operator isn't the effective action, that actually changes physics quite drastically. So now this would be a much more dominant operator than h equals 2. And in this case, the leading low energy effective action is not Schwarzian action, but this non-local action, which actually was discussed first in the paper by Maldacena, Stanford, and Young, and also in paper by Alex Miller. So moreover, in this case, in this case where h equals this operator with h equals less than 3/2 is present, the thermodynamics will be completely different, and this operator will dominate the leading low temperature expansion of the free energy of this model. And in this case, I also want to mention that there's no instability, so it would be the perfectly stable model without complex modes and gapped spectrum. So just to conclude, I want to say that there's a variety of random models with similar Lorentzian physics described by conformal solution, but the operator spectrum of such models can be very different. In some models, the operator spectrum implies instability of the conformal solution and spontaneous symmetry breaking. And in some models, exists an operator with scaling dimensions, the dimension less than 3/2, which leads to the non-local infrared effective action instead of the Schwarzschild action. Okay, thank you.
Okay, thank you very much, Grisha. Very clear and interesting talk. So it's open for questions. So go ahead, Zohar.
Oh, thanks for the nice talk, Grisha. Just a small question. When you change alpha continuously and you go from a symmetry broken phase to a symmetry preserving phase, is the transition in the same universality class as in QCD, this infinite order type thing?
Transition is a function of alpha, right? So
yeah, so in QCD as a function of an F over NC, it's believed to be infinite order, as you know. The large Veneziano limit, where an F and NC are large and it's a continuous parameter.
Yeah, actually, it's a good question, but I don't know what to say about transition as a function of alpha. No, I don't.
What phase transition? It's like a system with a disordered phase and an ordered phase, and there is a transition as you change the parameter continuously. It's like a quantum phase transition. So you can ask what type of quantum phase transition is there?
Yeah, that's a good question, but as a function of alpha, I don't know. As a function of temperature, it's the second order phase transition. I mean, when you in a broken phase, there's a transition as a function of temperature, and that's I know that's sorry, yeah, that's the second order. But as a function of alpha, I don't know. Yeah.
Thanks.
Thank you for that.
Well,
yeah, I think it would mean that there are effects of order e to the -1 over square root alpha, and I thought we saw some evidence for this.
Yes.
It's a difficult region to study numerically, but I think it's likely to work.
Well, the easiest way to prove it is to find that maybe there are complex Hamiltonians, which are pseudo-conformal, like the fixed point.
Yeah. But yeah, if you look at the beta functions in the region of small alpha, that from that it would follow that it's basically BKT, right, transition.
Okay, the question by Mihailo.
So in one slide, you mentioned that, of course, if you have a double trace left-right coupling like mu psi1, psi2, then you get this Megasena-Chi traversable wormhole construction. So for the coupling that you have, basically four operator coupling like here, so do we know anything about what would be the gravity dual, also some kind of wormhole, or can we look at it that way, or hard to say?
Yeah, it's a good question. I don't know if well, I think we don't really know, but it probably will be something similar. Yeah, it's just we think it should be something similar. It's just by deforming it by a relevant operator.
Okay. Yeah.
But we didn't study like something. We didn't study it in detail.
Thanks.
Emil?
Yeah, looking at this graph on the left, it seems like there's a region of a small density of states and then it takes off. Is that some artifact of small n, or is that something real that persists in the large n limit?
You mean that there are many states here in upper, or
that there's a region below that where it seems like the number of states is order 1?
Yeah, I mean, this is because, I mean, this is more natural in quantum systems, right? So this is what is surprising in a SYK model, that near the ground state, the number of states is exponential with that. In a general quantum system, it would be proportional to n. So here, that's what we would see in a
right. So
something which is standard.
Do those states have some sort of quasi-particle interpretation?
Yes, exactly. So yeah, the point is here that in this model we sort of break, when alpha is negative, we break SYK physics. Even when it looks sort of similar, it's also random and quartic. But with negative alpha, the SYK physics is broken. yeah.
I mean, another way to say it is that you just factorize the quartic term and you generate a quadratic term, and that gives you quasi-particle-like behavior.
Right, exactly. So yeah, because of this, this basically condenses this operator condenses. You can sort of say that now you get quadratic.
Okay.
Hamiltonian.
Thank you.
What?
Yeah. So in the model we had with Chi, even though we had a gap, there was still the SL2 symmetry was present and was acting in an interesting way on the spectrum. So the spectrum was governed by the SL2 symmetry. I was just wondering whether the same is true in your model.
I mean, is your SL2 symmetry exact for all values of mu, or just for small mu?
It's for small mu, and it's approximate. Yeah.
Yeah, that's guess. Yeah, I mean, it's a good question, but yeah, I don't know the answer. I guess at high energy, at high temperatures, it behaves as a usual SYK, so that there's a SL2 symmetry. But at low energies, yeah, I don't know.
Right. Thank you.
Yeah, I mean, I would guess it's there too at small, when the gap is small. Yeah. Any other questions? All right, I think we're out of time anyway. So there's a couple of questions in the chat. Yeah, I think since we're out of time, we have to move on. So thank you very much, Grisha, and I turn it over to the next discussion session.
Yeah, thank you very much. And yeah, once again, thank you very much for always being on time today. It's really amazing. So without further ado, I think everyone knows the rules by now. I'll pass it over to Fernando and Shamit that will tell us how to construct the sitter.
All right, thank you very much, Pedro. I hope you guys can hear me. If not, somebody send me a message. So I'd like to thank the organizers for giving us the opportunity to address the subject. And I hope next time we can actually be in Brazil. I've been there before. I'd love to go again. So with no further ado, I'm going to share my screen and then go through, a few minutes of slides. Then Fernando will do the same. I think we're going to be complementary. And after that, it'll be thrown open to discussion. So we were charged with discussing sort of de Sitter constructions in string theory, and I took the liberty of slightly broadening the title. And why would you talk about de Sitter space in string theory? Well, since 1998, if not before that, you need very little excuse. The subject is well motivated and has just been increasingly well motivated by data. The plot I have there symbolically is the latest DES data release. An Occam's razor interpretation of the concordance cosmology is that we live in a universe with positive cosmological constant. Other interpretations are possible, so that's of course not certain, but it seems like the right place to start. So in the context of string theory, if you're faced with this, the subject sort of splits into two interesting pieces, and the two interesting pieces could enjoy interplay. Okay, so one of them is, how do we arrange the ingredients in the theory to make lower dimensional de Sitter space? We don't live in 10 dimensions. We'd like to make, for instance, 4-dimensional de Sitter space. So I'll always parochially restrict my formulas to that. But how do we do that? Can we do that? And that really, in a glorified sense, it just involves engineering in extra dimensions. There are rules. We know a lot of the rules. It's a question of engineering. Then there's a second set of questions. Here there's more of a space-time diagram of de Sitter space. And the causal structure of de Sitter in the era after holography tells us that there are going to be interesting questions about formulating quantum gravity in de Sitter space. The asymptotics it provides are very different from those of Minkowski or anti-de Sitter space. There is no precise analog of a flat space S matrix or of CFT correlators that we've come to rely on as a crutch to make precise formulations. And this leads to a host of interesting questions, which I'll barely touch on. Okay, but hopefully the two subjects enjoy interrelations. So I'm going to focus on that first question And really importantly, I'm just going to describe how I think about it. I understand different people think in different ways. I'm best qualified to describe my own thinking. I find it pretty simple, so let me lay it out. What is the basic point? We have a question about constructing de Sitter space in string theory. What that means, following the fine tradition of string compactification, we want to find four-dimensional effective theories that arise after dimensional reduction with potential functions V that have minima at positive V. Okay, it's not rocket science. Now, that's not an empty exercise because the theory has constrained ingredients with known energetics. So it may or may not be possible. You have only certain building blocks. And so the first thing we should do is just try to get intuition. Is this possible or not? Which many of us started doing in the late 90s. Okay, so let's discuss some of the ingredients that are known to be in the theory. For instance, for critical strings on a compact manifold of basic size R, one of the ingredients that are present in, for instance, the type 2 theories are Ramond and NS fluxes. How do fluxes contribute to a potential? Well, there are more complicated formulas, but the simplest thing to do is you look at the terms in the Lagrangian containing the fluxes. There are some G's to contract them, and it's quadratic in flux. And if you take into account all the G's and go to Einstein frame in 4 dimensions, you get a potential that scales like a power of 1 over R. R to the 6th plus 2p for a p-form field strength. I'm going to focus on scalings with R. You could also focus on scalings with the dilaton just to get some intuition, because R, the size, and the dilaton are universal minor. So that's one contribution. Now, string theory also comes with D-branes and O-planes, D-branes and orientable planes. And if you have such an object wrapping Q internal dimensions and filling the non-compact space, you get a contribution of the potential that goes like the tension. It can be positive or negative, depending on whether it's a D-brane or O-plane, and the scaling is like 1 over R to the 12 minus Q. Importantly, for instance, if you take a 9-brane filling space in critical string theory, that doesn't just give you a vacuum energy from the tension. The rescaling to Einstein frame in 4 dimensions makes the scaling of that fall like a power of 1 over R, and that's why it's an interesting question to try and get, positive energy vacua. Okay. Now, there are other potentially important sources of potentials beyond fluxes and D-branes and O-planes. A common thing that you first learn when you first open a string theory textbook, and then you conveniently forget if you focus too much on critical strings, is the leading term in the beta function, which goes like D minus D critical. That could be present. It could be important. We often focus, and I personally have focused a little bit parochially on Ricci flat manifolds on Calabi-Yau's, but if there's curvature, for instance, at the KK scale, if you're reducing on a curved manifold, that contributes to the lower dimensional potential. This is familiar to all of you from Freund-Rubin solutions that famously give, for instance, ADS5 times S5. The sphere curvature, importantly, contributes negatively. In theories that have supersymmetry beneath the KK scale, which are going to be my subject henceforth, it's usual to package the potential in a superpotential. One of the terms that's common basically captures this flux energy that I mentioned before, but also it's well known, it has been studied for decades, that there could be non-perturbative contributions to the superpotential. In a supersymmetric theory, for every axion, there's a corresponding kind of instanton. In string theory, those come potentially from worldsheet instantons or D-brane instantons, and they contribute in a way that's exponential in the volume of whatever cycle they wrap in the internal space. Okay, so you can quickly convince yourself that if you randomly were to mix and match the ingredients you have qualitatively and compute the structure of the resulting potentials, okay, it's easiest to get runaways or anti-de Sitter vacua, but in fact, vacua with positive V at minima do occur in toy models without really too much effort, okay? Now, it's important to say that global models that you can really write down don't allow random mixing and matching of these types of ingredients. They're constrained by tadpoles and by the fact that, for instance, the relevant features have to exist in the given manifold you're studying. So the fact that random mixing and matching makes it seem easy isn't at all decisive. There's more work to do. And in fact, the next level of thought, slightly more thought, will reveal a variety of limited, and I'll come back to this, classical no-go theorems. Two famous ones dating from the 80s and about 2000 are those of DeWitt, Smith, Haridas, and Maldacena Nunez, which basically show that in classical supergravity with a variety of ingredients, it's impossible to find stable de Sitter vacuum. Another set of arguments that, for instance, we generated with Taylor and others around 2007, show that even if you include some of the stringy ingredients, not all of them, but you include O-planes and D-branes of certain sorts that occur in certain models and certain fluxes, scaling arguments show that you can get positive energy, but you can't get a classical de Sitter vacuum. Okay, so the list of ingredients there was limited. It's sort of obvious how you go beyond the list of ingredients based on the assumptions of the theorem. Okay, and so now let me come back to this word limited. The limits are obvious, and indeed those of us who started thinking about the subject in 2000 already built those in, and to my mind, we overcame those limits already, with the ideas of the early 2000s, though detailed implementation remains a challenging question. Okay, there are classical constructions that involve additional contributions from geometry and branes. They were discussed in TASI lectures. Gonzalo Torroba talked about a construction combining some of these ingredients together with a one loop effect. And of course, physics isn't classical, and it's hard to stress that enough. That last point isn't only a subtlety that matters for complicated microscopic physics, it matters for macroscopic objects in our universe. On the scale of strings, atoms are macroscopic. It certainly matters for those. It matters for white dwarfs and neutron stars, some of the biggest objects we know. It matters for most mass in the universe. So the quantum effects can be crucial. And I personally think it would be striking if they were in fact crucial to the existence of the basic solution we inhabit, which is true in some scenarios. So one class of constructions in this context, developed in the context of type 2b string theory on Calabi-Yau spaces, involves Calabi-Yau orientifolds with flux. So there's a packaging of the flux energy in a superpotential written down by Gukov, Vafa, and Witten. There are three-form fluxes, and wedged with the homomorphic three-form on the Calabi-Yau, they get the superpotential. It depends on the complex but not Kähler moduli of the space. The low energy effective theory also has a Kähler potential, as any n=1 theory would. We wrote it down in this paper I cite. And alpha prime corrections, so that Kähler potential will always be present. They play a key role in some ideas that build de Sitter vacuum along these lines, and Fernando will talk about that. Now, depending on the geometry beyond this no-scale superpotential of the classical supergravity, there can also be contributions to the superpotential coming from Euclidean branes wrapping certain divisors into space. They were written down in the mid-90s, and they take this basic form I said before. They depend on the exponential volumes of various cycles. And similarly, strong dynamics on branes can give similar contributions with differing prefactors in the exponential. Okay, and that's all well understood. Now, such models most easily yield supersymmetric vacua that you can analyze in various approximations, some of which I'll talk about. But there are also various ways supersymmetry can be spontaneously broken, and that's crucial if we're going to construct de Sitter vacuum. One way of breaking supersymmetry, and there are many, including just using the ingredients I've already described, but I like it for reasons that will become apparent, is supersymmetry breaking by dynamics of branes, because they sort of gauge theorize some of the questions. So a much studied model, I don't have any particular love for it, except that it's a good toy model, is that of putting anti-branes in the supersymmetric warp throat solution of Klebanov and Strassler. We studied this in a paper with Pearson and Merlinda long ago. And the idea is very simple. There's a smooth classical geometry generated by a lot of flux, this warp throat. If you put a small number of anti-branes into it, they carry the sort of opposite supersymmetry orientation to the throat. They break supersymmetry. For small numbers of such branes and small G string times the number, G string times P, there's a stable vacuum visible in the non-compact throat model. Approximations of this vacuum can be made arbitrarily reliable in the non-compact case by choosing sufficiently large flux. Okay, so at small G string times P and at large enough flux, I think it's essentially indisputable that there is a stable non-supersymmetric vacuum. But there are other ideas that tie beautifully to older literature on dynamical supersymmetry breaking as well. For instance, you can use various instanton effects in string theory to break SUSY dynamically by dynamically generating a small scale in models that are more like Phi or Rafferty models of sort of traditional supersymmetry. We did this with Ofer and Mina years ago, and Chris Beam. Others have engineered models of more conventional field theoretic dynamical supersymmetry breaking on branes. A recent paper is by Gregorio, Bertolini, Franco, and others. And in a paper in 03, cited there, we suggested some particular scenario for constructing de Sitter vacua in string theory, but it's trivially generalizable to a similar class of ideas that seems suited for the setting and the ingredients I've described. So what were the ingredients? There's a classical flux superpotential. We choose to study vacua where it's small, okay? And that small number from the classical superpotential will provide us with a control. We need to have instantons or strong dynamics to stabilize the volume. The small w makes it consistent to view those as a leading correction in some cases. In others, Fernando will talk about what happens. And finally, to get de Sitter vacua, we need some small supersymmetry breaking from some source or another. It doesn't have to be small, but small is the best if you want a sub-stringy vacuum energy. And that should shift the potential at some minimum to be positive. Okay, so those are the sort of basic ingredients in those scenarios. And the resulting class of models had the merit that there's sort of a clear cartoon of the effective field theory. There's a Planck scale at a high scale, a string scale beneath that. There's a scale of the overall extra dimensions, 1 over r, the KK scale. Beneath that, there's a flux superpotential that stabilizes things at the scale MCS. It removes the complex structure moduli. There's a scale at which the volume is stabilized, lambda. And then beneath that, you get a hierarchy of other scales at which further moduli get stabilized. But it allows one to organize the analysis and try to break the problem down into analyzable subunits. Admittedly, this is a caricature. If you study a model with hundreds of parameters, hundreds of moduli, there could be multiple scales R. You need to make sure all of them fall in some consistent regime for control. And that becomes an interesting issue in modeling.
Just a comment, you are a little bit over 10 minutes. Yeah.
I'm sorry, I'll be done in about 1.5 minutes. Now, I want to make 2 comments before closing. One is the small w that we introduce in this construction classically to offset the energy, to give control over the vacuum, always played a role in traditional model building in the DSP context, because you need to shift the vacuum energy by a small w just to get cancellation of the cosmological constant. So I don't think that's a qualitatively new ingredient in model building. Now, I want to summarize where the status of these models is quickly. I know Pedro said I have a minute at most. So global constructions are obviously work intensive. They're not evidently beyond reach. I'll say more about that in a second. Many partial problems can be isolated and solved. The statistics of classical flux vacua, coming out of beautiful work of Douglas and collaborators, already showed convincingly a decade ago that small w is attainable. The techniques used are generalizations of those that, for instance, let you estimate volume, numbers of lattice points in a volume on the plane by using the volume of the region. Okay, they're fancier versions of that. And explicit examples that verify that such small w is attainable have been found recently by the Cornell group. Global models with instantons in the right configurations to stabilize all moduli were found again more than a decade ago. The construction of full de Sitter models in this framework was not a direction of much effort. It's not that lots of people were trying, it's just that it wasn't really clear why to do this, since specific global models will not teach you new lessons, but will require careful control of factors of pi. And so there will always be debates about factors of pi. But it's been clear what to try and do for years, and there's no obvious obstruction. And a group, I'm told, is close to doing this. My own list of good problems is not so much let's make a construction and fight about factors of pi. It's more technology development. The more technology you develop, the more obvious such constructions will become. We can classify local DSP models. We should develop techniques to compute exact superpotentials in string theory. It's possible in field theory. It should be possible in string theory. It should tie to beautiful problems in mathematics. We can further explore the rich mathematics of models beyond Calabi-Yau of the sort Gonzalo talked about. And then finally, there are these deeper formulation issues, which I think, frankly, are a big part of the future. How do you formulate DS quantum gravity? That seems like a good problem to me. Thank you, and I apologize for going over time. Let me unshare.
Thank you, Shamit. So let's switch to Fernando sharing the screen while we thank Shamit for the very nice half of the introduction. Yeah, it looks good, Fernando. Although you are still muted.
Yes, sorry about that. Okay, well, thank you very much for the organizers, for Nathan, Pedro, and everybody else. It's great that you managed to organize this conference in a place that is very close to my heart. And so yes, I wish I can also visit you again and go to some churrascarias and so on. And and it's great to have this opportunity to talk about this subject, in particular with Shami. And I will just give a general discussion, so I will not have time to talk about my own work, but most of what I will be saying is related to the work of me with my collaborators, and this is a list of papers in the last couple of years that everything that I will be saying will be influenced by what we have been working on in the last few years, couple of years. Okay, so yeah, so let me start from the beginning, just to be self-contained. So it's two related string challenges. One is model stabilization, the other one is to get the sitter. So model stabilization, I think, has been there for 100 years since Kaluza and Klein. And I can say that probably it's fair to say that it's only in this century that real progress has been made into finding mechanisms to stabilize moduli. So we should consider this as a success of string theory so far. Of course, it is more challenging once you want to also get the sitter, and of course that's Shamit mentioned is partly motivated by observations, which is very good, and not only for observation of the cosmological constant, but the fact that there is a cosmological constant problem that this fundamental theory, like a string theory, should be addressing. And so I think it is good that in this conference we have been given a lot of space to discuss this subject, which I consider very, very important for string theory itself and also for observations. So we have to start with the Dine-Seiber problem, which is something already in the 80s. Dine and Seiber already realized that there is an issue. And the issue is very simple, that a very simple observation. The paper is beautiful. There's a few pages with only a couple of diagrams, but a very nice, clear idea. And the idea is that since we have in general in compactification, you have the volume over the string coupling, which is the given by the dilaton. So for infinite dilaton is zero coupling, for infinite volume is decompactification. And so they argue is that because we know that 10 dimensions and free string theory is a solution, at some point we have to, whatever potential we get for these fields, it will have to run away for those values, and that is unless there are some quantum corrections that will modify your potential. And so for these quantum corrections to be effective, then it has to be at a strong coupling or a small volume for the two expansion, the alpha prime and the string expansion. So then they said if there are minima of this potential, which will stabilize the moduli, then this minimum natural thing is to be at strong coupling. So either we have a strong coupling or we have runaway. However, we are not interested in either of the two at the moment, because first of all, we know that nature naturally is giving us weak couplings. We know that the couplings of the standard model, they all are running towards something which is relatively weak, and we also see hierarchies in nature, and so a minimum for the one string units, or I mean the Planck scale, everything will be the same scale, will not be. There will not be hierarchies, and there will be it will not be fitting with that nature is telling us that the couplings locally for us it has to be weak, and for us it's important because if we can compute in a weak coupling regime, then that's our own limitations, not nature, and so it's nice that the two things match together. So for this and this runaway behavior matches very well with this Swampland conjectures that Kachru and collaborators have been discussing, and Irene and Gonzalo Torroba discussed already in their talks. So this is a major issue, and I think it's important to address the question. So the question is there, and we have to see what to do with it. And so in string compactifications, this is what I can claim is that this is the price we have to pay for string theory for not having free parameters. In string theory, we say what you expect from fundamental theory is that you don't have free parameters. Precisely, string theory has that. But at the end, when you compactify, there are plenty of new parameters that come out upon compactifications. The topological numbers of the compact manifold, the Hodge numbers, also the ranks of the gauge groups, dimensionality of space-time, and particularly the fluxes of different forms. We have several forms, and there have been many fluxes, and naturally they are quantized, and then you have plenty of new parameters that we can play with those integers in general, those discrete numbers, and to try to see if we can there find solutions at weak coupling and relatively large volumes. Okay. The other thing is that there are not only these two expansions, because every single parameter we spend compactification with many moduli, and each of these moduli is an expansion parameter. So at the end, the space, I mean, of the potential has to be including all these other expansion parameters, not only the string coupling and the volume. So, but we have to live with the Dine-Savory problems. So we will never have full control if this is true, which I think is true. But we may have, we can use these numbers to play and to have weak enough couplings and large enough volumes that we can trust our calculations. And so what I like to say is that this Dine-Savory problem is not a disease from string theory, but it's actually a condition. We have to learn how to live with it, essentially. So, and there's nothing wrong except said that we have to make sure that when we do our calculations, we fit into the regime of that fits the weak coupling. So, and essentially, a lot of the developments in this direction has been done in type 2B. So I will just go quickly because Shamit already said a lot about this. So we have classified the modular, the dilaton, the Keller modular, the complex structure modular, and you have n equals 1 supergravity. So you have the F term component is well known, and we know from the Gukov alpha Witten the 3 levels of potential is given by fluxes that depend only on the complex structure and the dilaton. Whereas it doesn't depend on the T fields and the Keller modular. And for the Keller modular, they satisfy this interesting property, which is the no-scale property that you can see because of the scaling symmetries that you have in the 10-dimensional theory. And because of that, this is following the work of Kidins, Kachru, and Polchinski. The F-term potential is positive definite, and is minimized when the DWs are 0 for both the S and the U fields, and then that's how they are supposed to be fixed. And T is arbitrary, but this is only a 3-level result that we know that the no-scale property will not hold after we have to consider alpha prime and loop corrections. And then, but the important thing is that these corrections play an important role because at 3 level, the potential is 0. After you minimize. So the variation of the potential can be written in terms of the variation of the superpotential and variation of the Keller potential. And you can see 3 options. The natural thing is that to have the superpotential, the 3 level is much bigger than the correction, which is usually non-perturbative because of the non-perturbative non-realization theorems of superpotential. The corrections to the Keller potential are usually bigger than the corrections to the superpotential because these are perturbative and these are non-perturbative. And so the natural thing to get is the runaway. So that's the generic thing you get a runaway. And what ways out is that to do what KKLT did, just to tune the fluxes such that the 3 level competes with the delta W with the non-perturbative correction. So that means W0 is much more than 1. And you can do that if you have many fluxes. But then in the large volume scenario that we came out after, you can also play in a different way. You can compare the variation of delta K is competing with the variation of W in the sense that delta K this is only when you have more than one Keller moduli, which is the generic case. If you have only one Keller modulus, you have to do the KKLT story. But if you have more than one, then the delta K goes like 1 over the volume, but delta W goes like the exponential of another modulus, e to the minus 8 tau. And so when you compare these 2 corrections to each other, I mean, you have to compare dynamically. They're chosen to when you minimize the potential, and then you get that the volume is exponentially large, and that's how it's called the large volume scenario.
Normally, you would be more or less on time now, right?
Okay. Okay. So
I mean, on time for your 10 minutes, but over time for the total 20 minutes. So.
Oh, okay. I'll go fast. Okay, so this is the KKLT and LVS potentials, and this is how you get the minimum to exponential large. And then you have features that the fluxes imply that you have still a Calabi-Yau or warped Calabi-Yau. There is a hierarchy, as Shamit said. You have 2 sets of fluxes for F3 and H3 that will give you a big degeneracy, and so on. So to get the sitter, you may have this anti-different brain, as Shamit said, at the tip of the throat, and that has been probably the main proposal to uplift to the sitter. But then there are other proposals. You have D and F terms in the effective field theory with something that can be explicitly realized in terms of T-branes. The complex structure on dilaton uplift can be dW would be not necessarily zero, but small to compete with the Keller potential, with the Keller modular potential. Non-critical strings on negative curvature, as Shamit mentioned, and Eva has been working on it. And so number two, the effects on determinants. So there are several other proposals to get the sitter. And people have, well, achieved that now a well-defined prescription, including branes, orientifers, and so on, that gets you, first of all, the model stabilization, but also the sitter uplift. So since I'm short of time, I will go quickly to the challenges, which is probably just to motivate the discussion. So this is a story that has 17 years or so. And over the years, there have been a lot of questions that people have been asking about this scenario, which is very well defined. And people have questioned several things. For instance, the fluxes by themselves break supersymmetry. So can we trust then the number two of the calculation? You have only a runaway behavior at that time. I claim that you can trust it and you can verify it after your calculation is done, that the whole thing makes sense. But it has been sort of discussions. The other point is that can you do this treatment in 4 dimensions? Everything is an effective four-dimensional theory. So some people believe that doing it in 10 dimensions is better, and I don't see the need to do it to 10 dimensions. But on the other hand, if you do it in 10 dimensions and succeed to get a 4-dimensional result, that is very good. And I think all these people have been making progress on that, and I think that has been making this formalism stronger. The tuning of W0 to be much smaller. You say, how can you get something small from fluxes? But there has been recent progress in several two groups, the Cornell group and the Munich group, to get superpotentials to be much smaller than 1 in a natural way, exponentially. Higher corrections to this large volume scenario. That's something we have been working recently, in the sense that what the large volume scenario is based on the leading order correction that people know, alpha prime, which goes like 1 over volume cube in the scalar potential. People have tried in the past to look for other corrections. So the past 15 years, there have been several corrections computed, and they are all subdominant or the same order, so they don't change the picture. But we have been studying now systematically what will be the effect if there will be a dominant correction, which is interesting. Anti-branes that have been a source of discussion for the past few years. If there is a singularity, the fact that there is no supersymmetry, how you mix it with the unit condensation. And I think there's more or less consensus now that the thing works. I think, except in particular, we can see probably Arthur Hebecker will have something to add. If you have that people call bulk singularities, that is still a challenge. And then the tadpole problem that Mariana Grana summarized in her talk this morning. So I think that those are challenges and subjects of discussion. So an alternative to, so people say, well, what about, is the sitter the only solution? No, it's not the only solution. You can even...
Fernando, I think maybe it would be good to open up for the discussion.
Yes, well, one minute and I finish, yes. Quintessence will be a possibility, but you need to get quintessence, you need exactly the same techniques that you needed for the sitter, and on top of that, you need the runaway. So in that sense, it is interesting to get it, but it's equally challenging, if not more. So okay, to finish, that was open questions. Better control on alpha prime and quantum corrections. Realistic phenomenology, I concentrated only on getting the sitter, but it doesn't matter to get the sitter if you don't have the standard model somewhere. So for that, I invite you, my student, Andreas Schachner, will have a poster session, so we have a recent work on this. Model stabilization in F theory in general, that would be important to take care of issues like a open string model that have not been properly studied. And then populating the landscape. This is, as I say, it's not only a way of getting the sitter, but it's also, in principle, is the only way to address the, I like to say, is probably the worst solution of the cosmological constant problem, with the exception to all the other ones. So in the sense that this formalism provides a potential for solving the landscape to solve the cosmological constant problem, but we need to understand better the structure of the landscape, transitions between different vacuum and so on. And I have been working on this recently, and I found that there's plenty to be understood on the original work of Coleman, DeLuce, and others that I think probably new techniques that people have been using in a positive way recently for black holes using semi-classical gravity. Probably they can be used to understand better this vacuum transition, which is a way to populate the landscape. Okay, I stop here. Sorry to taking time.
Okay, let's thank Fernando and Shamit. And let's open it to discussion. So please, if you are discussing, if you plan to discuss, keep your camera on, raise your hand and wave if what you want to say, to ask or comment is related to what is being discussed right now. So that, and that's it. And I will be calling people, but if Fernando or Shamit find that there's someone that makes a lot of sense to call at a given moment, just override me and call. So Thomas.
Yeah, thank you. So what was interesting, and I think it's good, is that we heard very optimistic view on the Sitter space in string theory. And I think that's probably a good thing, because in recent years, we have been hearing a lot of very, the opposite sound, okay? But nonetheless, I just want to confront Fernando and Shamit with the fact that recent polls in our field have shown that the situation that we are really polarized, okay? There's actually now a way bigger part of our, our community that is believing we haven't succeeded in a single de Sitter solution so far. And then some of them are even thinking it might never be possible. So I'm just saying, this is a situation. What is going wrong? I mean, right, we are doing mathematics. We should, in the end, agree with each other, right? That there should not be any room for belief, but we're in a very awkward situation. And I would just like to have your take on this.
Okay.
I'd want to make a comment quickly.
Okay. Do you start or should I start?
Go ahead, Fernando.
Okay, thank you. No, just I think that that's good that you raised it, Thomas. Yes, my take is you tell me. They say I will not believe any calculation unless you are in the full control. That's what I emphasize the Dine-Saber problem. So then we all agree it's runaway. That's not, but that's something we already knew many years ago. So runaway is a natural thing, or this strong coupling thing. So, but then we have this ingredients of this many integers so that you can play to get to weak coupling. So, so in that sense, if part of the community don't believe unless you have full control of the expansion, so it's good for them. That's the way to think, and that's. But I will not lose any sleep about that. So and so it's I don't think that it's a big problem to trust the expansions, as long as you and this is, as I say, it's a price that we have to pay for string theory not having free parameters, and so that means that you have to work, assume that you have weak coupling, and then check if the result you get large volume and weak coupling that you can trust, and then how large the volume and how weak the coupling probably is a question of taste. But I think that's a very logical and consistent way of dealing with it, and I don't see any reason to.
But then, Fernando, sorry for interrupting. But then, what is weak enough coupling? What is large enough volume? Is it like in field theory? You think of an asymptotic series, and you're happy whenever the number is smaller than 1, or is it really distinct from field theory? Is what some people would be saying. Like the question of Ed Witten about the talk of Gonzalo was about this. Don't we want parametric control? Because maybe this is not like ordinary QFT.
I agree with you, and there is no solution to that. I said if you want to go to as large a volume as you want, you will go to the runaway. And now, yes, but at the end, but we are here to describe nature. We know that the runaway doesn't work in this way because this runaway of the volume or the dilaton is not good enough for quintessence. And I think some people mix quintessence with runaway, which is not correct. I mean, runaway is very generic. Quintessence is not generic. So getting quintessence is as challenging as getting the sitter. And and as I say, it's a condition for string theory. But it's not that we have to work as hard to evade the Dine-Sauer problem. That this is different, and we have to live with it. And so that's what I say. If it's a volume 10 to the 3, 10 to the 4, I will be happy. Maybe you will prefer 10 to the 6. So that is that's a question of taste. And probably Shamit will have something to add, I guess.
Yeah, let me add a little bit. First, thanks for your question, Thomas. I think it's a great question. I'm going to separate it into two parts. Part of it was a sociology question about what people believe. To be a little blunt, I don't really care what people believe. The history of science is that correct ideas will triumph. And so as a function of time, people will do this with their beliefs. Just look at US elections. The other part was about science. And this part I agree with 100%. The best parts of string theory so far have been the parts that can be essentially reduced to math questions. And so far, since the majority of work on de Sitter spaces and constructions that can't be asymptotically weakly coupled or an asymptotically large volume, there's no n like the n of Freund-Rubin, there is always going to be room for doubt, as Fernando said. And there you can debate. And the most logical answer is you should be at the point where you can compute the next correction and convince yourself it's small enough to preserve the sign of the vacuum energy and leave the minimum. But let me point out what I found a little bit frustrating. In KKLT, part of the point of the construction was to isolate certain problems that are math problems at this stage that don't require that kind of belief. The question of whether a classical flux vacuum can have small W naught. This is a math question. It can be answered decisively. It's a question about classical physics. It's algebraic geometry of some relatively pedestrian sort. Douglas and Denef answered it under extremely plausible assumptions, much more rigorous than most of physics, more than a decade ago. Explicit constructions have answered it more recently. They will get more explicit with even smaller values soon. That's a math question. I think it's been answered. I don't think we need to debate it anymore. The question of an asymptotic supersymmetry breaking state in a non-compact throat is a question that can be answered. You may not agree on the answer, but with a small number of probe brains in a non-compact geometry with an arbitrary parameter n, the question can be answered. That becomes a mathematical physics question. So I believe a lot of the mathematical physics questions do have bearing on pieces of these constructions. I'm sure the same is true of LVS and other constructions that Eva and Gonzalo have talked about. And those can be answered. And to my mind, in many cases, they have been answered and shouldn't appear on lists of these discussions because that isolated bit of the problem you can answer. That does leave the global question. And then I agree with you. There's going to be, unless you have a construction with an asymptotic n, a question of whether your control is good enough. And the best you do in physics is you try to estimate the size of the next corrections. I hope that was useful. And thank you for your question.
Since I'm sure this is going to be a fun discussion, let me go over the people that did not participate yet in these discussions, and then I'll go back to the chronological order. So maybe Fernando.
The other Fernando, I guess.
Yeah, Fernando, me or Fernando?
Yeah. Okay. Yes. Please.
Thanks. So yeah, well, I just wanted to make a comment because you put in some of the challenges of all these stabilization scenarios that are around, and it's also one of these math problems that Shamit was talking about, is modular stabilization of complex structure, dilaton, or complex structure in F theory. As a matter of fact, we kind of analyzed this from an analytic way 1 month ago in a paper in the large complex structure limit. And there you can see a bunch of things. I mean, you can actually see how many moduli are stabilized for an arbitrary number of initial moduli. It depends on the rank of a matrix. And actually, when the rank is not maximal, you end up with a scenario, or well, it's one of the cases is a scenario pointed out by Dermitas, McAllister, and so on, where you get that small W naught. So it gives you a lot of power. And one of the things that it shows is that this tadpole conjecture that was presented today by Mariana is simply not true. I mean, it's a very...
Actually, this is not correct. Your vacuum actually doesn't have... Your vacuum has problems. You don't have the metric. You're just assuming some metric from the throat.
I mean, please
let's just Fernando finish. And then...
Sorry, it's not correct. It's a scenario. It's not a construction.
It's a
the scenario and construction. Let's put US dollars and Zimbabwe dollars and two different things. Scenarios are nice. You don't have a construction.
If I cannot talk about... Okay.
No, but
since you are so, I mean, okay, it's really a math problem. So you can go through the math and tell me what's wrong.
There's a metric.
And actually, as a matter of fact, this kind of vacua, they are not even, the first one, they are not even from my paper. They're from a paper of Paltio and collaborators of 2008. So there, for general Calabi-Yau in type 2b, you can generalize it to F theory. It's a math problem, and then you can go and solve it, which is what we did. And actually, the fact that Mariana decided not to talk about it, I really don't understand, guys. I think we should have a more.
We thought about it for a long time,
especially in this conference.
We discussed it a lot. It's a scenario,
example
and we
for
believe
everyone.
there's a problem with the metric.
Please,
you cannot put
I'm not
fluxes with
interrupting you.
positive
I'm
and
just trying
negative
to
charge.
finish one sentence. If you would be some kind of let me do it.
Yes.
Thank you. No, I'm done actually. Whatever. I mean, read the paper and let me know if you agree.
We read it.
I mean, I'm
long
not saying
time
that
ago. We
the
discussed it
not
for
be a
hours.
problem. I'm sure that for many compactification it could be an issue, but the type of conjecture is wrong. And you can go and construct your favorite Calabi-Yau fourfold and apply the techniques that we did and see that, well, this bound doesn't need to exist. We tried to qualify it, but okay, we didn't. We tried to see if how could it work, but we just found counterexamples to it, and we did only scratch a tip of the surface. So yeah, that was my comment. The math problems are nice to look at because then there's no controversy, and this is one of them. Thank you.
Yeah, thank you. It's interesting.
So do we maybe maybe I would suggest Arthur.
Sorry, will you allow a comment, Pedro?
Yes,
or if
please.
not,
No, if your comment is related, yeah, please. Yeah, just wave.
No,
Sorry if I did not see you.
Not to what Arthur said, but just to the general point that Shamit and Fernando made, if you'll give me a minute only. You know, I think it's true that these constructions don't have parametric control in the sense that Shamit was mentioning, Fernando said, and I think it's completely correct that we should, well, at least the constructions I know don't have any parametric control. And I think therefore it's completely correct, given that this is such an important question that we should be very cautious, right? And I think that's a good attitude. I personally have that attitude. But I think one way to try and make progress is to try and compute corrections. Because if you don't have parametric control and you say, I have a small number and it's small enough, then the practical way to do it would be, okay, let's try to compute the first corrections and see, are the corrections small? This is a physicist's way to do it. And I bring this up because I think there's progress, and we heard some of it in Ashok Sen's talk on trying to compute with Raymond, backgrounds and so on. And I think that technology is the kind of thing which might allow us to get more control as we go forward. Okay, that's my small point. Please go ahead.
Let Fernando maybe respond, and then we'll go to Arthur.
Yes, I think it's a good point, Sandeep. So something that we have been working on is that the corrections that we use in the large volume scenario is the leading order in alpha prime that people have computed. They are the leading order in 10 dimensions, but they are the leading order in n equals to 2. But in n equals to 1, people say, well, there may be other corrections that we may have missed. That could be because they are alpha prime cubed, so it may be alpha prime to the 1 or alpha prime square in that sense. And so we have been trying to deal with them, so recently we managed to prove that what is the alpha prime to the 1, which would be the problem was alpha prime square give us something like we call a standard noise scale, that they contribute to the kinetic terms but not to the potential, for an interesting property. But alpha prime to the 1, they may be dangerous. As something that I think we want to make sure that if they're there, what kind of effect they have, or if they're not there. The only thing that we managed to prove so far is that they are not there at tree level. So any correction will come with loops. So it will be loop suppressed compared to the other one. So then again, you have a competition between the two, one alpha prime to the cube to alpha prime 1 with the loops. So you can still cancel each other without breaking perturbation theory. So that's the best we have achieved so far. But I think there's plenty to be done in that direction. And I think I welcome your comment. Yeah.
Thank you.
I think Gary, since he's waving, he would have priority, and then we'll continue.
Yeah, so it's just a quick follow-up to this discussion. So in one of Fernando's slides, you mentioned that you don't see the reason why one would like to go beyond four-dimensional EFT in these string constructions is precisely related to the discussions we are having now. Since we agree that there's no parametric control, it's extremely important to work directly with the microscopic construction and not just stay within the four-dimensional effective field theory.
Well, let me tell you my argument just addressed to me.
I was promised to be able to ask a question.
Sorry?
I have been forgotten. I would like to still ask a question at some point.
Okay, you
okay. So probably Arthur has the same thing. No, I fully agree but for me, I mean, this is an issue about describing Gaussian condensation, which is a four-dimensional strong coupling effect somehow. You want to do it in a formal way in 10 dimensions, you need much more than that. So whereas in 4 dimensions, it's very well settled. I mean, the question is very well posed, and you can answer the question how you can get the effective superpotential and so on in 4 dimensions from Gaussian condensation. People have been working on that for many decades already, and then you know what to do. From 10 dimensions, of course, you need to know to get to understand string theory at that level. You know, the Gaussian condensation is the lambda, which is is something that requires some strong coupling knowledge of the theory. So I welcome people trying to do it. But again, I think that I'm a 4D person, so with the 4D effective field theory, if things work, I will be surprised if things will not work with the 10D. And but I mean, I have nothing against people working on the 10D picture. If you achieve that and you get it, as I said also in my talk,
my comment is not specific to Gaussian.
It gives strength to formalism. So all these challenges that I mentioned, I think they're good challenges. All these are, by being questioned and by being answered, they're making these scenarios much more robust. So I will claim that both LBS and KKLT are far more robust now than they were 15 years ago. And because all these things have been questioned one by one, and people have been finding answers. So I think the more scrutiny we will do, the better. But it's essentially that I hope you probably I didn't say I said it probably too strong in that sense. I will apologize, but I welcome this the effort in 10D.
Well, let me suggest now. Let's go Arthur, then reply from Fernando or Shamit, then Ashok.
Thank you very much. So I do not want to argue with Gary Xu and Fernando Quevedo. I totally agree. The 10D picture, in my opinion, is also important, but I have a much more simple-minded and direct question to Shamit. Because I very much appreciate his comments about a low W0 being established, that can be small, that the throat is probably very much established. And I've always been a big supporter of KKLT being a simple toy model in parametric control, where we really are convinced that things work. And recently there has some criticism of this has come up by Carter Moritz Westphal, then we worked on this, and Carter Moritz again, which basically says that the throat has become so large, if you want it to be deep enough, that basically you are forced to have the Calabi-Yau, the bulk Calabi-Yau, in a strongly warped regime, and then you get either singularities or strongly curved regions, which means exactly that you lose parametric control even at the most superficial level. Order 1 curvature is really bad. And I wonder whether you knew about this point, or whether you follow this recent debate, and whether you have an opinion about this, how to overcome this. For me, it seems to be important, because I would like to sell to a skeptic a clear, simple model, independently of pi factors, as you correctly stated.
Thanks, Arthur, for the question. I want to answer. I'll say what I can about your question, which sadly is very little, and then I want to make some comments about what's in the chat. So first of all, I have to admit I'm otherwise occupied, so I haven't been able to attend all the discussions relevant to this at Strings, or to keep up with the papers from the last month or two. On the issue you're raising, which is when you glue a throat with reasonably large flux, quantum number, I guess n, we could call it, into a Calabi-Yau, does that constrain how large what I'd call the Planck brain in Randall-Sundrum, or the head of the Calabi-Yau, the bulk, has to be, which would have interplay with the instanton effects? I understand the question. I think in a toy model, the most recent work that I know about is this paper of Moritz, which shows that in a model where, frankly, the fluxes aren't that large, a K3 toy model, 7 brains arrange themselves to avoid any particular issue. And, the GKP construction, assuming a large enough Euler character, allows you to make a throat with flux up to the Euler character of the bulk in the no-scale regime with a dialable volume. And I don't see a part of that construction classically that breaks down. Now, your question is about what happens quantum mechanically and can you stabilize consistently with the bulk being not so big when the throat is large? And I have to just admit, I haven't looked into it yet. So KKLT is now an 18-year-old paper. There have been questions, over many years that I've tried to respond to with decreasing, enthusiasm. So that's my psychology. I plan to look. I hope it will be clarified, but I haven't looked. Let me comment a little bit on other questions in the chat, if it's okay. Is that okay, Pedro? Okay. So there's a question about.
I think this one is worth your effort. Actually, my personal feeling, of course.
Yeah,
I think that one is worth your effort.
Okay, I'm not arguing against that. I'm not trying to dismiss anything. I'm busy.
No. It's just a private, really comment that I'm really curious about your personal opinion on this particular issue.
Okay, thank you. I want to comment on some other things in the chat. There's a question about parametric families of de Sitter vacua with really an n that can go to infinity. I don't know of any obstruction. I think others have said that in the chat. I think that would be great. I think they would be unrealistic. Who cares? I think there's no reason they shouldn't exist, and maybe we'll find some. There's a question about what does it mean to have small w naught if after including alpha prime or g corrections, that's not a solution of the classical string theory because there's a tadpole. That statement is correct. If you start with a solution of the classical flux equations that break supersymmetry, a small w naught, and do loop corrections, you'll find, oh my God, the first loop correction leads to a runaway because the tree level solution was a no-scale supergravity. This has been a standard issue in string theory since the 80s. No-scale supergravities arose actually much earlier, in fact, before string theory became popular. And we answered this in 2 papers. GKP gives a precise meaning of what it means for W naught to be non-zero. There is a classical math question. W naught being non-zero but small is an answer to that question. And if W naught is small enough, that resulting effect is treatable in effective field theory as long as there are other scales in the potential that are below the Kaluza-Klein scale. You could treat that problem. And we wrote a whole paper responding to this criticism in 2018 with Trivedi. In fact, I'll give you the archive number. It's 1808.08971. So for that question, you can get my answer at least there. Those are the questions that I saw in the chat. That at least is my attitude.
We can come back to more chat questions.
Say again?
Let's come back to more chat questions a bit later. Let's now move to Ashok, and then we revisit some of the chat.
Okay, yeah. So I just wanted to add a philosophical note that it's good to have parametric control, but I think string theory has many surprises. And so my feeling is that even if you get a factor coupling constant like 1/2, you should not worry. Just do the calculation and see if you get something sensible, right? And I thought I'll remind you that in the study of tachyon condensation, the parameter that we had was 4/3√3. And orders of magnitude, a few orders in the expansion, people got like 1 in 10 to the 10 accuracy, right? So you shouldn't be too keen on parametric control. It's good to have parametric control, but string theory doesn't always work the way a normal quantum field theory works.
Very good, very good.
Thank you, Ashok. Let's go on with still the people that have not participated in previous discussions, and then I will go back to the beginning. So Senarath.
Hi, thanks for calling on me. So I have a somewhat different attitude towards the construction of de Sitter vacua. I mean, it seems the reason why people are trying to construct a de Sitter vacua is because the cosmological constant has been observed to be positive. But this is a measurement done at cosmological scales. String theory calculations are done at the string scale or the Kaluza-Klein scale. When you run down from the Kaluza-Klein scale to cosmological scale, a lot of things can happen. For instance, an ADS vacuum, and we can produce examples of this, can become at very large distances a DS vacuum. So even if somebody proves that that string theory cannot possibly admit DS vacua, that does not rule out string theory. It just tells you that at that scale, you cannot produce a DS vacua, but it may also be viewed as a prediction that the low energy physics is such that at very large scales, you end up with a DS vacuum. Well, that's all I had to say.
Thank you. Fernando or Shamit, you want to respond, or otherwise I'll finally give the word to Ignatius.
No, I agree with Shanta. We are collaborating, so we have discussed this in the past. So I think, yes, he has a good point.
So Ignatius, sorry for keeping you waiting for so long. Please.
I have a comment on the Dine-Cypher problem. I think it's analogy. It's fair to say that it's an analogy with a similar problem in field theory. If you have a field theory and you, with one coupling constant, and you try to compute the scalar potential, which has a discrete, let's say, symmetry, and you want to show that it has spontaneous symmetry breaking. This is never, you can never do it in perturbation theory because precisely the same problem happens, because for weak coupling, you cannot, you have to put the two orders of perturbation theory at the same level. A way out of this in field theory is the Coleman-Weinberg mechanism, in which the theory has two couplings and the logarithmic corrections to the scalar potential. And then we know how it works. So I would like to bring this in the discussion. We tried to implement it recently to a way of stabilizing moduli based on perturbative corrections, but using precisely logarithmic corrections in the scalar potential. And we had a working example in which W0 doesn't need to be small. Okay. Well, thank you, Ignacio. It's very interesting. I saw your paper, but didn't see the analogy with the Higgs mechanism. I'll take a look. Thank you.
Ivano?
Thank you. Hi. So there are recent swampland considerations, and there are two recent papers about this, that talk about gravitino masses versus the effective field theory cutoff, right? And there seems to be a tension, at least in some settings, between low energy SUSY breaking and separations of scales in the effective field theory. So I was wondering if you had any comments about this regarding, you know, the models with low energy SUSY breaking when constructing the Sitter vacuum.
I haven't followed those papers. I have no comments, but maybe, I don't know, Shami or someone else in the I can say something.
Yeah, please. Yeah, and again, remember, please wave when you want to reply to some comment. And
yeah, that's a comment. We have done an old work in 88 with 1988, trying to break supersymmetry with Gaussian models, and we have shown at that moment, that once you try parametrically to get a gravitino match which is very light, then you get a tower of states. But okay, in that case reminds compactification. So it was very old result. Apparently, I don't know if people knew it recently when they.
So there is some sort of tension there between having
but this was
consistent.
The assumptions there were well defined. I mean, were Gaussian models, but it was completely, it was controlled. It was a result within string theory.
Thank you.
Okay, can I make a comment also about that?
Go on, Shamit.
I'd like to say that, you know, in the spirit of an earlier response in the cosmology discussion, there's a piece of string theory and supergravity which is taking the known effects and potentials, computing the results, and seeing what happens. In that framework, with known superpotentials and Kähler potentials, and accepting that one can use approximations that are self-consistent, there's no problem getting gravitino masses beneath the KK scale. Now, in asking your question, you said swampland considerations. I don't know what swampland considerations precisely means. Some of them are rigorous, like bounds on signs of higher derivative terms. I don't think there's any inconsistency with bounds on sizes or coefficients of higher derivative terms. If you mean something more general than that, then my personal attitude would be these are speculations and I trust the calculation. If you mean precise bounds, like these things about higher derivative terms, then that's an interesting question.
Yeah, to my knowledge, what I mean is, reading the papers is like extrapolation based on concrete scenarios that are not necessarily realistic in any way. So it's a conjecture based on some existing models which are not necessarily related to these constructions. So yeah, I get your point. Yeah. Thank you.
Eva?
Okay, so there's a lot that's been said that's already covered things I would say, but the opportunities for parametric control would be things like large D and say topological parameters in negatively curved spaces. But it's not, in my view, it's not needed as long as you have weak but finite couplings. That's also okay in the spirit of sense question as well. I was hoping to maybe move the discussion towards some of the interesting questions that that were brought up on the more conceptual side. So if we use KKLT, for example, and we ask what could be the holographic dual, there's an idea that I pursued a while ago, and I wanted to just bring it up in this crowd to see if anybody can get traction with it. So there's a particular set of fluxes that one has in KKLT, the three form Ramond and S fluxes. And if you trade the fluxes for branes, if you did that in the ADS5 times S5 theory, you would get the ND3 branes, and you would kind of infer that you have this N equals 4 super Yang-Mills theory living on those branes, on their Coulomb branch. If you look at KKLT and you trade fluxes for branes, you get an interesting network of NS5 branes on which you have various strings and string junctions that end. And if you look at the sort of the spectrum of those and their dynamics, it fits well with things like counts of vacua and with how the complex structure moduli stabilization maps to fixed couplings in the resulting 3D gauge theory. So I just wanted to throw that out there because I find it an interesting, in general, interesting approach to how to think about the dual of these examples. So again, in a nutshell, it's trading what fluxes are there for branes and seeing what lives on those branes and trying to infer the dual content from that.
Maybe I can just, I think it's a very good point. Eva, I remember you gave a talk, I think 2003, I guess, in strings. And yes, we went through your talk. And we have a paper actually called KKLT CFT and LVS CFT dualities, trying to make sense of both. In the case of LVS, we found that the corresponding CFT should be extremely well defined with only one operator with a scaling dimension very well defined, and so on. But I think not that much was explored after that, and I think it's a good avenue to try to understand better if there's anything to be learned with the CFT. Yeah, thank you.
I've understood that Ofer Aharoni has a comment to make. Could we allow Ofer to speak?
Yeah, of course.
Well, my comment is a sort of trivial one, but I don't think it's been mentioned, and that is just that all these constructions that give you de Sitter space, if I understand correctly, they can also very easily give you anti-de Sitter spaces that are non-supersymmetric. So in principle, a way to make this whole story on better mathematical footing would be to find the CFT duals to these non-supersymmetric anti-de Sitter vacua that should have large gaps and so on. So if we could prove or disprove their existence, that would of course be a good way to test this. I mean, but again, I don't think that's necessarily a practical way, but at least in principle, that would be one way to make this a well-defined question.
I completely agree. And actually a well-defined math question there is just finding the situations in which a separate KK spectrum with a scale parametrically different from the ADS scale appears in the spectrum in a CFT, and putting constraints on those parametric separations of KK towers. And I think that's a little bit beyond what the bootstrap people can imagine doing today, but I'm not a complete expert. I asked DSD about this a couple of years ago.
Sorry, could I just add to Ofer's point, though, what Dan said in the chat, which I agree with. Those ADS vacua have no reason to be stable. And given that they're not stable, they actually need not correspond to a CFT because those bubbles hit you within an ADS time. Would you, am I missing something, Ofer? Would you agree with that?
Well, I mean, from the point of view of the potentials that you guys draw, I mean, they do look like they're stable, right? I mean, they may have some instabilities, but it's not obvious that they would have instabilities.
Well, the flux decays, for example, would sort of take them. A given one would.
Well, that depends on. It may depend on the situation. I mean, it's not obvious that all of them would be.
Okay, fair enough.
At least I don't think it's obvious that all of them would be, but yeah, that's certainly a good point.
Okay, thanks. Fair enough.
Let me do something because people might have schedules that they might have to leave, and I don't want people not to thank Shamit and Fernando. So let's thank Shamit and Fernando, but continue. So let's close the official informal discussion. But of course, there are so many people with the camera on, so many people with the hand raised. So I think if Fernando and Shamit can stay a bit longer, we can continue a bit more.
I need to run in 10 minutes, but I'm happy to stick around for 10 minutes.
Okay.
Can I say last word? Pedro, I just wanted to thank you and Nathan and everybody, because this format is extremely good for a conference. And I think it's a good thing that eventually people will repeat it in the next rounds of string conferences, because it's created much more lively, and we learn from each other much more. So congratulations.
Let's wait for the black hole information. That should be before we celebrate.
Very good.
Very good. So, but thanks a lot. I'm having fun at least. So, so let's take advantage of this last 10 minutes then. So, Aaron, I'm sorry.
Oh, yes. Hi, thank you. Thanks for staying. I have a question. So de Sitter space has probably an entropy, and it's most likely that in the quantum theory of gravity, this entropy should be associated to some kind of microstates. And in string theory, whenever we have a black hole, we can usually see what those microstates are. So in some cases, we could even calculate them precisely, but nearly always we can find out some what the states are. In de Sitter space, if we have a de Sitter construction in string theory, then how does KKLT manifest these microstates? And secondly, how does it manifest the divergence of the number of microstates as V goes to 0? That's my question, if there's any answers to this.
Does someone would like to comment on that?
Yes, I don't know if I understand your question, but it's.
I know, and sorry, I know Eva had some thoughts on de Sitter entropy. If Eva is still here, she can comment on that. Except she's muted.
Yeah, no, I can say, I mean, so there's a result in this DSDS correspondence that in that framework, it's entanglement entropy between the two sectors. They're large C sectors that are two large C sectors. They interact weakly via gravity, but you can make sense of their entanglement entropy and you get the right answer. What it all means, of course, remains.
That's macroscopic. That's about microstates, microscopic states. In a quantum theory of gravity, we should be able to see microstates like we do for black holes.
Yeah, I'm saying this is like with Ryuta-Kinagi and so on. That's right. This is like the gravitational description, but the thing is, the microstates here we understand as having come from, deforming a seed CFT via TT bar, then turning on the lambda2 deformation, and the count of states at the right level just stays the same. So it's in the 3D case, it's the level delta equals C over 3, or delta plus delta bar equals, equals C over 6. So in that approach to de Sitter holography, that would be the interpretation. The states would be the dressed via some TT bar like trajectories, the dress states at a certain energy level.
This is macroscopic entropy you're talking about always. I'm asking about microstates.
Yeah, it's microscopic. Yeah.
What are the microstates we should see? If we have a de Sitter construction in quantum gravity, shouldn't we see the microstates like we do for black holes in string theory?
Well, we don't see those at the level of the low energy theory, right? So that all this discussion of the solution has not, is not going to show you the microstates directly.
Yeah, but KKLT is the low energy theory that's claimed to be embedded in some string theory construction. So what, and not only where are they, but where's the divergence when V goes to 0?
I'm sorry, where is the divergence when V goes to 0?
Yeah, when V goes to 0, we should get an infinite entropy. So that means that the theory should have an infinite number of microstates visible. Like if we take a black hole in string theory and we send its volume to infinity, we see the infinite microstates.
Well, if you decay toward V equals 0, indeed, the Busso bound goes off to infinity. If you look at these, the FRW extension of DSDS, you find that the number of states indeed grows like the Busso bound predicts. And these are microscopic counts. So there is a literature on this. You can see what you think if you want to, but at least in that framework, that's the interpretation, and those are.
I think the Harvard node has a comment on this. They are waving, so maybe let's go to Harvard.
Yeah, just quickly, I just wanted to. So we have examples of horizons, which are, like in field theory, we just have an accelerated observer, right? You can have a horizon with infinite entropy. You can do this in Minkowski, right? It's just the Euro horizon. So that one doesn't. I mean, we don't see the microstates from. I don't know how to see any kind of microstates in the Euro horizon from any stringy perspective. There might be a way, but. So I'm just saying that there's some horizons that they can have infinite entropy, and you don't see it from the lower interface.
I think it would be nice to have, since I see no one waving, I think it would be nice to have some of the discussion in the chat brought up here. Maybe Leonardo could tell us a little bit about the connection to the bootstrap, and I think it's also related to what Offer was mentioning. I think that would be nice.
Yes, I was making some comments in the chat, but perhaps I can speak up. Can you hear me?
Yes. Yeah.
Yes. So of course, these are extremely subtle questions from a bulk viewpoint, and I think reasonable people disagree. So, for example, there is this famous sequence of ADS4 Bacchia by De Wolf et al. And I don't think there is a consensus on among experts whether they're under control or not, but certainly they're claimed to be under full control. So these are ADS4 supersymmetric Bacchia with a large scale separation, a handful of light states. So there's no issue of stability because you have supersymmetry. There's no issue of being under control because there's a large end sequence with arbitrarily small coupling and arbitrarily small curvature. And I'm really not an expert on the bulk construction to decide, but that's the beauty of the bootstrap. Who cares about the bulk? There's a claim, there's a sequence of three-dimensional conformal field theory with certain properties. Let's try to rule them out or to rule them in. Of course, this is very hard because it's a large N problem, and only recently the tools to incorporate large N in the conformal bootstrap are slowly maturing. And this is what we talked about on Monday, both in my talk and in Simon's talk. But certainly, this was actually my original motivation to do the conformal bootstrap, was to address this question. It was 10 years ago. And so slowly we're getting there. There's also some ADS3 Bacchia with large scale separation where you could hope to use a combination of crossing constraints and modular constraints. But even that is not so easy. We have worked on the modular bootstrap with Tom Harman and Dali Mill, and we're trying to say something about putative theory of pure gravity, but it's not easy, but certainly that's the direction where we want to go. So yes, we can debate forever about the Romans mass in 10D and which orientifolds are appropriate, but ultimately none of that will matter if the conformal bootstrap rules out these models.
Leonardo, what is the reference for the ADS3 case?
Sorry?
The reference for this ADS3 case?
I must put it in the chat, actually.
Maybe I think there's a reference in the Slack channel.
Yeah, on the Slack, there is a discussion on ADS3 already. So you could see in the S-matrix, I think it's in the S-matrix bootstrap channel.
Oh, okay.
Can I add a small comment? Or?
It's in the string universality discussion group on day 3. Yeah.
Okay, thank you.
Thanks, Sander. Someone asked if they could make a comment about this ADS stuff. Of course, yeah.
Yeah, sorry, Pedro. There was Thomas. This is me. Yeah.
Yeah.
Just want to say, given what is written in the chat, it's not just Romans mass. So people tend to forget that you can take a double T dual to these ADS solutions with Romans mass to still get a scale-separated ADS vacuum without Romans mass in type 2A, which then can be lifted to M theory. So it's not just always the usual problems don't always show up. It's not just Romans mass that is the big magic. It can work without. That's just a small technical comment.
Mm-hmm. Okay, so I'll go again. I remind people we are in this informal discussion, and I'll continue with Joseph. I think.
I just had some problem with So the point is, there has been a long discussion about, okay, do metastable vacua exist and so on. And, for many years, there have been moving goalposts. At the beginning, 10 years ago, when I started working on this thing, everybody said, yes, anti-branes are perfect and so on and so forth. Then, we showed that anti-branes are not perfect. They have a back reaction and so on. There's a discussion about that. Then the goalpost moved to a few anti-branes with small back reaction. Then it moved to a single anti-brane. And the point is, I think it's important to study those things. I think it's important to explore those things. The key elephant in the room, I think, at this point is the belief of many people that somehow you can put a huge amount of fluxes and somehow they give you a small tadpole. This is really a problem. And again, I don't think there's any example at this point which shows that this problem can be overcome. And the reason is very simple. When you have fluxes which give you charges, if these fluxes, first of all, if there's a metric where these fluxes can be self-dual, and you can have a supersymmetric or an ISD system, this metric the charge contribution should be everywhere positive on your manifold. Now, if your intersection matrix has pluses and minuses, for example, you can take some fluxes within intersection matrix, plus, minus, minus, and then you put some flux, 1, 1, 1, 1, tadpole is 0. And you think, great, I solved the problem. I put as many fluxes as I want, and the tadpole is 0, and everything is hunky-dory. The problem is you'll never find a metric where these fluxes can satisfy G equals I star G. This is really the problem. It's a problem of the metric. Everybody can write an intersection matrix. Everybody can put fluxes. You can just put them there and say, great, there will be a metric by some magic which will make things work. The problem is you'll never find this metric, and this metric cannot exist. And again, as Mariana was showing in her talk, we have very strong reasons to believe that you cannot just put fluxes and fluxes which have positive contribution and negative contribution all supersymmetrically and get a tadpole of order 1. It just doesn't happen. We tried. I mean, again, we have 500,000 examples of these Fano manifolds. It doesn't work. It doesn't work. And this is really one of the problems. And I think all the talk about W0 and control and small W0, you assume you assume a huge amount of fluxes. You play with them, you get a small W0. But the problem is these fluxes will never ever stay within the tadpole. They will always give you a tadpole bigger than whatever your Calabi-Yau can absorb. And this is a problem.
In view of time, and because Shamit has to go,
even for supersymmetric ones. So people who say KKLT, they have supersymmetric vacuum and so on and so forth. Yes, maybe for a few moduli, maybe. But when you have a large number of moduli, 10 to the 500 and all the numbers people have been floating around, those things will never ever have the moduli stabilized. Those guys are not going to give you vacuum with stabilized moduli. That's what I want to
make two quick comments.
Shamit.
Just two quick. Sorry, I want to make sure. Yeah, two quick comments, and I have to go. One is with regard to anti-brain. I don't know what normal people thought about, but certainly in my paper with Herman starts with P brains with G string P small and studies a probe approximation of brains in a throat. Certainly in writing KKLT, we did not use a gravity solution for anti-brains. The existence of metastable states depends on parameters. If G string P is small, there may be a metastable state. If G string P is large, but smaller than N, G string N, there may be a metastable state. These are logically distinct questions. And I don't see any reason to extrapolate the answer from one regime to the other. And gravity solutions are simply the wrong way to approach the problem of the anti-brain region when G string P is small. You don't replace the anti-brains with flux then. Another comment I'd like to make.
There's a problem with this.
I'd like to make
but Joseph, please let Shamit finish, and then maybe Arthur, and then you can come back. But
is with small numbers of complex structure moduli, which is where people work explicitly purely for convenience. You need to know the periods, and you need to write down fluxes explicitly. There's never been a problem with explicitly stabilizing moduli. With large numbers, the statistical approach of Deneth and Douglas, which is not a construction, but which is far more rigorous than much of this literature, has no problems constructing ISD solutions with small w naught with the ISD constraint imposed. It's possible that the statistics are incorrect or misleading, and that the absence of explicit solutions there will be a real feature. When people go to that regime, they won't find them. I'm highly skeptical. I believe those statistics are highly reliable for the same reason that you can count lattice points. But that's pretty much what I have to say. And anyway, I thank you all for the discussion, and I hope to see some of you later.
Okay.
Thank you, Shamit. Thanks very much.
I have a very, very brief comment, a reply directly to Joseph, okay? So if you allow, which I think you don't in your paper, to stabilize cycles at zero volume, i.e. to have some control singularities, then the tadpole problem goes away. Then you can stabilize a large number of moduli with a relatively small number of fluxes.
Yes,
that's
but
my understanding.
So no, but the problem is when you have singularities, then you have a huge amount of massless fields. So the point is singularities have massless gauge groups.
You're right,
and
but I
your
accept
point is to say
kind
it has all the massless gauge fields around, and then to find some setup where you can put some of the setups, and especially when you have a large number of moduli, you can stabilize. You can get rid of a few of them. You can get a few singularities, and you can get like 20, 30 massless fields. But when you have 10 to the 200,000 vacua, and you have a mega big number of things, you cannot. I mean, if you just put singularities, they'll give you like an order of like 10. They can lower your tadpole a tiny bit. But you'll never, you'll always get a huge amount of massless fields. And what we found in the discussion with Mariana is that, the more singularities you put, the worse off you are. You don't gain anything because when you put singularities, you basically have, you contract n cycles and you get n squared degrees of freedom. And that's a losing game. When your brains go together, the number of massless fields goes like n squared. When you have n brains far away, you put some fluxes, you uplift n of them. So normally you need n squared.
Why can't I have many gauge fields? I don't understand. I don't understand. Why can't I have many gauge fields? That's fine.
But how many do you have? There's a question.
I don't care how many gauge fields you have. As many as you want.
Maybe let's.
Can I respond to Shamit? Actually, there's a problem in Shamit's construction, which is the fact that it's
maybe
not really a probe approximation.
Irina has had her hand up for a long time.
Yeah, exactly. I wanted to. Then is the last lonely hand raised. I think it would be very kind to.
Yeah, thank you. I guess actually I had one comment about something we said very quick, and then one completely different question. That would be great also if Fernando Quevedo can answer it, and also we can change topic this way. So the quick comment was just because we said a lot about parametric control, and I think I completely agree that we don't need to live in parametric control. I mean, that's not the point. I think we all agree with that. And I also agree that no parametric control doesn't mean no control at all and so on. But I don't think this is the point and the relevance of all these works. Because, I mean, at least for me, it's not obvious at all whether we don't have these families of de Sitter backward parametric control. I don't think this is settled. And this is something that at least bothers me. Like there is something we don't understand. And maybe by trying to understand this further, we learn something about the sitter or about how to evade it. So I think this is the point. I mean, like try to understand why we don't find it, not just that whether we need it or not. And then the question I had is that, I mean, we've been discussing a lot about the sitter. I mean, clearly it's very important, but I was wondering, just out of curiosity, like if in the next years, I don't know, we measure experimentally that there is some variation of the cosmological constant, something like this, what is the most promising avenue that we have right now in string theory to try to engineer some quintessence model? I mean, what would be do we have any favorite model, or I don't know, is there any way to approach that problem? I mean, what would we say in that case, no, that there is no de Sitter?
Well, well, for your first comment, just a question of taste. You said you're not convinced, but you're not telling us why not, and you haven't raised any of the issues except for conjectures. So I don't see that there is an issue there. For the second point,
well, it's an issue that we don't know if there is some fundamental reason why behind all these no-goes. But
no, but what is the problem? I just told you what the Dine-Seifer problem is. We can. You want to argue that we have to get out of that problem. There is no way out. The Dine-Seifer problem is there, period. And then the question is to get something that makes sense physically, and that's what we have been talking about. So there is no issue there. The second point, I agree. I think I have nothing against quintessence, and I think that should be should seriously considered. And I think the best candidates I can see are the axioms. There are so many axioms, and we have in our old paper 2 years ago about quintessence, and then there are axioms with a flat enough potential, and there are plenty of them. The axiom coming from the volume modulus is just very flat, and so on. So that can be good candidates, and that would be very, very nice if they can play a role. But I think we have to keep an open mind.
And Fernando, do you need them to be Transplanckian or something? I mean, or is there? That's not necessary.
No. I think the question of how slow they can roll. If they're very close to the maximum, so they can be still rolling extremely slow, and a very, very small height of the potential. So there's no, I don't see any I mean, yes, it's not kind of a generic thing, but it is achievable. So no, I think that's definitely a possible avenue, and I agree with you that lambdas in the M is the simplest thing, but eventually there may be corrections. Like we have, you know, the CMB is not NS is not equal to 1, but it's very close. Or so there's no reason why W is be -1 or but close to -1, but not exactly -1. So yes, I think we have to keep an open mind on that. But I insist that the constructions, it's not that we have to change the game and then build something quintessence models. It is within the same framework we have extra fields that you can have quintessence, but it is not one or the other one. It's just the same technology we have. You can use it for quintessence.
Sorry, can I make a quick comment about that, if I may?
Sure.
Yeah.
Go on.
You know, which is that I mean, we did try our hand at building quintessence models, but, you know, it's really challenging, Irina, I would say, because, you know, the eta problem of inflation is so much worse here, because you have supersymmetry at the TeV scale and you want to protect a scalar whose mass is, you know, at least of order of h square over m Planck square, where h square is the current Hubble constant. And, you know, that's such a tremendous hierarchy of scales that the only way, but I'm not confident of the model, but the only way we could do it is with an approximate Goldstone symmetry, which we could implement through these axion monodromy models. But, you know, we never studied the globe, you know, I won't be confident of it. But I'm just saying it's really, as Fernando, I think, very correctly emphasized, you know, you have the usual lambda being small plus the flatness of the potential, but it's really very flat compared to the Susy-Briggs scale. I mean, this would be a real model building tour de force to pull off, you know, in my view. But okay, there are some axion monodromy type of ideas. I don't know if you want to. Sorry.
Yeah,
we can. The Harvard node is waving. Yeah, go on.
Yeah. Just quick to follow up on that. So then, to Sandeep and Fernando, I guess then you would say that even though maybe quintessence is also possible, that we have like a theoretical prior for de Sitter versus quintessence. Like, would you say that it's easy because it's easier? We should expect more. Like, would you be surprised or somehow more surprised if you get the quintessence? Like, would you be making a, you know, not a prediction, but some sort of prior?
No, I cannot say that much. Yes, I think anything is possible. I mean, the fact that the cosmological constant is non-zero is already so surprising, so crazy that
right.
We have to learn how to live with those things. Yeah.
And I guess people in the 90s were saying that, you know, like string theory naturally led to zero negative cosmological constants.
You're right. Yeah. So you have to be open-minded somehow.
Sounds like a great point to go for a caipirinha. It's unfortunate that we are not all in Brazil, but I think hopefully soon we will. And I think it's a perfect point to close this informal discussion. And let's resume again tomorrow with some black holes. So thank you very much, Fernando, and Shamit, of course, and everyone. Okay. So see you tomorrow.
Thank you, Pedro.
More lively discussions.
Thank you.